Hello and welcome to this session on deep learning. In this class, we are going to explore about deep learning. So deep learning is a concept wherein we create a mechanism into a machine and the machine tries to learn something from the environment, and at the same time it tries to improvise over the time. Like it tries to improvise its output, it tries to improvise the way it is processing that information from the surrounding. So let us try to understand this entire terminology. So deep learning, if we talk about, it is a core form of learning. So it is a sub part of machine learning, and as we know that machine learning is a sub part of AI. So let's try to understand each of these terminologies in detail. What is AI? AI is something in which we want the machine to mimic the behavior of an human being. So AI is something which can do things how a human is doing. In AI, machine takes its own decision based on certain algorithms, data which is fed it to the machine. Now here it behaves as a human being, which means as human being is capable of taking some decision on its own, AI will be capable of doing the same thing. Then how is AI trying to do all those things? So AI is taking this decision based on certain level of learnings which it is getting from the surrounding, and this learning is happening due to machine learning. So machine learning is the core part of AI, where it enables the machine or that AI device to learn something from the environment. So basically machine learning is something where the machine learns something without explicitly programming him to do certain task in a certain way. For example, if there is an activity or a decision has to make made for a person to approve his loan or not, so in that cases we need a trained professional who will take the decision in order to provide him loan or not, right? But when it comes to machine learning, that we are training a machine to understand what is the profile of that particular individual, and it will try to learn and understand different components behind that profile, and based on the previous experience with different profiles, the machine will try to give us some kind of prediction whether to approve this loan or not. Now this entire phenomenon is something where we are not giving any instruction for the machine to take decision based on conditions. Not at all. We are not asking machine to take decision based on a certain set of conditions or conditional phenomenon or something like that. Here the machine is taking decisions based on the previous exposure to the data. So this is how, like, machine learning is something where the data is given to the machine and machine will learn from the data, and based on that data it will take its own decision without any conditional influence of an external object or external body or external person. Now when it comes to deep learning is all about extracting patterns from the data, and this extraction of data has to be very much like the way we are doing it by a human being. So machine learning is something where we actually train the machine based on certain algorithms, make him understand the trends and pattern in the data. But if you want to do a deeper learning, like if you want to do a learning where the data tries to, or the machine tries to learn as a human being is learning, we go with deep learning. And deep learning is a mechanism where we have the same mechanism as a human being is having. Human being has nervous system, and the way human being perceives the information from a nervous system, from its surrounding through its nervous system, in the similar way we want the machine, like we want the machine to do the same. So the perceiving of information is going to change here. It will be different from machine learning, where an algorithm processes the raw data or the information, whereas in deep learning an algorithm will be there, but the algorithm is a network of different neurons, and each neuron is having a certain set of decision making within itself. It processes that information within itself, and after having a collective processing of information, this a output is getting like we get an output. It is similar to human neural network. This is something that we are going to discuss in the upcoming slides. So uh, why we are learning deep learning? So as you can see here, hand engineered features are time consuming, brittle, and not scalable in practice. Like if you see this images in front of you, lines and edges are there in the first image. Second image, we have mid-level features of eyes, nose, and ears. And then we have high-level features of facial structures. Now, when we talk about these features, it is difficult for a human being to go through each and every depth of these images at low level, mid level, and high level. We have trained ourselves since the childhood in a way that we are able to process all this information in a single collective way. But it is difficult for a machine learning algorithm or a machine to understand it in the same way as a human is trying to understand. It is due to the human's ability to process the information due to different layers of neural networks. And that is what we want the machine to do. And that's why we have deep learning, where we will be able to process each and every level of features from a image or from a set of information. And that is why deep learning comes into picture, which helps us to process all three levels of features, even the minutest level of features. If we talk about machine learning performance and the deep learning performance, so we see a constant improvement of deep learning performances because there is a mechanism of feedback in a deep learning algorithm. Deep learning algorithm always tries to improve over the time based on the feedback. Now, what is this feedback? Feedback essentially comes in the form of error. And deep learning has this mechanism of improvising this error over the time. And that is why deep learning, the performance is kind of improving compared to the ordered algorithm or ordered machine learning algorithms. So machine learning algorithm works kind of in a formula structure or algorithmic structure. So it will always follow a algorithmic structure to make certain predictions. It is going to make predictions based on a certain level of input, if and else conditions. For example, if we take this decision tree algorithm, so decision tree algorithms works in a way where it finds out what is the information gain, what is the entropy level for a particular feature, what is the information gain, how much information gain is given by that particular algorithm. So it works fine with the training data. But when it comes to a newer data, the machine sometimes makes wrong predictions. Like there's a problem with decision tree that it is kind of overfitting algorithm, and that is why decision tree will make decision based on the condition that is there on the root node or the decision node. But when it comes to deep learning, the deep learning phenomenon is completely different. It will not have this tree-like structure. It will have a structure in which there will be a certain level of neurons, and the decision will be made at the very first instance of training. And if the decision is wrong, we can simply improvise the previous learnings by adjusting the weights. What is weights? We will discuss it in the upcoming slides. But uh, the phenomenon is in a way that the deep learning algorithm first processes the information, makes some predictions, and if it is making wrong predictions, as we are also making wrong prediction, as a human being is also making wrong prediction. So in this, the machine will actually improvise whatever decisions were made wrongly. So if we are making anything wrong or any wrong decision, so machine will improvise over the time. So that is how deep learning works. So that's why deep learning has a very high efficiency compared to the current existing machine learning algorithm. Maybe in certain cases we will not find that. So, but most of the time deep learning has almost higher performance, always highest performance. Now, why we are trying to learn this deep learning algorithms now? First thing we will try to understand, was this deep learning earlier evolved? Was it there earlier? So yes, it was there earlier. If you can see the history of this deep learning, the stochastic gradient descent was kind of invented or was conceptualized in 1952. Then perceptron and learning weights concept was in 1958. Uh, Backpropagation, multi-layer perceptron, this phenomenon existed in 1986. And deep convolutional neural network, or all this digit recognition or convolutional neural network, took place in 1995. So if you can see the history, it is not something which is new. It was there in the articles, in the research papers. These all things were discovered. So why we are trying, like why we are exploring it now? So the answer to this is basically the availability of resources, the availability of fast computing machines. Okay, so earlier we didn't have this all fast computing machines for computing this complex information, as deep learning involves computation at each layer and each neuron level. And uh, and as we know that human body is a complex mechanism, like we have a complex mechanism of neural network where we sense the information and immediately it is processed in the brain. But we want this to happen in a faster way as it is happening in a human being. So that is why we need faster machines, and at that point of time it was not possible to have such machines. And now we have certain machines which can definitely help us out to a level where we can solve the or do the computation in a faster way. Nowadays, in today's generation, we have a lot of data also available in hand to train the machines, to make it informed, to make it understand what is happening in the surrounding or what is happening in the data. So we have a big data concept. So the data is evolving every day. There is larger data sets are coming. We have different methods by which we can store the data easily. We have cloud devices where we can store the data. We have IoTs from where we can extract information from different devices or something. So the availability of all these tools makes us like helps us out in storing and collection of data. Like the data is now abundant and it is available to us. Second part is processing. So we have very high level graphical units in computer, graphical processing units which can process the information in a faster way. And it is also possible to parallel compute your system, like you can do parallel computation across your system. And due to this parallel processing, high processing graphic cards, high processing computers, processors, due to the availability of all this hardware, it is possible to do the computation in a faster way. And on top of that, we have tools which help us out to kind of work well on the data, or make an interactive adjustment between the hardware and the data. And such kind of tools, if we can see there is TensorFlow, we have programming tools like Python. All these tools are definitely helping us to improve over or understand the data better. So due to availability of all these three components, it is quite possible for us to implement the learnings which was there in the past. So we are implementing all this learning which was done in the past due to this current tools and softwares which are available to us. We are going to start with neural networks at the beginning, and then we will explore different components of this neural network. So we are going to learn about different parts, components, concepts which are necessary in order to create a neural network. Now we'll discuss about the most important topic, that is neural networks. So what are neural networks? Neural, netro- Neural networks are like brain neurons, each neuron connected to every other neuron, which has the capability to understand and solve complex patterns. Now, neural network, as we know that in human being, we can sense all set of information which is happening around us due to the sensory organs, as well as there is a complex architecture of neurons within this body which is connected to the sensory organs. So we can sense something and the neurons are passing the signal to the brain. And due to that, the brain is able to compute or understand or process that information. So here also neural networks are like brain neurons itself, which are actually connected to each and every which are actually connected to other neuron, and the process is to the task is to process the information and pass the information to the brain, and that's how it is able to understand complex information which it is perceiving. Now we will try to understand how neural networks are actually there. So neural networks are the heart of everyday technology, like we are using it almost everywhere. Like if you want to understand that, we have automatic car plate recognition system where it can automatically recognize what is the number plate of car. If you want to decode handwriting, we have applications. If you write something, it will automatically detect what it is written. So if you want to detect the handwriting on postcodes or somewhere, if you are writing, so we can implement this neural networks to recognize the patterns of handwriting. um, there are programs that employ neural network are also capable of learning on their own and adapting to change the conditions. So there is a huge application of neural networks, and the way we have combined the hardware and software along with the mathematics which was done in the past, we are capable of now doing things which are kind of imaginary in the past. Now how does this emerged? So image recognition requires human intelligence, something that machines lack, however complex and powerful. So if we talk about recognizing images, machine it is difficult. Machine can store the images, but it will not tell you what is that image. And it is complex because images are not at all going to be stationary all the time. It keeps on evolving, so it requires humans perceptions of understanding what is there in that image. Now if you want the computer to get better in solving this kind of problems, as they are fast and we want them to do, because as they don't get tired, because machines can do a lot of processing easily without getting tired. If I ask someone to process 10,000 images and label what is there in each image, for a person it will be difficult because he will not be able to like match up the speed, or he may get tired, and even he may lose interest over the time, and there is a possibility of error as well. But when it comes to machine will do it like in a blink of a seconds. Now the problem of complex uh, the artificial intelligence, like what is artificial intelligence? So artificial intelligence is all about problem, computer and human. Problem is complex mathematical operations, and if you want to talk about image recognition as an example of it, then computer for a computer it is easy to do complex mathematical operations. Compared to humans, human will find it hard. When it comes to image recognition, machine will find it hard or computer will find it hard, but humans will find it easy. So the problem here is complex mathematic calculation cannot be done by human being easily, but a machine can do, and image recognition can be done easily by a machine, by a human being, but not by a machine. It will find it hard. So we want these two kind of like we want the machine to get this ability of understanding the images. So here we'll try to understand how a human brain learns. So you can see the structure over here. In this structure, you can see there are dendrites, synapses. These structures are dendrites, synapse. You can see here we have a synapses. We have axons and we have nucleus in a human neural cell body. So if we talk about a human neuron, it has all these structures, primarily this nucleus, dendrites, axons and synapses. Now these entire structure is something which will help to process information from surrounding in a human body. Like human body conducts the information due to this neural cell body. Now if we talk about a neural network, we have in a neuron, in a human neuron, the collection of signals from other structures or other environment is done by dendrites. Okay, dendrites will collect information. The neuron basically sends out spike of electrical activity through a long thin strand known as axon. So axon is something which will pass the electrical signal, because see, the information that we are talking about is not in a physical form, it is in a form of electrical signal. So the information is passed through this axon into thousands of branches of other neurons. Okay, and at the end of each branch, a structure called as synapse converts the activity from the axons into electrical effects that inhibit or excite activity in the connected neuron. So that we have synapses which helps to convert the activity of the axon into electrical effects. So whatever is the information, synapse will help you to convert that information and send it to the next processing neuron. So these are the three components which are important in a human neural network or human body, which helps us to process the information. Now we will try to compare or create a neuron which is similar to human neuron. Okay, so if we talk about biological neuron, we have this axon, we have this nucleus, and we have dendrites. These are the three important components which actually engage in getting some information from the surrounding, processing the information in the nucleus, and passing it on to the next neuron through axons. So let's talk about the similar thing in an artificial neural network. Now, what is an artificial neural network? Artificial neural network is something where we will take the information from the surrounding and we will process the information, and then we will create a output. This is what we are doing in a biological neuron. So artificial neural network takes the information like this from surrounding and it processes in this neuron. We call it as a neuron. This is an input layer. This is a neuron in which the information is processed, and after processing the information, an output is generated which will go out. Okay, so this is how we can kind of map how a biological neuron can be mimicked using a machine and create an artificial neuron. It is very much obvious that we cannot have the same level of processing that a biological neuron is going to have, but we are able to do the perceiving of information to a level that we can have similar functionality that a biological neuron has through a artificial neuron. So uh, the efficiency and everything of biological neuron, no doubt it is going to be high, but artificial neuron does similar kind of activity, and it eases out the way humans are doing things. So basically both the things will do similar activities on a scale. Now let's talk about perceptron. So the simplest and oldest model of an ANN is called perceptron. So perceptron is a linear classifier used for binary prediction, that is supervised learning. And this means that in order for it to work, the data must be linearly separable. However, most of the real life problems are not going to be linear in nature. And when it comes to model a very complex non-linear boundary multi-layer neural network, basically helps us out. Okay, so perceptron is a linear separator. A single unit of neuron that we have seen is a perceptron. So perceptron is a single unit, and it is kind of linearly separable in nature. And what is linear separation? Basically, which means we have a clear indication of something, dividing the data into multiple parts. So if we talk about this, linear separation is all about clearly having a clear division between the data. So perceptron learning rules state that the algorithm would automatically learn the optimal weight coefficients, and the input features are then multiplied with this weights to determine if a neuron fires or not. So basically, perceptron is a single neuron which takes information from the surrounding, and there are certain weights which are initialized, and it automatically adjusts the weight based on the activation function and the optimization done, and it improvises the weights based on the error which is passing over. So basically, as I discussed, the neural network has a mechanism of feedback where it improvises the learning based on feedback. So error basically helps us to adjust the weights. So let us understand what is a simple neuron. So a perceptron is artificial neuron with many inputs and one output, and this perceptron is the structural building block of any deep learning network. So it has two modes of operation, basically training mode and using mode. Neuron is trained for particular data or patterns into the data where it will learn something, and second is using mode, where when a taught input pattern is detected, its associated output becomes the current output. So basically, neuron has two mechanisms over here. If you see the structure, this is the input mechanism where it will perceive some information from the input or the surrounding. It learns that information and it processes that information based on a certain formula which we are passing in the neuron, and it will generate an output. Okay, it will generate the output, and based on that output, the dependence of like how the data is actually dependent over each other, or how the associated of this data is based on the output data is actually learned. Now we will try to understand about predictor. Predictors are something or are algorithms which helps us to predict an output. So basically, the output can be any continuous output, or classify something yes or no. So these are certain level of predictors. So simple predictor machine, a predictor machine takes an input value from the surrounding or any input, and based on that input it makes the predictions. Okay, so it processes that input and it predicts the output. For example, a machine that converts an Indian currency to its equivalent dollar or something. So here the machine basically is a predictor where it will take rupee as an input and it will pass dollar as an output. So the predictor machine here, as we are talking about the rupee and dollar conversion part, so there will be a multiplication factor associated with this predictor. So we can see a linear relationship between the dollar and rupee conversion, where C is that constant. As you can see, rupee is equal to dollar into C. So as C is constant, so we plug random values for C and compare it with actual values. So $1 is equal to 63 rupees to see the calculation, basically what we do is, if you take C is equal to 50, the error actually here is 63 minus 50, which is 13 error. So while making the guess of 1 rupee will be how much dollars or $1 will be how much rupees, we are making a mistake of 13 units due to the assumptions of the constant factor as 50. So the objective of our algorithm or the predictor is to remove or reduce this 13 units. We will try to reduce this 13 units so as to have or reach it towards 63. So 1 rupee is equal to dollar into 50. The calculated dollar value is going to be 50, but the actual dollar value is 63. So here the error is 13, and we are optimizing things in a way that we reduce this error. Now, if we do the same process is done for C is equal to 60. Now we know that C is equal to 50 is wrong. So we will change the value of C. We know that there is an error of 13. So we will change the value of C randomly and increase it. So if we are increasing it randomly and put it at C is equal to 60. So in this case, 1 rupee is equal to dollar into 60. So it comes around $60. And this $60 actually has to be $63, but here we are getting $60, which is closer to the observed value. So in this case, the error earlier, which was 13, is now reduced to 3. So this is how the simple prediction can be done over a machine, and this is how a predictor machine works. Now we'll talk about going to the next level, where we know that there is a lag and still we are not up to the mark. There is an error of 3 units, and we want to minimize this error and make a constant or a correct prediction. So what we will do is, we will change C is equal to 70. So when we will do C is equal to 70, so rupee is equal to dollar into 70, and it is coming around 70. But in our case, the actual value is going to be 63 for the conversion that we are calculating, and that is where we get an error of -7. Now here the error is reduced so much, like it is -7, it is way too below. Then we know that this -7 indicates that we are on the other side of the prediction, where we are making higher predictions. Now we are not making correct predictions. Yeah, it is higher predictions for the dollar value. So here also we see that we are not at up to the mark, and -7 basically tells us that yeah, we have crossed that particular boundary on which we are supposed to be. And that is where we now again change the value of C. So earlier the C value was 60 and the current C value was 70, and as this value is going to change, so it has to be somewhere between 60 and 70. So we will keep the C value as 63 right now, and if we do the prediction, and we can see that error value is going to be 0, because if C value is 63, so 1 rupee dollar is equal to, the dollar value is equal to 63, and actual dollar value is 63, therefore the error is equal to 0. So the model works fine and perfect for C is equal to 63. Here we can see that rupee dollar conversions are not up to the mark, which are wrong, but these are just hypothetical situation that we are considering, and that is why the value should not be considered in that serious way. But yeah, this is how what we are trying to predict. We are trying to predict that the value of the C value, which is a multiplier factor to predict something. So if you want to make a correct prediction of a value, the multiplier factor has to be optimized in a way that it reduces the wrong predictions or errors. Now we will talk about classifier. Classifiers are used in cases where we do not have to guess a value, but we have to guess a class, or we need to consider yes or no, or whether we just want to make a prediction on a particular class, if this is going to happen or not, if this belongs to a certain category or not. So let us consider distinguishing between two kinds of coins. There is a coin A and coin B based on their weight and diameter. So the weight and diameter of the two coins are given here. So coin A has diameter is equal to 3 and the weight is 1, and coin B has diameter is equal to 1 but the weight is 3. So let us try to understand how we are going to make the prediction. If we try to visualize these two coins on x and y axis, keeping diameter on x and weight on y, we can see that coin A is in red color and coin B is in green color. And if we try to build a linear separation between these 2 points, we can see y is equal to ax would be that right separation value, where the y is equal to width and x is equal to diameter and a is equal to the slope of the line. So basically, we are trying to predict the value of weight based on diameter, and a is the slope that will help us distinguish between the values. Now let's try to build up a simple classifier that will help us to separate between these two coins. So consider a coin which has diameter 3 and weight 1.0. So we will substitute the value of y is equal to ax, and if we keep y is equal to 1, so or the weight value is equal to 1, so y is equal to 2.5 into 3, which is coming to be 0.5. So the value of that particular coin is going to be or the y value of that particular coin is going to be 0.75 based on the weight. So for a coin of diameter 3, the weight should be 0.75, which is less than the actual value of 1, and in our case we want the value of x to be greater than 1. So to separate these two categories, so we will take the weight as 1.1, and therefore the error that we are going to talk about here is, so target value is 1.1 but our value is 0.75, which is 0.35 is the error that we are getting. So 0.75 we have got because we have considered the weight as 1 and we have put the value of y and x over here, or we have put the values correspondingly values here over here, and we are getting y value as 0.75. So if we are taking this random assumption, so 1.1 minus 0.75, the error is 0.35. And if we talk about, and if we put this on the x and y axis, where x axis the diameter is there and y axis we have weights, so the value or the line which is y is equal to 0.75 and the actual desired value where y is equal to 1.1, the value difference between y is equal to 1.1 and the y is equal to 0.75 is basically the error, which is 0.35. So this, out of these two lines, we can see that correct prediction is not done by the y is equal to 0.75, and that is the reason we are getting an error due to this line. So we can see this relationship between a and e, where the linear function of the classifier is y is equal to ax, and as we want to design an equation that can correctly classify, the equation with the line t is equal to a plus delta a into x. So the error can be formulated as t minus y, that is ax plus delta ax minus ax, which is delta of ax, and delta a is going to be e by x, which is 0.35 divided by 0.3, which is coming out to be 0.1667. So what is this delta a? Basically it is nothing but the error divided by the value of x. So we are trying to find out the error divided by value of x, that is our delta a. So amount of increase required in a is, basically the a value has to be increased by 0.25. The value is 0.25. It has to be increased by 0.1167 in order to get 0.3667. So the value of, or the increase in a has to be 0.1167, and the final outcome should be 0.3667. So same procedure for coin B is going to happen, which has diameter 1 and weight is equal to 3.0, and when a is equal to 0.366 and x is equal to 1.0, we get the value of y is equal to 0.366 into 1, which is 0.366. So the target value to be less than 3. So we take the value, so we will take the value 2.9, and as the error is 2.9 minus 0.36, which is 2.533, and similarly here also the new value of error or new value of a is going to be 0.366 plus 2.533, which is 2.9. So now what is happening here? We are trying to find out the value of a. in a way that trying to understand how much error also it is making. So the initial line along with the two updated lines can be plotted as this y is equal to 2.90, and the second line we can see the classifier, the line that we can see here is uh, so the classifier is not like the desired one, and substituting each value randomly is a tedious process. So we can see that the line keeps on jumping from here to here, and it will keep on jumping like this. So we need a constant separation so as to give correct separation between these two categories, that is red, green and red categories. So to introduce so we need to introduce a moderating factor called the learning rate. Now what is happening is, while we are transitioning ourselves from here till here and then again back, so we are not going to get a proper classifier. So for that we require a learning rate so as to moderate the speed of learning, or moderate the speed of improvisation. And learning rate will basically learning rate, so we will have delta A is equal to L into E by X. So basically learning rate is going to be L into E by X, and L will moderate now the speed of finding out an optimum classifier in this linear classification. So if L is equal to 0.5 and A is equal to 0.25, then delta A is going to be 0.5 into 0.35 divided by 3.0, which is coming to be 0.0583. Now if you want to update the weight of A, it is going to be 0.25 plus 0.0583. so constantly we are going to keep on changing the value of A based on this learning rate, and it will moderate the flow of coming over an optimal value of A. So from training example of coin A, where y is equal to 0.3083 into 3.0, it is going to be the value is 0.9350, and for coin B, 0.3083 into 1, the value of y is going to be 0.3083. So the desired value is 2.9. So if we minus it, 2.9 minus 0.3083, we can see 2.5917 is coming for E value, and delta is nothing but to E by R or E by so sorry, delta A is going to be E by X, and that's why 2.5917 divided by the X value, which is 1.0, and we multiply this with learning rate here as well. So finding it for A or finding it for B, in both the cases we are multiplying it with learning factor 0.5, and now the delta A value is 2.59, and if you see the new value of uh, A, so 0.3083 plus 1.29 value. So basically here there is a mistake. We need to get the value as 1.29. Okay, so when we add this value, we are getting the value as 1.60. Now the new value of 1.60 is something that will actually tell us the value of A and B as well for both coin A and coin B. So simple predictor. So we have seen that how these predictors are actually going to work. So basically what is happening, I will tell you. So we have a coin A and coin B, and we want to guess it whether it is going to be a coin A, whether it is going to be a coin B, based on a linear separation, and we want a fine separator between these two green and red dots. And what we do is we are optimizing the values of the weights that will help us build up this line, and this line is a linear separation. So as this is a line that separates out these two categories, so it will be made out of equation y is equal to mx plus c, or y is equal to mx, considering that this passes through the origin or the zero line. And the weights are the important factors basically here. But what happens is, when we are trying to find out an optimal line between line which can separate out these two categories, it becomes difficult because of the fact that the line does not converge to the optimum value. If these two lines or if these 2 points are very much close to each other, so it will be a very difficult for the line to separate it out. So that is why we require the phenomenon of adjusting the weight, these weights on time to time basis to get an optimum line. Now when we are trying to get an optimum line, this optimal line, the weights are adjusted accordingly on this optimum line, And as we are getting this optimum line, uh, we need to moderate the flow by which how this optimum line is reached out. So for that we require this phenomenon of learning rate, which will moderate the speed by which we will come to an optimum line which can separate out these two classes separately. And that's how it works in a simple classifier. Now if we talk about a multiple classifier, so simple predictors are classifiers that takes input and do some calculations and give an output. So they are not enough to solve the complex problems to be implemented by this neural networks. So for that, multiple classifier use Boolean logic in machines and take multiple inputs and give one single output. So basically what happens is we take multiple inputs and there is a logical function that will compute the logical calculations to so as to find out the probability of this set of inputs to be in a certain category, and based on this probability values we decide out on a particular class. So that happens in a multiple classifier where we take Boolean logics in machines. So now let us consider the example of AND gate, which only has true values if both the inputs are true, and let us try to understand it with the help of this tabular arrangement of data. Now in this AND gate we have input A and input B, and the value of input A and input B is 0 0. If the value is 0 0, both the values are 0, that's why it is going to be 0. If it is 1 1 0 1, the value both the sides as we can see that one side is 0 and other side is 1. So as per the AND gate it has to be 0 1. Okay, it has to be 1 1 in order to be true. So if any one of the value is false, so it will be 0 only, and 1 0 the value is 0, and 1 1 both the conditions are true. That's why we can say that the output is also going to be true. So the output is equal to true happens only if 1 1 is going to occur, and that's the only one scenario in which it happens. Okay, so if you want to divide this entire sheet or entire chart in a way that it separates out, so this is going to be our prediction value 1 1, and this is how a line has to be developed. So we are in a search of this line which can linearly separate between these four data points based on the value of input A and input B. uh, Dividing this line we have to ignore because 0 0 is going to be 0 all the time, it is not going to be true. So these three belongs to a single category, this belongs to some other category, and this is how the correct line has to be. Please ignore this line. And so we are in search of a line which can linearly separate this logical. So multiple classifier build up a logical understanding between the data, and based on this logical input only it will draw a conclusion or create a classifier. Now we are talking about the OR gate here. In this OR gate we can see in this OR gate we can see the values of the truth table of the values for input gate A and input B is given here. So if the input A has value 0011 and input B has value 0101, so if both the values are 0, so it is going to be 0, otherwise it is going to be 1. So in any case it is going to be 1. So in this case we can see the logical dividing line, this line that we are talking, current line, this logical line basically divides perfectly the data points into two halves. That is, the first part, this part basically is for 0 only, and these three red dots are basically indicates the category as 1. So this is how a separation, this linear separation basically helps us out to build up the correct guessing of the data, whether it is going to be in the category 0 or whether it is going to be in the category 1. Now XOR gate only has true if either one of the true values are going to be true. If both the values are true, it is going to consider as false. If both the values are false, it is going to consider as false. It requires only explicitly one value has to be true, and we can see it in the truth table as well. In the truth table, we can see the input gate input value A, input value B, and input value C. And input A the values are 0011, and input B the values are 0101, and input C the values are we can see that if both the values are 0 0 in input A and input B, the final value, the output is going to be 0. If one value is 0, other value is 1, it is going to be 1. One value is 1, other value is 0, it is going to be 1, because it is XOR gate. And if both the values are true, still it is going to be 0, because it accepts only one and another should be 0. And if we talk about logically separating it out, so right now we can see that it is difficult. We can see there needs to be a dual boundary in order to separate this data out. A single boundary is difficult, we can see, or either in this case we need a separator which can definitely consider like this, a sigmoidal structure or something like that in a single category, and these two in a single category. Some kind of non-linear separation requires to be there in order to separate. But here also the separation of this data is based on logical gates and logical values. So that's how the separation happens here. So we to fix this problem, we require two classifier, as I mentioned, or we can have a multiple, or we require a non-linear separator. So we require two lines which can separate these two data, and we can see the green ones are out of these two lines, and anything falls within these two lines are red categories. So here also we will try to understand. So basically classifiers are something which will divide the data in order to have data on both the sides, one on the particular category and another on the particular category. So now we will try to understand about a single perceptron, and we will see how we use one line to separate out the different regions. Here we have a perceptron with certain values. We can see x1 and x2 as the input, and 1 being the constant output or weight or bias that we are adding here. We have a summation symbol here, which indicates that there is some level of filtering going to happen, or some level of processing of data is going to happen, and then there is an activation function symbol here which is given. So these are our inputs. This is our neuron where we process the information, input information. This is basically an activation function, basically how we process the information. And here we have an output as a predicted value. So W0, if you consider, is equal to 1. And as we see, the input value as 3 and minus 2. So 3 and minus 2 are the two values. And if we want to process this information, we will pass this set of input or the matrix in a function g, and this function g, the value is going to be w0 plus xt of w. Now this w0 plus xt of w basically helps is the value or the input value that we have received, and we when we pass on this value as into this function. So basically if we pass 1 plus the xt or the transform of x matrix, so transform x matrix is going to be uh, x1 x2 as the values, as a transformed version of x1 x2 as a matrix or a vector, and w is the weight, so weight 3 comma minus 2. So we get an equation that is 1 plus 3 into x1 minus 2 into x2 based on the values of 3 and minus 2. So this is just a line which is a two-dimensional line, and this two-dimensional line basically kind of helps us out to do some kind of prediction over a data. So a single perceptron helps us out to create this value or get this value, which is a two-dimensional line, and we apply some processing or functions over it. Now similarly, if we process the data, if you use one line to separate out this different region, if we consider that particular line 1 plus 3x1 minus 2x2, we can see that if x value, and we are putting the x value as minus 1 and 2 over here. So 3 into minus 1 minus 2 into minus 2, if we are putting it, so this value point, data point 1 minus 1 comma 2 is going to be in the upper half of this line, and it will lie, and it will have g of minus 6. You can see the value, the total value is coming out to be minus 6, and the function we are applying g. After applying this function, the value suppose is going to be 0.002. So basically this value now indicates where or in which category this point is going to lie. So single perceptron has this value. So this is how the calculation actually happens in a single perceptron. And similarly here as well, so any value, if we see, if the z value is less than 0 and if y value is less than 0.5, in this cases this is going to be in this blue category. And if z value is greater than 0 and y value is also greater than 0.5, so in this case the data point will fall under this green category. So there are two categories, that is blue and green. And this is how a single perceptron builds up or divides the data. It has a simple logic. Basically, there is a function which will divide the data into two halves based on the line that we are going to create. Now we'll talk about multiple classifiers. So perceptron, which is a two-dimensional figure, can't represent XOR problem because XOR problem required two lines. So we can solve this problem with either of the two methods which are used in machine learning, by adding dimension in support vector machine using polynomial kernel. We can use a polynomial kernel, or by adding layer in neural network which is used for complex operations. So we can add two layers, like two neurons basically. So in either of the case, we can use first one as the polynomial kernel using sub SVM, or the second one, as we said, that we can have two neural network layers. So let's understand what is this layered neural network. So as we are going into layered neural network, we will try to understand how we can have layer over another neural network layer. So many simple neurons are interconnected in form of layers. So as we are talking about a single neuron can do the classification for AND gate and OR gate. But when it comes to XOR gate, where we require a complex classifier, we cannot do with the single neuron. So we require another classifier and another neuron, okay, another layer of neurons which will do the other operation, other task. So each neuron takes inputs from many before, and it provides signal to many more. Okay, so this is how the mechanism works in a neural network or in a central nervous system of a human being, where it takes information from the surrounding and it processes out the information and passes it on to another neuron and something like that. So here we have multiple layers of neurons which keeps on passing out the information from one place to another places. So as in layered neural network as well, we require multiple layers. And the functions and weights are best represented using matrices instead of equation. So neural network can represent XOR gate, for example XOR gate line 1 and line 2, or line 1 NAND line 2 we can have, which can separate out the data based on line 1 and line 2, and or if line 1 and line 2 is not there. So we have a layered neural network in which there are certain terminologies that we need to understand. First is node. So node is each neuron in neural network is called as node. Each neuron is a node. Weights are the signal strengths or importances for that particular input value. So it basically tells us how much importance, how much weightage is there for that particular data. Then we have input layer, where we have the first layer as an input layer. Then we have output layer, which will throw us output. So these two layers are physically connected with the external environment, which is input layer taking information from the environment, and output layer which shows the information to the output world. In middle of all this input layer and output layer, we have different or several levels of hidden layers which are not at all connected with the environment, which are only connected with the input and the output layers. So it keeps it acts as a backend for giving out information, and actual processing of information happens in this hidden layers. Now we will talk about activation functions. So a single neuron basically takes an input from the surrounding, and based on this input it gives an output. But based on this input it gives an output. But this output, as it is going to pass, is based on a certain set of processing which is there done there in the neuron. So this processing which is done through a function or mathematical function, and that is called a activation function. So there are several activation functions which basically helps us to process out information in the data. So For this activation function, it may also require certain level of threshold values so as to process the data based on that function. So the first activation function that we are going to see here is sigmoid. So sigmoid activation function is similar to that logistic regression function, and the objective of this function is to either get the data into a sigmoid pattern where it generates a sigmoid equation or S-shaped equation. And sigmoid activation function gives two value, that is either 0 or 1. The formula given is 1 plus 1 upon 1 plus e raised to minus x, z, where z is basically the input data that we are going to pass, or a linear combination of that input data. So sigmoid activation function helps us to get the data into linear fashion. Then we have hyperbolic tanh function. So hyperbolic tanh function basically is given by e raised to z minus e raised to minus z divided by e raised to z plus e raised to minus z, where again z is nothing but our input linear combination of the input value to that neuron. And this tanh function basically gets the value between -1 to +1. This is also used to get the data or the values between -1 to +1, in which basically we are getting all the polarity, like we are considering the polarity of data. Then we have rectilinear unit of which is an activation function again. And this is a very interesting function because rectilinear unit helps us to serialize the output and reduce the linearity in the data or in that data. So we have whatever is the linear combination, what is the input data, uh, we are going to find out maximum of 0 comma z. So 0 is the value if in case the z or the linear combination of your input data z value, if it is negative, so it will consider 0 as the value. So basically the output of a rectilinear unit is also going to be 0 and 1. But understand one thing, this is not going to be an sigmoid. It is not similar to a sigmoid. Sigmoid is different, where it calculates the value and based on the information in that data, it gives the value 0 and 1. It scales basically the value based on the formula which is given, and here it just finds out if the data is greater than 0, less than 0, it is going to convert the data into 0, and if it is greater than 0, it will keep it as it is. So this is how a activation functions are in this. These are the three important activation function. And why we need activation function? So the purpose of activation function is to introduce non-linearities into the network. Now what is non-linearity of a network? So let us first understand what is a linearity in an prediction or in a prediction operation on in any kind of operation. So linearity basically, when we are trying to consider certain things in a certain way, like pre-assumptions. So linearity indicates pre-assumptions, considering that if this is going to happen, this is also going to happen. Okay, such kind of assumptions are good to do predictions, like it helps us out to do the prediction. But when we have cases when we do not see any linear dependence of the data over each other, in such situations the algorithm will fail if we are considering the linearity part. Okay, so we need to introduce certain level of non-linearity so as the algorithm doesn't try to build up a linear combination all the time. It will also consider non-linearity over the dependence of input and output data, and that is why we require activation function. Activation function reduces the non-linearities. Activation function reduces the linearity, and that is how the model will now the new learning algorithm will now not have any pre-assumptions. It will not be biased at all. It will be considering everything as a new situation, and based on that new situation it will keep on changing all the time. So if we wanted to build a neural network to distinguish the point, as we can see here, we see that there is no linear separation between these 2 points. If we assume, like we can see that there is a polynomial kind of separation like this, but there is no linear combination or separation of data. A single line cannot distinguish between the data. So in such situations, the neural network may fail, and that is why we require activation function, which can help us out to reduce such kind of anomalies while predictions. So for that we require the purpose of the activation function is to introduce, as we know, that non-linearity. A linear activation function, as we see that it is not able to clearly distinguish between the red and the green points, but when we see about this non-linear separations of data, it will definitely build up a separation where it will clearly tell us what is green and what is red category. So this is how it will help, this is how the activation function helps us out to get separation. And here we have certain activation function. First function that you can see, that is unit step function, and uh, it is also useful. We can see per unit step function, the graph for the step function is given like this. As we can see, step function basically is something where we give a bias over that particular value. Like if the value is 0, we will have the value as 0.5. If the value is 1.5, it will get the value as 1. Like we are just giving a bias just above that particular input data. Then we have signum. Signum is a function where we are getting the values like this. -1 to 1 is the value for this activation function, and here also it is an perceptron variant. You can see the values are coming as -1 to +1. Then we have linear separation. Linear separation, we have the example is Adeline, and linear regression lines are basically this linear separations of data. Piecewise linear, where we have support vector machine, where we can see separation not just in a single line vector, but yeah, if we can have a multiple separation levels of this line. So these are piecewise linear regression. Then we have logistic or sigmoid activation function that we have discussed just now, which has the values like 0 to -1, and it is always in a form of sigmoid activation function. And sigmoid activation function is very commonly used because it helps us out to clearly separate out the data based on a probabilistic value or a logarithmic value. Then we have hyperbolic tanh function. Now hyperbolic tanh function is a multi-layer neural, it is used in multi-layer neural network, and it basically gives us the value between -1 to +1, but it gives a value based on the input data that is passed onto it, and very commonly used in neural networks and useful as well. Now we will talk about a three-layered neural network, as we can see here. So in this neural network we have three layers. First is the input layer, then we have hidden layer, and then we have output layer. Now let us try to understand what is happening in each of this layer at the neuron level. So at a neuron level, you can see there is a input coming to 1 as 0.9, 0.1 and 0.8. I will be discussing about only the neuron 1 over here and what is happening. So this neuron 1 is getting three inputs, that is 0.9, then it is getting 0.1, and it is also getting 0.8. Okay. So if we talk about this neuron 1, this neuron 1 will have certain activation function which will process out the information, and this information is passed on to the new hidden layer. It can be passed here, here as well as here. It is passed to all three neurons if it is fully connected, and all these three neurons will have information from each of this neuron like this. And again the same thing is going to happen for the third neuron as well, third input layer as well, and it will process the information and it will transform the output in the next output layer. So what is happening here is the weights that we are going to decide here, weight for 1 comma 2 and weight for 2 comma 1 and weight for 2 comma 2 is weight for 1 1 and weight for 1 2 and weight for 2 1. Basically all these three weights are kind of getting over this input layer, and this input layer process out the information. Now when we talk about multiple neural networks, each neuron becomes a judge. Each neuron has its own weights and biases, and it has its own activation functions. Activation function can be same in a single layer, and based on that activation function, but the input value is also going to be same, but the weights are different for each neuron in that layer. And based on the weightages and importance given according to each and every neuron, it will adjust, or the output will be different, and this output is shared over the next hidden layer. Now this hidden layer becomes a very deeper level analyst. It analyzes the input or the output. It analyzes the output given by each of this layer 1, 2 and 3. Now due to that, what happens is this output information, when it is processed, we have a second level of verification or processing the data, and this will go to the layer 3. And similarly it will go for layer 3 from each of the output, and this level 3 output, we have probability value, we will have different probability value 0 0.4, 0 0.3 and 0.3, and based on these values we will decide in which category this particular data actually lies. So based on this we decide whether in which category this data point lies. So multi-layered neural network will always have this feature of having multiple layers, and each layer will do the processing at every neuron possible. Layered neural network. So let us take the input of depth ratio and assume random weights from the nodes. So input 1 is 0.9, 0.1 and 0.8, and the input which we are talking about, which is then hidden input, it is going to be 0.9, 0.3, 0.4 from the first layer, then 0.2, 0.8, 0.2, 0.1, 0.5, 0.6 as the values. So we have passed only the values 0.9, 0.1, 0.8, but in the input hidden layer, you can see there are multiple inputs now for the weights, because each weight will be associated with the each neuron as it is connected with the next layer. And the hidden input for the next layer, or the hidden layers output, weight output, is going to be 0.3, 0.7, 0.5. So we will assume the random weights here, and initially it is always random, and the output at the first node is the input to the hidden layer, and this is what is happening here. So x hidden is equal to w input hidden into I. So this is at the first neuron level, or the first layer of this neural network, and these random weights are multiplied with the input values, and we will get an output value for each and every neuron. Okay, now these neuron will transform the output to the next hidden layer. For example, here the O hidden layer, the hidden layer where we apply the sigmoid activation function on the hidden layer output, and whatever is the output that we have received, the sigmoid activation function is applied over it, so as to get values as 0.761, 0.6 and 0.6. Now these three values are the output of the hidden layer, and as this output is received to the output layer 3, which is the output layer, and this output layer again has three different level of input hidden layer or the weights, and these random weights are again multiplied with this output of this hidden layer. So when we multiply this, we get some values like 0.97, 0.88 and 1.254. Now again, for the sigmoid activation, to pull the output from the output layer, we apply the sigmoid activation function over the output layer, and on this, after applying the sigmoid activation function, it converts the value on a scale of 0 to 1, and we get the value 0.726, 0.7 and 0.778. Now as we can see, there are three outputs over here, and based on this output, the category of that data is decided. So as we can see, it is in the first category, so it will be considered into the first category of the data. So if we talk about all three layers, each layer is doing what? It is taking some random weights, it is multiplying that weight with the input value, and once the output is received for each neuron, this output is passed on to the next layer, where this next layer will also have the random weights. This output of the first previous layer as well as the weights of the current layer will get multiplied, and then we applied an activation function based on whatever level of hidden layer or whatever layer it is. So if it is an hidden layer, we will apply ReLU activation function or rectilinear unit, and this rectilinear unit, when we multiply it with the data, so it will get transformed to some other level, and as it will also create an output of vector. This output vector is passed on to the last or the output layer, as we have only 3 layers over here. The output layer will multiply the data with the weights, and as it is multiplying, these weights are again random weights, and when we multiply this, it will again create an output. And on that output we apply the activation function, which is the sigmoid activation in our case right now. And this sigmoid activation function will cover this data or convert this data into either in the form of either into a value of 0 to 1. So this is how entirely the phenomenon of a neural network computation happens. Now we will talk about backpropagation. So we have discussed it earlier. There is a mechanism of feedback when it comes to neural network, which is not usually there in the other algorithms. And this feedback mechanism essentially helps us out to improvise over the time. And how it does with the help of back propagation. Now what is back propagation? So we have seen in the previous slides how the network was, or how the information was processed in a neural network. So information was processed where we have input layer which interacts with the input or the surrounding, and we have the hidden layer which processes that input which is extracted from the surrounding. Then we have output layer where we transform the input data and convert it to readable output, and that readable output is what we get as an output. So basically this is how a neural network works in the feed forward manner. So this is what a feed forward neural network is. Now there is a phenomenon in neural network where it wants to improvise over the time, and this is how it can be done with the help of backpropagation. So backpropagation is a mechanism where the network sees what is an output and it compares that output with this actual output for that particular data. And as it compares, so it understands what kind of lack of accuracy is there in the output generated by the neural network and the output which is there, um, actual, like what is the actual output, which what is the desired output. So as we see that the algorithm understand what kind of problem is there, what kind of lack is there. So in order to improvise this, it goes in the backward direction to improvise that particular error. And to minimize the error, it will move in the backward direction. So it will just keep on adjusting the weights in this backward direction, and it improvises over the time. So backpropagation consists of the repeated application of two passes basically over here. So in this step, the network is activated in on each one activated on each on one example, and the error of each neuron, the output layer is computed. So what happens? Uh, it actually identifies the error at each level of neuron, and in this step, the neural network is used for updating the in the forward pass. It basically, so backpropagation consists of repeated application of two passes. First is forward pass, and second one is the backward pass. As we saw in the forward pass, the network is activated on one example, and the error of output layer is computed at that example. And in the backward pass, in this step, the network error is used for updating the weight. So it wants to update the weights, and starting at the output layer. So initially it will start the update of the weights at the output layer. The error is propagated in the backward direction through the network layer by layer. This is done by recursively computing the errors and finding out the local gradient at each level of the neuron and reducing that gradient so as to get minimal error. So this is how backpropagation actually works. And MLP, multi-layer perceptron, we can see the forward propagation here. In multi-layer perceptron with one hidden layers computes the function. For example, we are applying a sigmoid activation function, as it is an sigmoid, as we discussed that it is a multi-layer perceptron. So we are applying sigmoid activation function over the activation function, or the function that we are getting for a single level of neuron. So sigmoid activation function of xw1 plus b1 into w2 plus B2 is the value, as we can see for the first layer at the one hidden layer values. A multi-layer perceptron with two hidden layer computes the function, that is it is done by applying two sigmoid activation function over the function or the value or the z value. And generally an multi-layer perceptron with n number of layers will have n number of sigmoid activation function applied over the hidden layers or the input data. Like this, during forward propagation, the activations or the output from neuron of one layer are passed to the neurons of the next layer. So this is how a forward propagation in multi-layer perceptron happens. And in the backward propagation, what happens is, as you can see, that we are applying multiple level of function over each and every input data or that linear combination of input data. In the first hidden layer, we can see linear combination onto which we are going to apply our hidden our activation function. In the second also we are applying two activation function over that additional activation function. So this actually keeps on happening. Okay, so as we add more and more activation function, more and more as we add more and more layer, for each and every layer we will have to have more activation function for each and every neuron, which is actually kind of recursive in nature if we are seeing. So during now we'll talk about back propagation. So if we have understood, like we have applied multiple level of functions on the output of each and every hidden layer recursively within itself. Okay, so it is going kind of incognito when we talk about applying this function. The function is applied incognito like that, and this is how the output is processed in the forward propagation part. Now let us talk about the backward propagation part, in which during this backward propagation, during training, the error of the loss function is calculated at the output layer. Okay, at the very output layer we calculate the error, and we need to minimize this error. Now how can we minimize this error which is happening at the output layer? So in order to minimize this, we need to change the so error has happened because of certain assumptions of weight. So we have initially done random assumptions of weight, as we discussed in the first calculation part. So we are doing random assumptions of weight. So as we are doing random assumptions of weight, we need to change these weights now, because the random assumptions are giving us wrong values. So in order to change these weights, we update this weight based on the gradient or the error that is happening. So error of the loss function can be minimized by updating the network parameters, which is weights of the connections between the neuron, and the gradients of this loss function is calculated with respect to the weights using this back propagation algorithm. Now at every level we are going to partially derivate that particular error or gradient based on the previous weights. So each neuron will be associated with a certain level of weights, and we will do partial derivative in order to get that weight, and the partial derivative is done in a way that the gradient has to be minimized at that level. So we will apply the gradient descent at each and every level of or each and every level of the parameter to update the weight performed by using the weights and bias. These steps are continuously repeated up to a fixed number of iterations or until the differences of errors are optimal or acceptable. So in two successive iteration is less than predetermined threshold. So we can keep a threshold below which we can accept that particular data, or we accept that level of convergence at that particular point. So on this in this back propagation, basically this iterative this keeps on happening iterative for this happens iteratively to adjust the weights in such a way that the gradients or the weights are minimized. So back propagation, we have two parts, that is network activation, which is feed forward part, and the second part is error propagation or the backward step part. So in both the parts we are basically getting this data, or we are propagating the data. Back propagation adjusts the weights of a neural networks in order to minimize the neural network, that is total mean squared error. So the objective of this back propagation is to reduce the error. Usually it is mean squared error, and that is done with the help of this partial derivative with respect to the weights that we are going to update, or the weight that we are going to change at each level. Now, back propagating errors. So back propagating errors at multiple nodes, both the output nodes can have errors. So T1, T2, let us consider it as predicted output. O1, O2, let us consider it as actual expected output. And E1, E2 are errors. So in our case here, E1 is equal to T1 minus O1 and E2 is equal to T2 minus O2. And our objective is to reduce this value E1 and E2 so as to have a very closer values of T1 and O1. So E1 is split into two using the below ratio. As we can see, W11 upon W11 plus W12 is to W12 upon W11 plus W12. So here E1 value, as we can see, E2 is split into two using the ratio, like W21 upon W21 plus W22 is to W22 upon W21 plus W22. So these are the two splits for each E1 and E2. E1 is the error corresponding to the value T1 and O1, and E2 is the error corresponding to the value T2 and O2 for the actual and the predicted value. Now, we are backpropagating the errors, backpropagating the error in case of multiple layers, the error which is split as per the proportion will again be split based on the weights in the previous layers until the input node is reached. So, for example, we have input layer 1, input hidden layer 2 and output layer 3. So whatever is the proportion, or when the errors will be split as per the proportion, will again be split based on weights in the previous layer. Like once the propagation or the weights have been adjusted here, it has to be done for the consecutive previous layers also. So E hidden one will be again be equal to sum of split errors on links W11 and W12. So E1 into W11 upon W11 plus W12 plus E2 into W12 upon W11 plus W12. Now this is the hidden layer error, and it is again dependent on the value of error 1 and error 2 which we have received recently. Now propagate the error back to where they were originated in order to correct the output. So if you want to correct the output, current output, the weights of the previous layer are not sufficient to be getting updated. We need to update the weights of the previous layer as well. So it is not just about the current layer, it is the weights of the current output layer, but it is again the weights of the weights which are passed on to the hidden layer as well. So the following illustration, like we can see that here in this illustration, we have three simple layer: input layer, hidden layer and output layer. And the weights of this output layer is getting identified or adjusted based on the value of the output layer. Output E1 is 1.5, E2 is 0.5. We need to reduce this errors, or in order to reduce this error, we need to change the weights again. And again, you can see the newer weights will get optimized based on the previous weights and the gradient value or the error value. Now this has happened at this hidden layer or the hidden layer, and between the hidden layer and the output layer. Now this has to happen again in the input layer and hidden layer. So it is going to happen in the consecutive next or the previous layer as well. So here also W11 the weight needs to be optimized. Now if we optimize this at this level also, then only we will be able to get an output which will be less of error. So this is what is expected. Now, if we talk about the matrix representation of backpropagating error, so the starting point of error that emerge from neural network at the final output layer, here we only have two nodes in the output layer. So these are E1 and E2. E output is equal to E1 and E2. The first hidden node's error has two paths contributing to it from the output layer. The error signals E1 into W11 divided by W11 plus W21, and E2 which is W12 divided by W12 and W12, which is, these are the two errors that we have talked about. Now the second hidden layer node has two paths contributing to its error, that is E1 into W21, W21 plus W11 and E2 into W22 divided by W22 into W. So this consecutively keeps on adding if you add multiple hidden layers, and that's how the hidden layer ratio also becomes. So W11 upon W11 plus 2 W12 upon W11 plus 12 and W21. So here we are getting a matrix representation of an error. So this is how finally the error matrix looks like. So error matrix is now based on the two level of weights optimization has been done. Now the multiplication of output errors En with linked weights Wij, the larger the weights, the more of the output error is carried back to the hidden layer. So as we are increasing more or the weights are more in the output layer, if it is more, so output error is carried backward to the hidden layer. Now where we have even which is dependent on W11, even into W11, W11 plus 21 would become much simpler as even into W11 than the transpose of matrix itself. So here what is happening, the multiplication of the output errors En will be linked with output or the weights Wij, and larger is the weight, more of the output error is kind of processed or carried backwards in the hidden layers. So the matrix approach to propagate the error back can be represented by using hidden error is equal to Wt into hidden output into error of the output. So this is how the equation of the hidden layer is. So for hidden layer, the transpose of the hidden weights, output weights of hidden, the transpose of the output weights into error of the output will give us the error of the hidden layer. And this is how the matrix transformation works. And due to this, the weights are kind of computed. So now we have the challenge of getting an error at each level, and this can be done with the help of this formula, which is a matrix representation of the propagating errors. Now we will talk about chain rule. What is this chain rule all about? So chain rule is a concept in derivatives which will help us to derivate the data if it is sequential in nature. So let's try to understand the chain rule. So we're talking about backpropagation. So backpropagation computes the chain rule in a manner that is highly efficient. So let us consider a function g where r is r, where r basically represents a function, and where y is equal to g of x and z is equal to f of y, and f of y basically is nothing but g of x. That's why z is going to be function of g of x. So basically what is happening, y is a function of g of x and z is a function of y. So we can see that it is actually incognitive. It is kind of linearly related across each other. And that's why if we want to derivate z with respect to x directly, it is not possible because z is dependent on y and y is dependent on x. So such kind of dependency is there. So z is a function of y. That's why if we talk about the chain rule of derivatives, so z has to be first derivated with respect to y, and then y has to be derivated with respect to x. This is how the derivation or the chain rule of derivative works, where a direct derivative of the data is not possible at all, and due to the dependence or the linear combinations of the functions over each other. Now let us assume that we have multiple paths for our data or the data nodes. So we have y1, we have x, then we have y2, then we have z. So if I want to derivate z with respect to x, so directly also it is not possible because z is in combination with y2 and y1 directly, but not with x. And that's how it is not possible to get the derivative of y directly. If I want to derivate y with z with respect to y1 or y2 directly, that is also not possible because z is coming due to y1 and y2. So z, if I talk about z is equal to y1 and y2. So if I want to derivate or if I want to do the derivative of y1, I have to first derivate y with respect to x as well. So what we will do is we want a derivative of z with respect to derivative of y1 plus derivative of z with respect to derivative of y2. But y1 and y2 are combination of the functions with respect to x. It is actually happening due to x. So y1 will be we need to derivate y1 with respect to x as well and y2 with respect to x as well, as both of them are the combination or functions of x. So if we see the multiple paths of this derivative, so dz by dx is equal to dz by dy1 into dy1 by dx plus similarly dz upon dy2 into dy2 by dx. So this actually tells us that the combination of this derivative is, even if it has multiple paths, we have to follow the linear partial derivative function or the chain rule derivative function. Now we will talk about the vectorization of this chain rule. So vectorization also is possible for this chain rule. For example, it can be notified or it can be represented in a vector form. For example, I want to derivate z with respect to x, which is directly not possible, but z is in linear combination with x. And this linear combination of x can be through multiple paths, or it can be through multiple levels as well. So for that I can represent it as dz by d partial derivative of these z with respect to partial derivative of x1 is equal to summation of partial derivative of z with respect to y1 and partial derivative of y1 yj with respect to xi. And in vector notation also we can represent it by having linear combinations of or vector combinations of or partial derivatives of z with respect to x1 x2 x3 and xm if we have multiple variables or multiple level of inputs. And similarly here also we can have the same formula will get replicated, only thing is the x value will keep on changing, x1 x2 x3 and xm. So this is how the notation of an vector formation of your linear regression is. And it is actually, it can be denoted with the form of delta of xz, and which is nothing but partial derivative of y with respect to x, a transform of the partial derivative of y with respect to x into delta of yz. So this is how we can do the vector notation of the data. Now vectorization and chain rule, we'll try to understand what exactly it refers to be. So this is our denotation of our function, which is a chain rule or partial derivative function, which is given as a partial derivative of y with respect to x and transform of that vector value and into delta of y with respect to z. Now this partial derivative of y with respect to x is the n into m Jacobian matrix. Now this is actually a matrix value, this particular value, and we are taking a transformation of it. Gradient of x is a multiplication factor of Jacobian matrix partial derivative of y with respect to x with a vector that is the gradient partial derivative or delta of y of z. So we are multiplying this value with the gradient. And backpropagation consists of applying such Jacobian gradient products to each operation in the computational graph. So in the backpropagation, what we are doing, we are applying such Jacobian matrix or Jacobian gradient products to each level or the each operation in the computational network. In this in general, this needs not to apply to vectors but can apply to tensors. So we have tensors of values in a neural networks on which we are going to apply this Jacobian product of Jacobian product or Jacobian gradient products at each level of the neuron. So now we will talk about gradient descent. So we have understood the concept of Jacobian product and the partial derivative or vector operations or the chain rule of derivative. Now we will try to understand how this gradient descent works in case of our partial derivative function. So there are plenty of weights which needs to be adjusted in a network of neural network. So the trial and error method cannot be used directly to update the weights as in a simple classifier. So as we are doing in a simple classifier that we have just seen, so we cannot do the same mechanism for the gradient descent as well. Like we cannot do it for neural network because there are lots of weights to be tried out, and in order to update all these weights it is not possible practically with this trial and error approach. So for that we require gradient descent method, which will reduce the gradient values and keeps on updating the weight values by reducing the gradient. So gradient descent is an optimization algorithm which is used to find the values of the parameters or the weights of a function that minimizes the cost function. Okay, so cost function is nothing but error. By mistake it is a weight, it has to be error. This is error. Okay, So the objective of this gradient descent is to reduce the error, minimize the cost function or error in a way that it optimizes the weight. So error can only be changed if the weight is going to change, because the input data is not at all going to change. So that is why weight needs to be optimized. And the derivative, so we have initial coefficient is equal to 0 and weight is equal to function of this coefficient, and delta value is equal to derivative of this weight. So derivative is to find the slope of the function to know the direction to move the coefficient values in order to arrive at a better weight in next iteration. So what is happening, basically I'll tell you. We have a coefficient value and we have minus alpha into delta. Alpha basically is our learning rate, which tells us how much speed the algorithm should converge to the minima or the minimum value of the error. So alpha basically governs the control of flow of the algorithm, and delta is our value that we want to reduce, that is the partial derivative or the derivative of that function, or the derivative of error with respect to function. Coefficient is the new this is the old value of your weight or the parameter, and this is the new value of the parameter. So new parameter is equal to new weight is equal to old weight minus alpha into delta, where delta is derivative of error with respect to the old weight. Now this process is repeated until no further improvements can be achieved. So it keeps on happening iteratively again and again till we reach to a level where we cannot have lesser error or cost function. So we want to reduce the cost function in a way that it is least. Now updating the weights. So to update the weights, gradient descent concept is applied, as we can see. And in this concept, as we can see, initially suppose we are at this point and our error is maximum. This particular line basically represent error and this is weights. So we keep on adjusting the weight. So here the weight is very high, and for this higher level of weight the error is also high. So there is a possibility that the error can be minimized to a very least value, which is at this point. So what we do is we keep on adjusting this. So we need to shift this value weight towards the left side. Okay, so as the weight shift left side, so this is the left side, this is the new weight, and on this weight you can see the error is kind of less compared to the previous one. This was the error 1 for this point, and this is the error 2 for the second point. And as the error is less at this point, we can see clearly that yeah, definitely this algorithm works out well. Now we need to move to the next part, which is the next point where we want the algorithm to move. But we see that 2 point, the error at 2 is also not that least. We can go and we can do better here as well. So what we do here is we will shift towards the left again, and when we shift towards the left again, the error gets reduced further, and this is the level 3 at which the error is least. And beyond this point the error cannot go below, like it cannot go below. So we need to reach out at this point, okay, at this point where the error is least. And this is what is done in gradient descent method. So gradient descent, the formula as we can see here is alpha into e into sigmoid of ok into 1 minus sigmoid of o into O of t. So these are the weights. This is how the delta of weight is computed. So we need to find out the change in weights with respect to the change in the gradient. So we need to change the weights based on the change in the gradient value or reducing in the gradient value. Now we'll try to understand about updating weights. So we have three layers, that is input layer, hidden layer and output layer. So when we are talking about this weight, delta weight jk, which is the change in the weight, it is equal to alpha, which is the learning rate, into e, which is the error at k instance, into sigmoid at the o of k, okay, and 1 minus sigmoid of o of k into o of t. O of t is the transpose of the output value. Now when we substitute all these values, we get the new weights, which is W11 and which is 2 plus 0.006. So the new weight has to be 2 plus 2.006. Earlier the weight was 2 and now we are making a shift in the weight, which is going to be 2.006. So this happens continuously. So we have to iterate the procedure multiple times until a minimum error value is reached, and that is how we are going to do. So we need to tune certain parameters. So the hyperparameter, yeah. So this is how it has to be done. We can see there is a slight modification in the weight which is happening, and this slight modification will tell us, okay, how much improvement it is going to make in the error value. Now we will talk about hyperparameter tuning. So the hyperparameters to be tuned for a neural networks are how many number of hidden layer we want, what is the number of neurons in each hidden layer, and what are the activation function that we should use. uh, will be like most of the time in hidden layer we are using ReLU activation function. So the activation function for the output to be chosen as one of these based on the needs. So sigmoid activation function will give the values as 0 and 1, 0 to 1. Hyperbolic function will give the value -1 to 1. ReLU will give the activation function or the value between 0 to infinity, and leaky ReLU will again give you value between -infinity to 0 plus infinity. So these are certain activation function you can choose based on the set of values that you want at that particular network or the layer. You can decide number of hidden layers based on the computing speed and the complexity of data. If you have more data, try to use higher level of hidden layers and the number of neurons. So if you want to do more and more processing of the data, more hidden layers can be used. If you want to dive deeper into the data, more hidden layers can help us out. If you want to have multiple layer or multiple level of analysis over the data, you can have more number of neurons. As you increase the number of hidden layers and neurons, the complexity of calculation also increases, and that is where the space also increases. So it is always recommended to use optimum value of hidden layers and neurons. If you use less, so you are doing less computation, you are not exploring the data much. So you need to balance out this all things in a way that you get optimum value. So it has to be fine tuned. There is no thumb rule as such to get hidden layers. Hidden layers ideally are the number of neurons in the hidden layer are ideally similar to the what is there in the input layer, or maybe one or two neuron extra, or 10 neurons extra. And number of hidden layer depends upon what level of computer, what level of detail you want from the data. So it keeps on happening, like you can have 10, 15, 16, depending upon what level of detail you are trying to capture from the data. Now we will talk about deep ANN, or deep artificial neural network. So what is a deep neural network or deep artificial neural network? So number of hidden layer and number of neuron in each layer decide how deep is the network going to be. So here we can see a set of input layers, features, and these features are x1, x2, x1 2, x22, and x1, x2, sign of x1 and sign of x2. These are certain input layers, and we can see deep level of neurons. So we can see this is the hidden layer 1, hidden layer 2, hidden layer 3, hidden layer 4, and hidden layer 5. And this is our output layer contributing towards getting this output. And we are in each level of neuron or each level of this hidden layer, there are neurons which are processing this information based on certain level of weights, and these weights are kind of giving some output, and this output is used in the next layer, and it is happening over each and every consecutive layers. Deep ANN or deep neural network basically has deeper level of neurons or deeper level of hidden layers. It will have more hidden layers into it. As many number of hidden layers we have, that many number of neural networks or that many deeper level hidden operations are happening. So we can see this is an interface to show how this input data is. Now we'll talk about deep neural network in detail. So a deep neural network is a multi-layered neural network, which means it will have multiple hidden layers. Usually there are hidden layers, many hidden layers in deep neural network. There is no consensus on the number of hidden layers to have in that data, and that is why it is called deep net. However, more than two hidden layers are sufficient in order to call it as a deep neural network or deep ANN. Due to the presence of many layers and associated non-linear operations applied to the weighted input to the activation functions. So the inputs to the network is transformed at the output through a complex non-linear challenge changes. So basically, as it is having multiple layer of evaluations, at each layer it has to go through multiple activation function at multiple instances. This helps deep neural network to model very complex non-linear decision boundaries for pattern classification tasks. Moreover, such network has the ability to extract features automatically from the given input data. Therefore, raw data can be fed to such network. So, what happens is such a network with multiple neural network can have a very fine level of extraction of features and from the data, and it will get more and more information from the data, so it can be useful for images, audio signals, etc. Such deep neural networks have the ability of representing the input as hierarchy of important features in earlier layers of the network and subsequently using these features in the final layer to make suitable decisions. So such kind of deep neural network represents hierarchy of important features at every level of layers, and this is how it guesses and identifies important information from a network or a input raw data, which can be image, audio, object, and anything. Now we will talk about deep net here, which is conventional machine learning hand engineered feature. Many hidden layers and non-linear activation help DNN learn complex patterns in the data. So as I told you that if you want to make more and more informed decision making, more and more exploration of the data, you can increase the number of hidden layers. We can see a fully connected hidden layer network or deep neural network where each and every neuron is connected with each and every input layer and the consecutive neurons in the upcoming hidden layers. So deep learning refers to the use of very deep, many hidden layers, artificial neural network to solve the complex problems. So deep learning involves using such kind of complex mechanism of neural networks, which can help us to make informed decision, which can help us to build AI applications. Now we will talk about batch normalization. What is batch normalization? So batch normalization is a technique used in deep learning by normalizing the output of each layer to have zero mean and unit variance, reducing the internal covariate shift and improving the performances. What is batch normalization? It is used to kind of scale up the data on a value in order to reduce it to a value where we can have the data with central value as 0, which means if I scale the data, the central value will be considered as 0, which is going to be mean of the data, and unit value as a variance. So batch normalization, it is used to improve the training of the neural network, and as we know, neural network has multiple neurons, it has multiple hidden layers, input layers, so there is a computation challenge all the time. So it is always better to normalize the data and reduce the data complexity. It helps to address the problem of internal covariate shift. Okay, now internal covariate shift is all about getting covariance among the internal input parameters, which refers to the phenomenon where the distribution of the activation of a given layer changes during the training part. And while training the data, it is possible that the internal covariance is always shifting, which usually happens in a machine learning problem. By reducing the amount of covariate shift in the network, batch normalization can lead to faster convergence and better generalization of the performances. So, by using or reducing the covariance shift in the data, it will reduce the uh, problem of covariate shift. Batch normalization is often included as a standard component in modern neural network architecture. So, it is a standard component of modern neural network architecture, and in order to train deep learning network, it is as it is a complicated in nature. The that it has multiple input layers, and it requires training, and at each level of training it may encounter covariances among the data. So batch normalization helps us out. Batch normalization slows down the training by requiring lower learning rates and careful parameter initialization, which makes it notoriously hard to train models with with saturating non-linearities. So when we talk about um, uh, when we talk about uh, uh, when we talk about internal covariate shift, so we require training of data in a way that if there is an internal covariate shift among the data, so at every level what is happening is, if there is a neural network and there is a neuron, and if there are certain parameters which are associated like weights and all, so if this weights keeps on changing due to that internal covariance shift, so the data training of each and every neuron will not be correct, and that is why such kind of problem may occur. Okay, so it will reduce the speed of the execution as well. So the deep learning backpropagation also will gradient descent operation, learning rates, everything will get tempered because of that internal covariance shift. So this problem can be addressed by applying batch normalization method. So batch normalization method normalize the input before feeding to a layer. It draws its strength from making normalization a part of the model architecture and performing the normalization for each training mini batch. It allows the use of much higher learning rates and be less careful about initialization of the weights. And it also acts as a regularizer in some cases, eliminating the need for dropout. So basically it helps us to eliminate the need for dropout because it regularizes certain parameters at certain levels. So batch normalization kind of reduces the dependence of certain parameters as well. Here we have the batch normalization. We can see mini batch normalization where we take the average of the value by taking x of I divided by m, summation of x of I divided by m. Then we have mini batch variance values. So summation of xi minus mean of b, the square divided m, which is similar to our mean squared error kind of function. Then we have normalization by using this z distribution normalization method, but here we are introducing plus epsilon, where xi minus mu b divided by square root of sigma square b plus uh, mu b is there, sigma is basically our standard deviation. Then we have scale and shift method where we can use min max kind of operation where gamma into xi plus beta, which is kind of scaling and shifting the values in order to get this batch normalization. So we have these all levels of batch normalization which can be utilized to normalize the data. And that's that. Hello and welcome to this new module on TensorFlow and Keras. In this, we are going to explore about what is TensorFlow, what is Keras, and how it is helping us to solve complex mathematical formulas and problems. How we are implementing this to build up machine learning and deep learning models, and how it can be helping us to process the data faster and in convenient way. So let's try to understand the TensorFlow. So the objective of this module is to make you understand about different concepts in TensorFlow and Keras. So we will try to understand what is a tensor and what is TensorFlow. We'll understand TensorFlow in real-time applications, advantage of TensorFlow, how to install TensorFlow, TensorFlow 1.x versus TensorFlow 2.x, and the latest version of TensorFlow, eager execution in TensorFlow 2.x. Also, we will try to understand what is Keras, in which we will understand what is a Keras, advantages of using Keras, how to install Keras, why Keras, pre-processing methods, what are layers in Keras, and different models of Keras. At the end, we will also understand what is CNN and CV or computer vision, and also understand what is RNN and natural language processing. So let us begin. TensorFlow. TensorFlow is a combination of two words, that is tensor and flow, which is helping us out to process the data efficiently And when we talk about data, the data can be anything, video, audio, or any information. So let's try to understand TensorFlow in detail. Before that, let us understand what are different level of ways in which you can arrange the data. So the first way in which you can arrange the data is scalar form or unit form. Scalar is a data which has no dimensions, which means it is unidimensional or no dimensional. Scalar is a singular unit of data. Basically, it will have only one value. Okay. Then we have vectors. Vectors are data with n-dimensional information. For example, it will have a series of information, list of names, list of students, list of numbers, and so on. So anything which comes in a form of list is called a vector. When we have data in the form of rows and columns, we call it as a matrix. Matrix is a combination of rows and columns. So we can see when the data in the form of matrix, in the form of table, can be considered as a matrix form of data. Now tensor. Tensor is a data which is usually in 3 dimension or more dimension. So data, when it crosses more than 2 dimension, okay, or it is 3 dimension or more than 3 dimension, we call it as a tensor. We can clearly see from the pictures as well, one-dimensional data or scalar is no dimensional, which means it is a scalar unit or single box. Vector is a list of box or sequence of data or a series of data. Matrix is a tabular representation of data, and tensor is kind of a grid structure with it is kind of a cubical form of representation of data. So tensors are data which are more than 2 dimensions. If you want to represent tensors in a different form, we can represent it like all this data in a different form. Scalar can be represented as a single unit value, that is 1, 2, 22, 23, any value. If you talk it, if it is singular, that is scalar. Vector is represented, as we can see, as a series of values. It has two values in a single series. In matrix, it is not a series, it is a tabular structure with two form of data, that is rows as well as columns. And tensor, as we can see, it is showing data as rows and columns, and within that each column you have multiple values as well, which means it is not 2 dimensional, it is more than 2 dimensional. Now we will understand TensorFlow. So what is TensorFlow? TensorFlow is a free and open source library, software library, which helps us to work on tensors of data. It is usually used in deep learning, and as deep learning is a mechanism where we want to analyze the data or the complex combinations of data, that is why TensorFlow is the best possible solution for it. So in deep learning, we are analyzing complex data which is in the form of image, audio, and it is not necessary that all the time the data which we are getting is always going to be in 2 dimension or matrix form. It can be more than 2 dimension. Images, as we know that images are 3 dimensional. Images are usually rows and columns, and a third dimension basically represents the number of channels, which means red, green, blue combinations of channels. So such kind of data can be easily handled using TensorFlow, and it cannot be handled with anything else. Like only in TensorFlow can help you out to handle such kind of data. TensorFlow was built by Google and released in 2015, and post that we can see there is a constant improvement in the field of deep learning. TensorFlow is to neural network and deep learning what scikit-learn is actually to machine learning. So it is like the heart of deep learning. Without TensorFlow, deep learning is kind of very difficult to handle. Like it cannot be imagined also. The way in which scikit-learn is there to machine learning. TensorFlow is very high demand and one of the most popular choices for deep learning. Like it is the only choice I would say for deep learning. Now, what exactly this TensorFlow is utilizing? TensorFlow utilizes CPU, GPU, and TPU, all three components of a computer. So, it is used for computing. Like TensorFlow involves multiple dimension of data, therefore it requires all three processes by which it can process the data, all three processing units to process the data. Now we'll try to understand the real-time applications of TensorFlow. So TensorFlow in real-time application can be used for speech recognition. Speech basically is a combination of voice, tone, pitch, frequency, and everything. And all these combinations are not just one dimensional; it has multiple layers of combination as well. So it is more than one dimension. And to analyze such kind of data, which is a combination of multiple dimension, we require a complex architecture of database to handle it, which can be done with the help of Tensor or TensorFlow. Speech recognition helps us to identify speech of an individual. Then we have image recognition. Image recognition helps us to like when we are trying to recognize what is there in an image. There also we need to have a complex data and understanding. Data usually in an image is in a form of row and columns, and there is also, if the image is colored, it is always in red, green, and blue. That's why the image is actually split into three dimensions, and that's why it is necessary to analyze such images with the help of TensorFlow. So only TensorFlow can help us out to store and process such information which is in the form of multiple dimensions. Then we have object tagging videos. So there are instances or there are applications where we have videos on which we have to tag. There are videos on which we have to tag people or tag objects. So that also can be done with the help of TensorFlow, because videos are a combination of multiple images together. Then self-driving car. In self-driving car also we require TensorFlow to handle such data. The data which is coming to a self-driving car is not just images, it is also sensor information from IoT devices which are attached to that self-driving car. Then we have sentiment analysis. In sentiment analysis also, TensorFlow can be helpful to process complex sentiments in different forms or different layers. Mobile image and video processing. So when we are processing data using mobiles, there also we can use TensorFlow to process complex images, videos, and audios. When we are developing application for drones, so air drones, land and sea drones, basically they keep on capturing images from the land and surrounding, and these images needs to be identified and analyzed, and this can be done with the help of TensorFlow, as TensorFlow recognizes information in an efficient way. It is also used on on-device computer vision for OCR. OCR basically helps us to reading the documents on a computer images. So if there is a document and if you want to read the information or the text written on the document, we can do it with the help of OCR, computer vision. And when we talk about computer vision, the data which is kept on the computer vision application is also in a form of images, and we need to analyze these complex images. That's why we will require OCR. Smart reply. If you are constructing an chatbot or chatbot kind of application, there also the information which is stored in a chatbot is actually in a form of tensors of data. It is also using massively multitask networks for drug discovery. So if there is a complex architecture where we want to understand drug discovery or medicine analysis, biological mutation, anything like that, where the data is complex in nature, we can use TensorFlow there. Now let's try to understand several advantages of using TensorFlow. TensorFlow is very much efficient as it is flexible. It is flexible enough. It provides multiple models or multiple versions of the same model, and which can be helped which can be worked out simultaneously. So it is flexible across different models and different versions. Portability. You can work on any platform. You can work on any platform and device using TensorFlow, so it is portable enough for working on any devices. Research and production, so it is open for researchers to contribute, like anybody can freely use it. It is open for researchers. Auto differentiation, so it can manage derivatives computing. It can manage derivative computing process automatically, resulting a graph that can be visualized. So it can help us differentiate complex processes and get a graph out of it. Performance, it is helping us to allow to make performance. It allows you to make the most of your available hardware with its advanced support for threads, asynchronous and complex computation. It provides flexibility when it comes to processing the information and distribution of resources across your hardware. So it is that much efficient if you want to develop work on it. So these are certain advantages like flexibility, portability, research and production. It is used in there, auto differentiation and performance analysis. Now we will try to understand how to install it on TensorFlow on your devices. So if you are a Mac user, what we have to do is you have to open your Mac and open your terminal over your Mac, and there you have to type pip install TensorFlow. If you write pip install TensorFlow, it will install the latest version of the TensorFlow. If you do not want the latest version, you can use pip install TensorFlow equal to the name of the version or the number of the version. So with this you can easily install um, with this you can easily install it on terminal or Mac. Similarly, you can do it for Linux. You can write the code on Linux as well. Like you can open your terminal on Linux and you can type sudo apt get TensorFlow, or you can simply use your pip command, because nowadays the pip command is also applicable over Linux or Ubuntu. You can use on Windows as well. In Windows also you can use the command prompt or terminal, and you can simply type out pip install terminal pip install TensorFlow, or you can use your conda prompt, or wherever, if your Python is there, you can there also install uh, pip install Windows, pip install TensorFlow. With this command you can simply install your TensorFlow in your devices. Now we will try to understand the difference between TensorFlow 1.x versus TensorFlow 2.x. So um, initially, when TensorFlow was developed, writing a code in TensorFlow 1 was quite difficult and overwhelming. You need to be very much skilled in coding in order to write it. This gave rise to a high-level packages like PyTorch and Keras. Like, there were other developers who started investigating and working out, like PyTorch and Keras. Keras is an interesting choice here, as in 2017 it was integrated with TensorFlow, and Keras is treated as an interface of TensorFlow. Basically, in order to make it flexible to write code, so Keras was kind of introduced in 2017. And due to the difficulty in writing code in TensorFlow 1.x, TensorFlow started losing out to other popular high-level programming libraries like PyTorch, Keras, and all. To fix this, they have the Google team in 2019 have integrated or introduced TensorFlow 2, and the syntax of TensorFlow 2 is kind of borrowed from Keras, and it is done in a way that it can be said that TensorFlow 2 is actually Keras, and you will interact with TensorFlow in a very efficient way through Keras. So they have integrated Keras along with TensorFlow, and Google acquired it, and it made it more and more flexible and easy to handle. Eager execution. TensorFlow 2 uses something called as eager execution. Now this is a mode of kind of executing code, or DSA or DS algo. Eager execution simply means allowing Pythonic way of coding. This means allowing Python rules rather than using complex computational graphs. So here in eager execution, it is using the programming base Python's base executional method. Eager execution is an imperative, and is an imperative defined by a run interface where operations are executed immediately as they are called from Python. This makes it easier to get started with TensorFlow and can make research and development more intuitive. So it is very much efficient as it uses the Pythonic way of execution of code, and where like operations are executed immediately as we are like implementing in the Python. We do not have separate interface like compiler, interpreter and all. So it is very much easier to implement. Writing a code in TensorFlow is very much easy also. Like suppose you want to create a variable in TensorFlow, you can simply create it by using tf.variables, and you can pass in the value. It will create that variable. Similarly, you can add the variables as well. Like if you want to add the two TensorFlow variable x and y, you can simply use tf.add x comma y. Now see, it is not in usual normal variable that we are talking about. It is a TensorFlow variable, so it will be in a form of tensor. That's why it is better to use TensorFlow libraries to handle it out. You can use the print command to use it, and you can see the shape and size and everything is given over here. Um, Now, if you want to initialize a session variable by process, you can simply use like if you're directly printing add, so it will be difficult. But if you want to initialize, so what you have to do is you have to start the session as s. You have to run the session of TensorFlow s.run by using s.run. In the with command, you can use tf.session, which will activate the session as s, and s.run. In the session, you will be running tf.global variables initializer, and this global variable initializer will initialize the variable, and z will be equal to s.run of z, which will run the value of z. Now the value of z will be assigned with all the value which is there. Directly if we printed, we didn't get anything, but now if you print z, it will just give you the value 8, because it has now implemented and run on the TensorFlow. Initially it was not giving any value because it was considering it as a tensor, but after running tf.global variance initializer, it will create a global variance variables z. So z will now become a global variable and it will be executed. So in TensorFlow eager execution, into TensorFlow 2.1, TensorFlow 2, we saw this the problem, like a simple variable had to be initialized and all these things were done in the previous version. So it was difficult to kind of run all these things in TensorFlow 1. So TensorFlow 2 made it very easy. They skipped the process of creating initialization of global variables. They directly, if you just run tf.add x comma y, and it will simply add the tensor values x comma y, and it will give you a tensor value with 8 and shape as none. So this makes it much more convenient to use and handle the data. Now we can also use TensorFlow 2 for working on data, because TensorFlow is the best way of handling the multidimensional data, and in deep learning neural network we will have multidimensional data all the time. So for that, we first initialize the TensorFlow sequential library from the TensorFlow. Keras sequential is something that will help you to build up a stack of variables or stack of hidden layers on it. So we can add multiple layers, like we can add dense layer, again dense layer, a lot of different dense layer which are hidden layer we can add on our existing sequential layer. We can also add a layer of optimizer and the output layer and compile the output. So basically in deep learning also, TensorFlow is utilized to create variables or create hidden layers. It helps us to create layers and deep learning neural networks. So we have seen what is TensorFlow. TensorFlow is a library or data handling library which will help us to arrange the more than three-dimensional data in an efficient way. In deep learning, we require such complex libraries which can handle the information and help us to process out this information. On the other hand, interacting with such complex libraries becomes difficult, and that is why we require a kind of a top-up of that library which can help us interact with this library as well as data efficiently, and that we can do with the help of Keras. So Keras is something which kind of building up a bridge between the TensorFlow and the raw data. So As I told you, Keras is also an open source library, and it is capable of running on top of both Theano as well as TensorFlow, and it is considered as a heavyweight wrapper for both Theano as well as TensorFlow, and it is easy to use as compared to Theano and TensorFlow directly. When we talk about interacting with these environments or libraries, it is easy to actually work on it. But when we talk about Keras, it is easy. um, Keras actually uses TensorFlow in the backend, and Keras has multiple functionality like building up libraries and all. And Keras is actually integrated with TensorFlow after Google kind of acquired it. Keras runs seamlessly on CPU and GPU. It doesn't require a very higher order of graphical processing or any kind of thing. It helps us to work on both of the environment. It is compatible with all like Python 2.73, all the above versions of Python. By default, Keras will use TensorFlow as its tensor manipulation library, which means the data manipulation libraries. And the advantages are kind of there are a lot of advantages in Keras. When we talk about that, is it is user friendly. Interacting directly with the tensor is very difficult at times, and that's where Keras will come into picture, because see, the data that is coming to us is not always going to be a structured two-dimensional or something data which is kind of very organized. It can be a multi-dimensional data in a form of kind of audio, video, and all different segments of information. uh, that's why it requires like directly interacting with TensorFlow, which is already complex. It becomes difficult. So that's why Keras can definitely help you out to interact with such a data very efficiently and easily. Keras is modular in nature, like it renders standalone models that can be combined to create new models. So it is modular in nature. It is extensible, can extend the model very easily. It is minimalistic, like models are described in Python code, which is compact, easy to debug, and very simple to use. Like it is minimalistic, it doesn't require too much of exaggeration of codes onto it. Now we'll try to understand Keras. The way we have installed TensorFlow, similar way we can install Keras as well, either on your terminal or either it can be your command prompt on Windows. So you can open your terminal and you can simply type out pip install Keras, and it will install the Keras into your environment. Now, why we are using Keras, as we discussed earlier. So, deep learning research and development is carried out with powerful platforms like TensorFlow and Theano. These are tensor manipulation libraries, and that's why it is very important to use it for handling the data. TensorFlow and Theano can be difficult to fit in most of the time. Like most of the people are not that much skilled to handle such data, and that's where it requires a kind of easy build between the programmer as well as the machine. So TensorFlow, interacting with TensorFlow becomes difficult at times, and calculation and computation at the next level is very difficult. So we require an intermediary library like Keras that supports multiple backend engines like TensorFlow, Theano, CNTK. All these libraries, all these backend engines can be easily supported. Like Keras can help you support with all this tensor manipulation and data manipulation libraries. TensorFlow can be trained on a number of different hardware platforms beyond CPUs. Like it is not just CPU on which it is trained, it can be used on other hardware libraries as well. It allows us to perform fast experimentation, like it allows us to perform faster execution of code, and it creates a clean and convenient way to build deep learning neural networks. Like the interface that it provides is much more cleaner, and that is why if someone who is new to the programming environment or the deep learning environment also doesn't feel difficult to work on it. Pre-processing methods. So pre-processing method is a method of standardization to make the data easy in order to perform modeling on the data. Based on the data, we can choose the following pre-processing method. Like first is sequence pre-processing. Second is image pre-processing, and third is text pre-processing. Sequence data usually in the form of RNN, which is sequential like time series data, or maybe it is a form of paragraph or something like that. RNN is the best way which can help us to uh, rearrange the data in a sequential format. Image processing can be done with the help of convolutional neural network, which will help you to work on the data in a very detailed way in a sequential manner or an image data. For text data, we can use the text data like Keras for performing text analytics on TensorFlow and do natural language processing. These are three types of pre-processing which are complex in nature, can be used using TensorFlow and Keras. So it actually enables us to work on these data handling libraries. Now we'll try to understand different pre-processing, as we mentioned, like sequence pre-processing, like time series generator. Here we take in a sequence of data points gathered at equal intervals of time to generate batches of data. Then we can use paired sequences to say to the same length as that of data. Like paired sequences help us to arrange the same sequences as that is there for the data. Skip grams allows us to transform a sequence of word indexes, a list of integers, into tuple of words. Like we can use skip grams. Then we have images. In images, we can use image data generator for augmentation of data and build up different tensor values of data based on augmented values of data. It is real-time data augmentation with different ways of arranging the data in vertical, horizontal, shared version of data. Then we have text in which tokenizer, we can use tokenization, converting the text to a token, and it can be saved as an array or tensor of data. Hashing trick, it converts a text to sequence of indexes in a fixed size hashing process. So text analytics also requires tensors or TensorFlow as a kind of base data handling mechanism. Now, layers in Keras. So, Keras is about like it is used for deep learning. So that is why in deep learning we require different layers of data, and that is where Keras will come into picture. Keras is about deep learning. It is used in Keras is about deep learning. It is used in handling the data, and in deep learning we require sequential architecture where sequentially we are going to place one layer after the other. And ANN becomes a deep neural network when no number of hidden layers are more. Like if you have more than one or two hidden layers, we call it as a deep neural networks. And in order to create this more number of neural networks, we require Keras. Keras has built-in layers that represent common qualities that can be used directly for a deep learning neural network. Layers are chosen based on the data requirements, and Keras helps us to build such layers. And you can you choose your own custom layers based with the help of Keras, and it has all possible sort of data layers that can be used for building deep learning applications. Few of the layers that we can see here is core layers. So basic layer of a neural network, usually the first layer in a deep learning neural network is the core layer or the input layer. Then we can talk about convolutional neural network. So convolutional layers creates a convolutional kernel that is convolving around an image or layer of information or tensor. It can be of the size that we will define, the kernel size we can define as per our choices in the convolutional neural network, and it performs convolving operation over that tensor of data. Pooling layers, it's downsamples the data using pooling technique, which means if we have a dimension n into n dimensional data, we can downsample it to n minus x into n minus x sample of data. So it kind of extracts the meaningful information from the data. Then we have locally connected layers, like convolution layers with unshared weights can be considered as the locally connected layers are also there. Merged layers is a combination of any of the layers in the data. Advanced activation layers, it is used for activation layers for activation function. We have normalization layer to normalize the data passing through this layer. So if we can directly do the batch normalization or data normalization over here. Layer wrappers. So wrapper take another layer and augment it in various ways. It is only an abstract base class which is used. Custom layers like user defined custom layers can be used to provide user defined data. Now we will talk about models in Keras. So different models are there in Keras. There are two ways of composing models in Keras. First is a sequential method by sequential method, and second one is by functional method. In sequential method, you will create a sequential layer first and linearly stack one by one layers on top of it. On functional method, you will create a functional complex network of layers, and directly we will do it with the help of a function. Now we will talk about the sequential model. The core data structure in Keras is deep neural network model, which is the simplest way to stack up the layers one over the other. The simplest way is to stack up the layers, such as a model. Such a model is a sequential model of Keras, and it is simple, easy, and used for linear computation of information, and it does not allow shared layer or multi-input or output. Sequential model is most commonly used model which is there in deep learning because it enables us to stack up multiple neural layers one over the other. Sequential model, first of all, we have to initialize the model. Steps for sequential model. So the first step involves initializing the model, and then step 2 is about adding the layer to the stack. Then in the step 3, we compile that layer and configure the optimizer in step 4, where we will decide which optimizer we are going to use. Then after building that configuration, we will train the model, and once the training is done, we will predict the new data, and at the last step we will evaluate the performance of the model. So this is how a sequential model is built up using Keras. So the code to create a sequential model is starting with creating and importing sequential model. Model is equal to sequential, which is imported from keras.models. Then we will, from keras.layer, we can import multiple layers like dense layer, dropout layer, and all. We can add all these layers, and we can specify number of units, like number of neurons, what is the activation function, what is the input dimension for the input layer. We can add multiple dense layer also, which are acting as a hidden layer. And finally we will add the softmax function. Softmax function will help you to do a multi-class classification over the data. Step 3 is about compiling the data, where we validate that our model is ready, and now we are compiling the data with the help of a certain optimizer. We can specify optimizer like Adam, SGD, mini batch gradient descent, ADA boost, and something like that. And we can keep at accuracy as metrics, so that when we are keeping accuracy as the metrics, so it will keep on improvising the accuracy in the model when it is trying to retrain or do the back propagation. And finally, after compiling, we can simply just specify and configure the optimizer. Like we can specify a particular optimizer also. Like here in SGD, we can configure the learning rate, momentum, and Nesterov function to be true. In the step 5, once the model is ready, we can fit the training data, and we can also specify the epochs. Now, what are epochs? Epochs are number of iteration that we want the model to take on our deep learning data. So there is a data, and what we are going to do is we are going to pass in certain set of sample of data into that model, and model will learn from it. So we will first set up our training data. Model will grab some information, or deep learning model will grab a certain set of information, learn on it, and after learning it will decide, okay, what kind of error it is making, what is the challenges, and in the next epoch it will improvise. So it keeps on doing this epoch by epoch, and in every epoch it tries to improve from the previous epoch. Then we use the class is equal to model.predict. Predict function will help you to predict something new from the data. Like it will help you to predict. You have to just pass in the data. And performance evaluation can be done with the help of model.evaluate. It will tell you like what exactly is this model about, how much weight the model has, and everything. So we can use the performance evaluation of the model. So it will tell you weight, size, and everything about the model, how much weightage it is carrying. Now we'll talk about models with functional API. So the Keras functional API allows defining complex models such as multi-output models, directed acyclic graphs, and models with shared layers. So um, the Keras functional API is basically easy to use and helps us to train the model as layers. It is easy to share the layers between models. A layer instance is callable and it returns a tensor. Input tensor and output tensor are used to define the model, and unlike the sequential model, you must create and define a standalone input layer that specifies the shape of the input data. So we can develop a model with the help of functional API as well. Like it is basically easy to reuse the trained model with the help of layer, and there are a lot of benefits for this input model with the functional API. So it helps us to input tensor and output tensor can be utilized to define a model. Now, model with functional API, how we are going to create. So first we have to create or grab in the input uh, function from the layers part, and we define the input shape is equal to minus 2 comma something, like whatever is the shape of the data, input shape of the data. Then we create the layers. So from keras.layer we call in the layer, and we are calling the dense layer, for example, and in dense 2 we are going to put it as visible. Step 3, we are going to build the model. So in the model we are going to put input is equal to visible. Visible is nothing but the input layer, and output is equal to hidden, that is the number of neurons or number of layers that we are talking about. Then we will compile the model. So for compiling the model, we are going to use the model.compile in the same way that we have done, and we are going to specify the loss as the metrics. Like we don't want the loss to get increased, we want the loss to reduce, so we are specifying the loss. In case of a binary modifier or binary classification, we use binary cross entropy. Loss weight is 1 comma 0.2, which helps us to monitor the weight. And model.fit will help us to fit the training data. So we will first fit the headline data, training and validation data, and the training and validation labels or a wide data. And epochs is equal to 50 and batch size is equal to 32, that we have to specify, which means this model will train on 50 samples of data and every sample will have a size of 32. Now we will talk about computer vision and try to understand the concept behind computer vision. So computer vision is a phenomenon by which we want the computer to understand what is an image and what is happening in that image. Okay, so we want the computer to give a vision as a vision is there for a human body, like a human being is able to recognize what is there in front of it. So we want the computer also to recognize what is there instead of just capturing that image like a mirror. So computer vision is an extension of human vision. Computer vision tries to mimic how human perceive the world through vision. Human vision consists of eyes, which can act as a kind of sensor to see the images and videos, and there is a brain which actually understand what image this person has seen. Similarly, computer vision also has these two parts where eyes are basically replaced by cameras, input images, and different way by which we can perceive an information in an image format. And second, we have a neural network which will identify what is that image. It will try to identify the patterns and trends in that image and identify the objects in the image. So here we have mimicked the way in which human vision is there. In the same way, computer is also giving us the same sort of vision. The scientists and data scientists evolved around finding out a neural network which can help understand an image in detail and understand how we are able to recognize certain things in an image. So that we have done with the help of CNN. CNN basically tells us is a convolutional neural network. When we talk about computer vision, we were talking about convolutional neural networks in short. And convolutional neural network is something where the images um, captured by the devices, or whatever is the image that we are going to we have, the data, image data is kind of recognized by the computer. We make the computer understand what is this image. So CNNs are a class of neural networks which are specially used in field of imaging and computer. CNNs are a class of neural networks which are used in specifically in the field of computer and convolutional imaging, image processing, and they are used in the field of natural language processing and time series, but are almost synonymous with computer vision. So it is also used in natural language processing for analyzing the data. Now, the name convolutional basically comes from the mathematical called as model called as convolution. Convolution is an operation on two function that basically produces a third function expressing how the shape of one is modified by other. So basically it is all about a data. On top of it we apply a convolution operation. It keeps on convolving around that particular model. This function is applied over another function, and that is why it will give rise to a third function. So at a very high and simplistic level of a CNN, if you want to understand, so image, we have an image and there is a label for that image. Okay, and we are going to apply a CNN in between. So this CNN will identify what is that image and give it a label. So a image, suppose here we have an elephant, CNN will identify it and tell it that yeah, it is an elephant. So the architecture of CNN involves four parameters. First is input image, convolutional layer, pooling layer, and flattened layer. Now each of these layers are important when it comes to convolutional neural network, because first input image will give us an input raw array of image with 3 dimensions, that is row, width, and channel. Then we have convolutional layer. Convolutional layer is a layer where we apply convolution operation, mathematical convolution operation over that input array of image, and we apply convolutional operation in a way that it identifies certain set of information based on the convolutional kernel and the size of the rectilinear operator or activation function. Then we have pooling layer, which basically extracts meaningful information over that convolved image or convolved information. And then we have flattened layer, which will be serving as a input layer to our input ANN network. So basically convolutional neural network is a combination of CNN operation of image processing, and finally we have the ANN. So it is a combination of convolutional operation and artificial neural network, and that's how it becomes convolutional neural network. Now we will talk about NLP. NLP is all about natural language processing, where the machine tries to understand what is there in a particular textual information, what this textual information is all about, tries to identify meaning from the text. So this entire operation is natural language processing. We are calling it natural language because normally what we talk in general communication is a natural language, but machine doesn't talk in the same way. Machine works on a very different node, where it works on high level and low level programming languages, which is it actually understand the signal language. It doesn't understand the human language. So to bridge that gap, we require natural language processing, which will make the machine understand what is happening in that conversation, or what kind of conversation is happening, what is there into a text or textual information, what is the meaning of it. So such kind of thing is possible using natural language processing. So natural language processing is a branch of AI and linguistics that deals with interaction between computers and human language. NLP involves the development of algorithms and techniques that enable computers to understand, interpret, and generate human language. There are different types of NLP. First is natural language processing. Then we have deep learning. When we combine natural language processing with deep learning, it is called NLP, or deep neural network, deep natural language processing. And we have a phenomenon called as sequence to sequence in order to arrange the data in a sequential manner, or in order to analyze the associativity of sequential model of a data. So why NLP? So computer doesn't understand the text that we are passing it directly. It is able to understand instruction in the form of logical statements or in the form of Boolean entries. In order to make machine understand, we have to make sure that how the machine will convert the raw information that we are providing into a low level programming language. So deep learning is not directly capable of doing this. Like neural network cannot interpret words. What is word? What is the meaning of this word? For that we require something, and neural network can interpret numbers. So we need to do embedding of information wherein we will make the machine understand about different proponents of this data. The machine will understand what is the numeric computation of a particular word, and it will assign it as a token, or it will create it as a token. We have word vocabulary fixed with us. We know the word English word vocabulary, and this word vocabulary is actually called as corpus of words. In this corpus all the words are there, and there is certain indexing provided to this corpus. We provide, or we do one hot encoding of this indexes, and we will convert this uh, raw information into words, into numbers. We will convert this raw information to numbers. When we do this, we are creating a vector of value, or vector of tokens. So each token is basically represented as a vector, and now we will make sure that the machine is able to understand the token value, which is in a form of a corpus of word, or it is in the form of a vector value. How actually this vector is representing what kind of information. This way machine will understand the associativity between different vectors with certain numerical values, where each vector represents a word or token. Now we will try to understand certain applications of natural language processing. The first one is speech transcription. Speech transcription is a phenomenon where we transcribe the speech. Say if you are attending a meeting, if you don't know, like if you want to make a note of what is happening in the meeting, what are the serious important discussions that is happening. So speech transcription can be helpful there, where we capture all the textual or the words spoken by each and every speaker, and we can see different applications of it in certain like certain softwares like Zoom and all. Then neural machine translation, which is helping us very much in order to translate. Like we have Google there, where we transmit the information, translate the information, like in any languages it is there. You can translate it to English, Hindi, any possible language. Then we have chatbots. Chatbots are very much essential. We sometimes it is not possible to have an interaction directly with the executive for certain help, and that's where the problem begins. It is not possible for keeping a certain person to help on certain things. So chatbots can help there to do simple kind of help, enable in a virtual assistants which can interact with the people. Then Q&A, which are similar to chatbots, which helps to interact and have an interactive one-on-one with the chat or the machine. Text summarization will help you to summarize the text. Say if you don't want to understand what is there in the entire meeting, so text summarizer can tell you, okay, this entire thing was there, being discussed in the meeting, and the summary of this text is so and so. Image captioning. Image captioning is a one where we will be captioning out, or we are going to describe out what is happening in image. So here it is a combination of both natural language processing and image processing, where the natural language machine is trying to understand what is happening in an image. Then video captioning, where we can see different examples over YouTube and other live streamers, where it can video caption, like when we are talking, all the information is getting transcribed as a caption below. So video captioning is also a very important application of NLP. Now we will talk about RNN, or recurrent neural network. RNN or recurrent neural network is a type of artificial neural network that is best suited for recognizing patterns in sequence of data. RNN can be used in textual data, video data, speech, language, genomes, and time series of data. Whenever we see a association of data in a sequential format, recurrent neural network can be the best thing to help you out in in such situations. It can be used for classification algorithm, it can be used for clustering, and it can be used to predict data based on classification or clustering. usually in a time series context. Now let us try to understand the architecture of RNN. Remember, RNN and LSTM and our derivatives, basically LSTM is derived from RNN and are used mainly for sequential processing of data. So here we have a sequential network where we can see multiple layer of networks, multiple neurons. Now these arrow basically means that long-term information has to be sequentially traveled through all cells before getting to the present processing cells. This means it can be easily corrupted by being multiplied many times by smaller numbers less than 0. This is because of vanishing gradient problem. So basically what is the problem over here? So we can see this recurrent neural network. So a recurrent neural network with value, suppose a is the value over there, xt is the input, and this ht is the output. But this output is divided into two parts. One is going to the next neuron, and another set of output which is going to the previous or the next layer which is going to come. So this is how it works. Basically, x0 is the time 0, x1 is the time 1, x2 is the time 2, or say it is row 1, row 2, row 3. Now, information in the row 0 is analyzed and processed, and it has divided in two parts. Like it gives output. First output goes as an output to the individual contributor for the output of that operation or for the data, and the same output is again traveled, or part of it is given to the next neuron as an input. So the next neuron next neuron is what? This is the neuron, or this is the same neuron in the next iteration of information, or basically in the next row. So the same neuron, when it is processing the next row of data or next time sequential data, it was considering the previous information, input of the previous information as well as the current information. This way it will be more robust, and it will be analyzing more of the more information. And that is why it will, whatever output it will generate, it is not just dependent on the current scenario but also on the previous scenario. That is why RNN is a data model, or is a model which can be used for sequential data. So the arrow basically means that long-term information has to sequentially travel through all the cells before getting to the present processing cell. So long-term information has to pass through a long effect. It has a long effect, like it is sequentially getting vanished. Okay, so the output of the first neuron, first row observation, it is not necessary that whatever is the output of this is going to be there in the xth phase. The output of this first layer gets vanished over the time, and it gets corrupt slowly, and the effect of the first output is getting minimized over the last output. And this is what is called vanishing gradient, where the output of the first basically gets corrupted by the output of the last. So there are different types of RNN. Here we can see one-to-one binary classification RNN, where will I pass or not such kind of information. We can use the simple RNN. Then we have many-to-one RNN, where it will take information from many data and it will give output as single data, like textual information. If you want to just summarize whether it is positive, negative, you can use many-to-one transformation. One-to-many transformation, where you have image with you and you want to just summarize what all information is there in that image. So you can use image transformation, or you can use image conversion. Then you have many-to-many machine learning translation. Like for example, you have a text written in a certain language, that is Spanish, and if you want to convert it to English, so Spanish will have multiple inputs, and the output that we are going to get is also multiple outputs. So these are certain types of RNN, like one-to-many, many-to-many, many-to-one, and many-to-many. So this is all about RNN. RNN has a problem of vanishing gradient descent, and vanishing gradient is a phenomenon where the model actually forgets the information from the very past. It just remember what has happened in the recent scenarios. So this is what is the drawback of RNN. That's why it vanishes. The information gets vanished in the RNN. So now in this module, we are going to understand what is optimization techniques in a deep learning model. and how we can work on loss functions. So optimization is a very important task in deep learning because deep learning model always learns from the surrounding or the data which is provided to it, and it improvises over the time. So the mechanism of improvisation over the time is important, otherwise it will not converge to the minimum loss, is to converge towards a minimum loss. So let's try to understand what is optimization. So in this session we are going to understand about optimization algorithms like gradient descent, batch gradient descent, stochastic gradient descent, and Adam optimizer. Then we will also learn about loss function, that is mean squared error, binary cross entropy, sparse categorical cross entropy, and sparse categorical cross entropy. Let's try to dive deeper into all these topics in detail. So optimization algorithm are, as I told you, like when we are working on a machine learning algorithm, it starts from taking data from the input layer and processing this data, uh, analyzing information or the complex trends and pattern through different level of hidden layers. Multiple neurons are there. It moves forward, the information move forwards, a output is generated. Now this output is mapped with the actual output, and it is observed that there is some kind of discrepancy, some differences there. This discrepancy is error, so we need to improvise this error. So how to improvise this error in an efficient and faster way so as to get the model effectively predicting the future unseen data. So for that we require optimization algorithm, and we have different optimization algorithms starting with uh, gradient descent, mini batch gradient descent, and so on. Optimization algorithms are kind of crucial component in the training of deep learning model. As I told you, their primary goal is to minimize the loss function or error, thereby increasing the efficiency of the model and reducing the weights and adjusting the weights and biases of the neural network. Optimization algorithm is responsible finding out the set of weights and biases that result in the lowest possible error. Without an effective optimization algorithm, it is difficult to find an nearly like it is impossible to find a nearly equivalent model which can identify trends and the patterns in the data well. Optimization algorithms are important for several reasons. Firstly, they will help the neural network to converge to the set of weights it is finding out, and it also helps us to converge in a reasonable time also. Secondly, they can avoid issues such as overfitting, underfitting, because at the time of training itself, it adjusted the data in order to avoid overfitting of the data with each and every epoch. Overall, optimizations are critical components of deep learning, and choosing the right method will be the best possible way. And it is also crucial to understand which would be the best way of optimizing the current learning algorithm. So we'll try to first understand the gradient descent approach. Generally, if we want to find the minimum of a function, we go by the gradient descent approach. We set the derivative to 0 and solve for the parameters. It turns out that it is impossible to obtain a closed form solution for weight and biases. Instead, we iteratively search for a minimum using a method called as gradient descent. As an analogy, we have to imagine, like we imagine yourself standing on a mountain peak and you're trying to get to the bottom of your peak. So at every step you walk into the direction of the steeper descent, since the direction is the most promising to head to lead you towards the bottom in minimum time. So gradient descent is all about finding that direction in which we have to move forward. Gradient descent also operates in the similar way. When trying to find the minimum of a function, we it starts at a random location in parameter space and then iteratively reduces the value of j until it reaches to a local minima value. At each step of the iteration, it tries to minimize or reduce or it moves or it searches for a steepest descent where we can go across and find out the uh, the minimum error or loss function. This process is depicted for the one-dimensional case in the image. Now, the direction of the steepest ascent of a function at a certain point is given by the gradient at that particular point. Therefore, the direction of a steepest descent is given by the negative of the gradient. So, now if we have a rough idea how to minimize the j, so j is the cost function, and as we are moving towards the downward direction, we are looking for a negative gradient. Here we start with the random values for weights W and biases W and B. We compute the gradients of J with respect to W and B. Take a small step along the direction of negative gradient, and we keep on doing this again and again until we converge to a local minima. So this is the entire process of gradient descent. Now there are certain versions of gradient descent. For example, we have batch gradient descent. So the pros of gradient estimates are stable, and concept needs to compute gradients over the entire training for one update. So infeasible for a very large data set and for a large neural network where there are millions of parameters to be updated. So if you are talking about batch gradient descent, it requires to analyze the data at a batch level. So initial parameter is theta, and while stopping criteria is not meeting, we will compute the gradient over n samples, and we apply the weight, and we keep on updating the weights, until we reach at a lower value of the gradient. Now batch gradient descent, we can see here with the help of a contour plot where how several step of gradient descent brings the error closer to the global minimum. We see a small step of the error gradient. Gradient descent is also known as batch gradient descent, as one of the gradient computation step requires the entire batch of the training observations going through the gradient computation process. So batch gradient descent is all about changing the weights after a certain batch is over. So we divide the data into a certain set of batches, and after all the data is getting trained, we optimize the weights. So weights are changing after the optimization and learning of all the data points. Now, on the contrary, we have stochastic gradient descent. So it is faster in convergence because it improvises at every iteration. So it keeps on iterating over each and every iteration. It keeps on improvising with each iteration. Imagine that you are trying to learn a new skill, and say if you are trying to solve 10 mathematic problems, and the teacher actually helps you out when you are completing 10 problems. So imagine you have given 10 questions to solve, and your trainer, basically your teacher or trainer or tutor, helps you out after you complete 10 questions. So batch gradient descent is all about that. So basically where we have the output or the feedback or the improvisation is done at the end of 10 or set of batch is over. When we talk about another gradient descent, where we get the improvisation at each and every problem being solved. For example, if you have 10 questions, in the previous case, when all the 10 questions were solved by you, you got the feedback. But if you get the feedback at every problem, like if you solve one problem and you get a feedback like whether you are correct or going in the wrong direction, in the second problem again you get the feedback. So this way your learning and improvisation is happening at each and every step instead of completing a certain set of batches. So this basically is a phenomenon of stochastic gradient descent, where your learning will happen at each and every step, and it keeps on improvisation. So that is why the learning basically becomes faster. So basically for you to solve 10 questions and then get a feedback, where your learning will be slow, because after a certain set of time you will get a feedback, your learning will not happen at that time. But when you are getting your learning immediately after you are solving a single problem, there your learning is fast. So a stochastic gradient descent is all about getting a learning fast, where a very faster learning. And you can see the iteration over here, stochastic gradient descent. The advantages of stochastic gradient descent is computation time per update does not depend on total number of training examples. Here various in the case of batch or gradient descent, where you have to do all the training and then you get the update. No, here that is not the case. So you will get an update at a very fast pace. Instead, a parameter update is done at end of every gradient descent step on a single observation. That is the best part, and it has faster convergence than any other gradient descent, and it is suitable for very large network with millions of trainable parameters. Now, potential problems. So gradient estimates that can be very noisy, as shown in the red lines. Blue is the reference lines for batch gradient descent, but when it comes to stochastic gradient descent, it is very much noisy. It can be it can change at every instance of time. So that is why it becomes difficult to like error never get to the global minimum, but oscillates around the global minimum. So it keeps on oscillating around the global minimum, but it doesn't reach the global minimum at all. Now, feature importance and error surface. Now, till now we assign the same learning rate to all the features. If the feature vary in importance and frequency, then it is probably not a good idea to implement this gradient descent. Like, we need to make the learning rate adaptive in nature. So we require adaptive learning rate methods. So all the features are equally important, but there are certain cases where some important features are more important than any other feature. So in such instances, we can use adaptive learning methods where it can improvise the gradient descent or the gradient value. So that is where ADA-grade takes into picture. ADA-grade basically is a method where we downscale a model parameter by square root of sum of square of all its historical values, and we keep on minimizing these values, sum of squared errors. Parameters that have large partial derivatives of the loss learning rates for them are rapidly declined. So in adaptive gradient, we rapidly decline the adaptive learning rates. ADA grade is good when the objective is convex in nature. If we are moving towards a convex end at the bottom, ADA grade might shrink the learning rate too aggressively. We want to keep the history in mind, so it can shrink the learning rate too aggressively. We can adapt it to perform better in non-convex settings by accumulating an exponentially decaying average of the gradient. So we can do the change in the mathematics of exponential gradient, and ADA grade can help you out to do that. And here we can see the example as well. So while stopping criteria is not meeting, it will compute the gradient estimate function, and then it will accumulate the value of R, that is regression value of R, which is which is the initialization parameter, and it keeps on adding. We will compute the and update the value of delta theta and apply update again and again. So what we are doing is we are changing the learning rates and the weights accordingly at each every iteration, but the weights are getting optimized at every step for each and every parameters. So the features are getting different learning rate. Then we have RMS prop. RMS prop is a gradient descent optimization algorithm commonly used in deep learning. It adapts the learning rate based on the magnitude of the gradient, which allows for faster convergence and better optimization of data. So RMS prop computes a moving average of the gradient values which are there, squared gradients for each weights, which is then used to adjust the learning rate of for each weight. So basically here learning rate for each weight is adjusted based on the moving average of the recent grade or the weights. So the algorithm uses a decay rate hyperparameter to control the influence of previous gradients on the current learning rates. RMS prop is basically less sensitive to the choice of hyperparameters like than the other optimization algorithms, making it a popular choice for many deep learning models. Despite its benefit, RMS prop may still suffer from local minima and can be slow to converge in some cases. So it is very much useful RMS prop because RMS prop helps in optimizing the weight, and it uses the moving average method to kind of optimize the weights of a data. It is also less sensitive to choices of hyperparameter than other optimization algorithm, because that is why it has become a popular choice in the deep learning environment. In some cases, RMS prop also may converge to a local minima instead of global minima, so that can be a problem at times in RMS prop. Then we have ADAM optimizer, which is the most commonly used optimizer. So it is a popular optimization algorithm used in deep learning, and it combines the benefit of both RMS prop as well as momentum optimization. ADAM optimization computes the adaptive learning rate for each weights and based on the estimates of the first and the second moments of the gradient. The first moment represents the mean of the gradients, while the second moment represents the variance of the gradients. Now, ADAM uses bias correlation terms to prevent the estimates from being biased towards zero at the beginning of the training. So it uses a bias correction tool to avoid the biasness of the data at the beginning of the training itself. The algorithm also uses hyperparameters to control the decay rates of the moment estimates and the learning rate. So Adam optimization uses hyperparameters so as to reduce the effect of decay rates of moment estimates and the learning rate of the data. Now we will talk about the loss functions. Loss functions is a function that compares the target and predicted output values. It measures how well the neural network model the training data. When training, we aim to minimize the loss between the predicted and targeted outputs. In supervised learning, there are two main types of loss functions. First is given an input value, the model predicts a corresponding output value, and there is the square of differences, mean absolute error, these kind of loss error. Given an input, the neural network produces a vector of probabilities of the input belonging to the various preset categories. Then select the category with the highest probability of values, for example, in binary cross entropy, categorical cross entropy, or be it sparse categorical cross entropy. Here, we are not predicting a category, but we are giving out a probability of being into a particular category. So these are the two possible ways of loss function. So the first one basically happens in the regression, and the second one basically happens in the classification loss function. So the hyperparameters are adjusted to minimize the average loss. We find the weights WT and biases based on the minimization of the value J, which is the cost function. So in order to do that, we basically do the partial derivative of the loss function with respect to the weight that we want to optimize, and then we subtract that weight value or the loss function value from the existing weight. So the first loss function we are going to talk about is mean squared error. Mean squared error loss function is commonly used in the measure of error in regression problems in deep learning. If we are performing a regression problem, it measures the average square differences between the actual values and the predicted values, and the mean squared error is calculated as the sum of square differences between the actual and predicted value divided by the total number of samples. The mean squared error penalizes larger errors more strongly than smaller error due to squaring operation, and mean square error is differentiable and convex, which make it a popular choice for optimization algorithms. Mean square error is also sensitive to outliers and can be influenced very strongly due to the presence of outliers. And alternative to the mean square error, we can have mean absolute error, root mean square error, or Hubbard loss for optimizing the error. Then we have binary cross entropy. Binary cross entropy loss function is commonly used in binary classification of data, usually in logarithmic or binary classes. It measures the difference between the predicted probabilities and the ground truth of binary classification problem. It is calculated as negative logarithm of the likelihood of the predicted probabilities given the two labels. So it is negative log likelihood of the predicted probabilities in the truth table. The BCE basically loss function penalizes more strongly the prediction that are farther away from the true labels. BCE is commonly used in neural networks with sigmoid activation function in the output layer, and binary cross entropy is differentiable, which makes it a popular choice for optimization algorithm. Binary cross entropy is sensitive to class imbalance, which means if there is an imbalance in the class, there is a certain category which is higher compared to the any other category, binary cross entropy will not work out well. Alternative to binary cross entropy, we have other cross entropies such as categorical cross entropy or multi-class classification of the problems. Here we have an equation like 1 by n summation minus 1 by n summation of yi log of py plus 1 minus yi log of 1 minus py. So basically is this is negative log likelihood value for probabilistic data, where suppose y is the label, 1 basically stands for green points and 0 for red points, and py is the relative probability of the point being green and for all n points. Now we will talk about categorical cross entropy. So categorical cross entropy is another set of cross entropy method where we find out multi-class classification problems in deep learning. It measures the difference between the predicted probabilities and the actual probabilities using the true one hot encoded labels of the multi-class classification problem. The categorical cross entropy is calculated as a negative sum of products for the true one hot encoded labels and the logarithmic value of the predicted probabilities of that product. So the CCE loss basically penalizes more strongly the predictions that are farther away from the true label. So basically it looks after the losses which are very much farther from the actual prediction lines. Categorical cross entropy is commonly used in neural networks with softmax activation function in the output layer, and categorical cross entropy is differentiable, which makes it a popular choice for optimization algorithms, and it is sensitive to class imbalance and may lead to be weighted to account for unequal class distributions. If there is an unequal class distribution, it is always necessary to make sure that we have a class balance before. It is given as minus 1 by n 1 by n summation of y log p, where y summation of y log p, where it will consider all the y values and the log p values across. Binary cross entropy is a special case of categorical cross entropy, where m is equal to 2 and the number of categories is also 2. Then we also have sparse categorical cross entropy. So sparse categorical cross entropy is commonly used in multi-class classification problems where true labels are integers rather than one hot encoded vectors. It measures the difference between the predicted probabilities and the actual true integer labels of a multi-class classification problem. The sparse categorical cross entropy is calculated as the negative algorithm or logarithm of the predicted probability of the true integer label. The loss function, this loss function basically penalizes more strongly the predictions that are farther away from the true labels compared to the one which are closer, and it focuses commonly on computationally. It is commonly used in neural network with softmax activation function in the output layer. Sparse categorical cross entropy can be more computationally efficient than categorical cross entropy, since it avoids the need to convert to integer labels to one hot encoded vectors, and it is given as minus of I is equal to 1 to n and t log p for n classes, where t is the truth label and pi is the softmax probability for that particular class. So in summary, we have in regression we have linear as an activation function, which is mean squared error. We also have mean absolute error. In classification, if it is binary outcome, we have sigmoid as an activation function with binary cross entropy as a loss function. Classification, if it is single label multiple classes, we have softmax activation function with cross entropy as the loss function. And if it is classification, then we have sigmoid activation function with binary cross entropy as the loss function. So this is how the entire summary of the categorical cross entropy and the loss function is all about. So we have seen the concepts behind the deep learning algorithms, what are neural networks, how those works, what is the calculations behind it. Now we will try to work on implementation of this neural networks using Python. So before starting with any neural network, let us first try to understand what is that neural network. So we are going to talk about artificial neural network today, and we are going to implement a simple regression problem trying to predict any regression value over here. So let us first start with understanding or a kind of recall over that artificial neural network architecture, and then we will start with the coding part over a data set. So as we can see on the screen, we have a artificial neural network in front of us. This artificial neural network comprises of input layer, hidden layer and output layer. Now let us talk about each of this layer in detail, and then we will get started with our model building or deep learning neural network building. So the first layer, that is input layer, this layer talks about adding. So we are talking about the input layer. Input layer is a layer which takes input from the data, which means it is connected to an input source of data. Input layer will process the information or take the input, and that information is passed on to the next layer, which is hidden layer. Now hidden layer comprises of multiple neurons. Each neuron is capable of doing mathematical computation over the input data. So each neuron will take input from different sources, like this is first input x1, say, this is x2, this is x3, and this is x4. Now the input layer over here will take input from all the four layers and or all the four input parameters, that is x1, x2, x3 and x4, and it will do some processing. Here it will happen, like some kind of processing will happen with respect to a function. It can be any activation function, that is usually we are using ReLU activation function in this hidden layers. So it will work as a ReLU activation function over here, and this ReLU activation function will process that information and develop an output which will go to the next hidden layer. Okay, so each hidden layer will have the same, each neuron in that hidden layer will have the same functionality that is having for a single neuron, but the way in which it processes the information will be different. For example, input layer, the first neuron N1, let's talk about the N1 neuron, let's call this as N2. Each neuron N1, N2, N3 and so on, each neuron will do the same activity, like it will take input from the input layer and process that information and give an output. So if we are doing the same activity, why do we need multiple neurons? So the reason for having multiple neurons over here is, the first neuron, when it does the processing of input data, it considers different weights for different input levels. For example, here we will have the weightage for N1 for the first variable, that is x1, x2, x3, x4. So as we can see, whenever this activation function, whenever this neuron is trying to process this information, it will also process with respect to some weight w. So how exactly this processing is happening? It is happening with respect to a activation function which is applied over the neuron. For example, here we have x1, x2, x3, x4 as the input. So the neuron N1 will apply activation function f over the input data x1, x2, x3, x4 governed by a weight w1, x1. So it is a product of weight as well as the input data. Here we have w2, x2 and so on, like all the weights, product of weights and variables. So what is happening in a single neuron? We are multiplying a certain weight which is associated with x1, x2, x3, x4 respectively. These weights are initially assigned randomly in a neural network, and that's why the first neuron will have certain weights for different parameters. The second neuron will have some other set of weights. So the weights for first neuron, say it was w1, w2, w3, weights for second neuron may be w1 dash, w2 dash, w3 dash and w4 dash. It will be different. The weights processed by N1 neuron, the weights which are used by N1 neuron is not going to be used by N2. The weights will be different in N1 and N2. So that is why we can see different level of processing happening in each neuron, which means even if the neuron, each neuron is taking some input x1, x2, x3, x4 and processing it with the help of same activation function, but the weights are different in each neuron, which means the processing is different in each neuron. I'll give you a practical example. For example, we are developing a neural network for predicting whether a particular animal is a cat or a dog or something. So x1, x2, x3 and x4 are four different parameters. Say x1 is the shape of that animal, x2 is number of eyes, x3 number of tails, and x4 the size of that animal. So now if we talk about this all four parameters, we can see that x1 which basically is the shape of that animal is relevant to identify whether it is a dog or cat. x2 x3 basically tells us number of eyes and number of tails. So dogs and cats have same number of eyes and same number of tails. So we do not need these two parameters, which means our neuron, whichever neuron we are talking about, it should process, like say first neuron is giving more importance for x1, x2 and x3, but ideally x2 x3 are not so important, x4 and x1 are important. So each neuron will analyze the data with respect to weights which are associated, and a particular neuron which correctly identifies the differences between whether a particular animal is a cat or dog, that particular neuron will have higher weightages with respect to the input data, that is x1, x2, x3, x4. So say n4 is the neuron which correctly diagnoses whether a particular animal is going to be a cat or dog, because n4 ideally gives higher weightage to the shape of the animal and the size of the animal, because shape and size will basically tell us like, yeah, particular animal is going to be dog or cat, but the number of eyes and number of tails are going to be same for both the animals. So it is not going to help us out much in diagnosing whether it is a cat or dog. So ideally, considering this situation, each neuron judges based on different weights which is assigned. So n4 has higher, say n4 is giving correct diagnosis, which means n4 is having higher weightage to the x4 parameter and x1 parameter. It is giving the least weightage to x2 and x3, and that is why we are correctly getting n4 the output from the n4. And similarly it goes, the output of n4 is kind of passed on to the next neuron layer or the next hidden layer. Now let's talk about what is happening in the next hidden layer, h2. So say this is our hidden layer h1 and this is my hidden layer h2. H2 is doing what? H2 kind of summarizes the processing output of the first hidden layer. So whatever is the output of the first hidden layer neuron, that output is passed on to the next hidden layer neuron. So this is kind of an neural mechanism which we have in human body. We are having the similar kind of mechanism over here. Why? Because we are trying to distinguish between a particular animal being cat or dog based on certain parameters, and maybe the first layer of the output of the first hidden layer, we want to strengthen that output further. We want to dive deeper into the outputs of each of the neuron. That is why a second neuron will help us do that. What this neuron will do is it will take information from the first 2 3 kind of neurons, and like all the neurons, and it will do some processing. Now this is our hidden state 2, so I'll call it as n1 dash n1 dash, and it will do the same for processing as we are doing in a single neuron. So whatever processing is happening in this neural network 1 or neuron 1, the similar kind of processing may be happening in the second neuron which is there in the hidden state 2. And similarly all the neurons, and it also works in the same way. It initially has the same some random neurons or random weightages, and according to the outputs that it is receiving, it will generate the output for the next layer. And whatever is the output for each neuron in this hidden layer 2, it is kind of helping us to give us some kind of output in the output layer. So now let us talk about output layer. Output layer is the layer where we get the output. Here we will basically get the probability of a particular animal being in a particular category. For example, this first part is the probability of being a cat, second part is probability of being a dog, third probability of being a sparrow, or probability of being an elephant or something. So any kind of whichever, like after doing all the processing, whichever category, whichever output layer has the highest probability, that is considered as our neuron, or that is considered as our output. So this is basically happening for classification. If we have classification, we will have 4 classes, but if in case we have regression, we will have only one output element, which means here we will not have 4, we will have only one, which means all the hidden layer 2 output is going to give us a number over here, and that number will be similar to the output of that input data. So this is how the architecture of ANN is. In ANN, we take input in the input layer, we process the information in the hidden layers, and we get the output in the output layers. While we are doing regression, in regression regression we will have only one neuron over here, not 2. If we are doing classification, we have more than one neurons in the output layer. Now let us start with our program. So we have seen what is the architecture of this ANN, artificial neural network. It is a simple architecture: input layer, hidden layer, output layer. In hidden layer we have neurons. Neurons will do the processing, and then we will get the output. Now we will talk about the data, and we will import the data. First we will import the library, that is pandas as PD. We will then import numpys as np, and we will import matplotlib.pyplot as plt. Now let's talk about what are these libraries. Pandas help us to get the data from an external resource. We can do some level of analysis, some level of data cleaning using pandas. NumPy is used to store the data in a form of NumPy array. Why we are using NumPy array? Because if we have a vector of data, so NumPy array is the best possible way to store it, because it does faster retrieval of information, faster processing of information, calculations are faster compared to traditional way of storing the data. And then we are also using matplotlib.pyplot as PLT. So pyplot is a sub library within matplotlib, which is helping us to create charts, graphs with respect to the data. Now we will import the data. So we have a data over here. We are reading this data. The data is stored in my current working directory. So my current directory is downloads folder, and that is where my data is also placed. So this is our data.csv, and we will read the data df by using pd.read_csv. Read_csv is a function in pandas to read the data, which is in CSV format. Then once we have a look at the data, we can see we have age column, we have education level, we have occupation, number of dependents, location, work experience, marital status, employment status, household size, ownership status. Then we have type of housing, we have gender, primary mode of transportation, and then we have income. Okay, so we have all these columns with us in our data. Now we will try to understand the data in a much better way. So we are going to do a regression problem. So practically we are not going by a logical approach here. We are just going to use this all input variables and develop an output, regression output as a numerical output. Okay, so right now we do not have to go with the logical sense of this problem statement. We will go directly with the implementation part, how we can implement a regression operation using artificial neural network. Then here we have df.info, which will basically give us information of each and every column in our data. So we have age, and age column has 10,000 observations which are non-null, and it is of integer type. Similarly, education level, which is again object data type, occupation, which is again object data type, number of dependents, it is an integer data type, location will have object data type, work experience will have integer, marital status object, employment status object, household size it is integer 64, home ownership status it is object data type, type of housing is again object, gender is an object, and primary mode of transportation is again object, and income is also integer data type. Now what is this data all about? This data is telling us that whether the type of information inside that column is integer type, it is numeric, or object type, whether it is an alphabetical string value. So if it is an alphabetical string value, it is telling us that it is an object data type. So we can also see the size of the data type data here, which is 1.1 plus MB, and we do not see any missing values here in our data. So let us move to the processing of this data. So initially we need to do a little bit of processing of this data. So for that we will separate our data into two parts, that is categorical columns and numerical columns. For that we will create two lists. One list is cat and another list is num, and I am doing this without having a logical flow. As I told you, we are here to learn how to implement a regression over a certain data set, whether it is a regression or classification, whatever is the data set, how to utilize it for ANN, like how we can implement an artificial neural network over an data set. So that is the purpose. So right now we are not going with a very logical data cleaning approach, but yeah, to some extent we will try to do justice to this data set and try to retrieve practical possible information. So categorical is a list and num is a list, and what we are doing is we are iterating over each and every columns in this data set. Okay, so df is our data set. So for I in df dot columns, which means I basically represents each and every column, and we are checking if the type of the column is O. O basically tells us object data type. So if the type of the column is O, it will be added to the categorical list. Otherwise it will be added to the numerical list. Right now we have only two type of data, that is integer and object. So we will use this if else condition. If in case we have float 64 or something else, so in that case we, or date and time, so in that case we can have multiple if and else kind of operations over here. So this loop, this code will basically separate columns into two parts. Like it will just give me a list of separate columns. First list is cat, in which we will have only the categorical information. Second list is num, in which we will have only the numerical information. Then we will move on to creating charts using this data. So we will create different types of charts. So if we are having a categorical information, so what kind of charts we can do? We can ideally develop a bar horizontal bar chart. So we are iterating over each and every column in cat. Okay, and what we are doing is we are creating value counts for each and every column. So for I in cat basically represents each and every categorical column. df of I means df and that categorical column. That categorical column we will calculate the value counts, which will tell me how many what is the count of each category in that column, and we are developing bar h. So bar h is going to help us to develop a horizontal bar chart, and horizontal bar chart on y-axis we will have indexes, which is nothing but names of the categories, and on x-axis we will have the width as the values of the value count, which means y-axis we will have indexes or the name of the category, and on width of that each bar will be decided based on what is the proportion or what is the size of that, what is the count of that value or the category. And we will also use plt.title to show the title, and then plt.show to end the visual, each visual. So here we can see different columns. So first categorical column we can see, that is education level. In this education level column we can have different education levels, that is doctorate, masters, high school, bachelors, and kind of this data is arranged. We have higher number of bachelors in our data. Then we can see occupation. In occupation we have different occupation categories, kind of balanced. Then we have location. We can see that most of the people are from the urban background, very few are from rural and then suburban. Then marital status, We can see marital status also, most of the people are married than single. Then we have employment status. We can see full-time, part-time, self-employed. We are trying to visualize each and every categorical column, trying to understand which column has what is the distribution of each category in those columns, and we can clearly see each and every data is quite distributed. We do not see a perfect imbalance in the data as of now. So that is our categorical data we have visualized. Now we will move on to the visualization of our numerical column. So we have also we can also develop the charts for numerical data like this. So for I in num, we will apply a for loop on the numerical data and extract each and every numerical column. And we are going to develop two charts for numerical data. That is, ideally we have a box plot and second one is histogram. So first chart will be an histogram, second one will be a box plot. We can interchange the positions. We are using subplots approach of PLT or matplotlib. In matplotlib subplots, we divide the data into two categories. Like here we have 1 and 2. So what this basically tells us, so in each subplot I want two charts, which means one row will have two charts. That's what this 1 and 2 basically indicates. This is the size of each chart, and on the first AX0, so this is my AX0, on this I want histogram, and this is my AX1 on which I will be creating a box plot. And plt.super title, this is a super title which will be imposed over each of the two charts. Like this is a combination of two charts, so super title is a super title of these two charts, which is nothing but the name of that column, and plt.show will show that visual, which means if I'm running a for loop, I do not have to, like, it will not overlap over each other. So that is why plt.show will help us. So let's see what are the charts that we have developed using this for loop. So the first column, that is age, and we can see a distribution of age which starts from somewhere close to 18 to 20, and the age distribution is still 70. There are higher people between the young age group and the old age group, and it is quite symmetric distribution, as we can see over this box plot as well. So no outliers present. Then we will move on to this number of dependents column. So number of dependents column also shows a significant level of data distribution on the histogram as well as this box plot, and it is also quite symmetric in nature. Similarly, work experience data is also symmetric in nature. Household size is also symmetric in nature. These are categorical kind of information, and doesn't represent a continuous flow of data. That's why it will always be continuous, or it will always be symmetric. Here we have a column that is income, which is not at all correctly showing the symmetry, or this data is right skewed, because we can see there are a lot of outliers here. Outliers basically indicates there are people who are earning more here, and very less proportion of data is there, which is outlier, and there is a presence of outlier. So let us try to analyze the data. So we have seen the data, kind of understood where the problem lies, and now we will start with understanding the data correctly. So we have these all columns, we'll keep it open, and we will start with analyzing the data. We will use the label encoder and one-hot encoder to properly encode all the categorical data. So we'll start with education level first, and we are doing encoding. We are not using label encoder or one-hot encoder directly. We are using dot to replace as an alternative to one label encoder. And wherever we see high school, bachelor's, master's, doctorate, we are giving manually our own hierarchical data setup. That is, high school is 0, 1 is bachelor's, 2 is master's, and doctorate is 3. And we are using replace function in the education on the education level. So we are replacing so in the education level, wherever we see high school, bachelor's, master's, doctorate, we will replace it by numbers. Now, why we are converting data into numbers? Because the machine learning algorithm or deep learning algorithm will not understand what is high school, what is bachelor's, what is master's. So we have to encode it into a proper number so as to make the machine understand, yeah, this particular number represents this particular information. So we can do the de-encoding part or decoding part later on, but this is how we are going to create the data or encode the data. Then we'll do it for education level. We see the data. Now we'll do it for occupation, and occupation is also quite balanced, and we are using one hot encoder here. The reason of using one hot encoding is, so what is a one hot encoding? One hot encoding will first of all convert the data. So say I have only three categories: A, B, A and C. In my data I have only these all data, which means there are uniquely three categories. So when I do one hot encoding, it will convert the data into columns. This one column will be converted into three columns because I have three unique information, A, B and C, and wherever I see A, it will put 1, and rest of the value it will put 0. So wherever I see B, it will convert it as 1 and rest of the 0. Similarly here, and when I say C, it will put 1 here and it will put rest of the data as 0. So what is one hot encoding? One hot encoding will convert the data into a numerical version. It will convert the data into a version where the categorical data is converted into numerical, and each category will now be becoming a new column. And when we are doing one hot encoding, we convert the data accordingly. So for that we use this one hot encoder function, and we are keeping sparse output as false because we do not want a sparse matrix to be created for each column or each level of data. Then we have we are creating one hot encoding array. We want that array because when we apply this one hot encoder over column, it will create an array. So we are creating a one hot encoder of occupation column. We will use fit transform over it, and once we do the fit transform, we apply it over occupation column. Make sure that we are using double square brackets. Double square brackets basically helps us understand that this is a data frame that we are trying to encode. And then once we do it, we get an array which is one hot encoded, and of that array I will create a data frame. So I will create a data frame called occube using pd.data frame, and the input data will be occuped array, and columns we are using OHE computation dot occupation dot categories, which means this one hot encoder which we are using, from there we are getting the column names. Now what is this column names? These column names are nothing but A, B and C for our, if the data has A, B, C as categories, these categories will uniquely become as the columns for that array. So the array, say if array has A as the first column, B as the second column, C as the third column, numerically presented, so is going to be represented by OHE occupation dot category. So it will sequentially give us according to the generation of the array. The column names we will get A, B, C accordingly. So whatever is the occupation, say healthcare become first column, technology will become second, finance, others and education. Once we do an one hot encoding operation, what we will do is we will treat the data, or we will script the first column, which means we are removing the healthcare column and we are keeping rest other column. We are not, like when we create this data frame, occube data frame will have multiple data. So I'll show you what is this occube right now. So this occube column or data frame, okay, I need to run it all. So occupe column is having education, finance, healthcare, others and technology, all these columns. And what we have done, we have healthcare, technology, finance, others and education. These are how many columns? 1, 2, 3, 4, 5. And here also we have 5 columns. Now once we apply, see, when we are using these columns, it will show us perfect correlation among itself, which means that if education is 1, rest other is going to be 0. Similarly, if tech finance is 1, rest other is going to be 0. So here we see that if we know that which one is 1, then we are able to easily able to understand or recognize others are going to be 0, which means these are interdependent or correlated. If we know any one column, if it is 1, rest other columns are automatically understood that it is 0. So this shows a clear correlation among itself. So that is why what we will do, we will try to remove this collinearity or correlation among this data or multicollinearity. This is a multicollinearity problem where the data is actually connected or the data is actually connected or actually correlated with each other. So we need to remove this collinearity because that will not help us in the that will not help us in model building, because the primary assumption of building a model or machine learning or data science or any model tells us that the data should not be correlated among itself. So that is why we need to remove one column, and that is why we are using this ilog method. Ilog method will remove one column, and say we are removing first column. We can remove any column, so but we are here removing only the first column. So we remove the first column using ilog, and that's how we do it for others. So we will check which all categorical columns are there. Education level is done, then we will go for occupation is also done, then we will go for location. So location column has 3 columns, 3 categories: urban, suburban and rural. Now for urban, suburban and rural, we will try to replace it, and we'll try to give us it a label encoding. So urban we are giving 1, 2, suburban we are giving 1, and rural we will give as 0. So here we are doing label encoding, and we'll move forward. And then we have this location column. Location column again, we will do the location column has automatically converted to 10, which was earlier urban, suburban and rural. Then we will do it for marital status. Marital status, we can see married, single, divorce. Here also we have the data, but we cannot see any hierarchy between married and single and divorce. So for that we have to do one hot encoding for that information. And here we are doing the same way, one hot encoding, where we first create a one hot encoding one hot encoder for object, and this one hot encoder object will fit transform over the marital status data, and we will use pd.data frame to create this one hot encoder. So we will use this array which is generated, and columns we are going to use the columns one hot encoding ms dot categories. So we are going to use the same one hot encoding method that we have used recently, and we have successfully converted a marital status column as well. Then we have again this categorical columns. Now we will try to understand marital status done. Then we will do it for employee status. Employee status again, full-time, part-time and self-employed. It cannot be hierarchically recognized. That for label encoding is not possible. So label encoding we cannot do it. So we will do one hot encoding again for this data, and we are removing the full-time. We are keeping part-time and self-employed. So then we will use home ownership status. Home ownership status basically has only 2 categories, that is own and rent. So we can simply do label encoding. We can use replace method. We will set own as 1 and rent as 0. You can do vice versa, it doesn't matter. Only thing is we have to put a number for that particular data. Home ownership status is also completed. Now we will do it for type of housing. There are 3 type of housing, that is single family home, apartment and townhouse. And here also we need to do one hot encoding, and we will do one hot encoding and convert the data. We are removing one column over there, and then we use it for gender. Gender has only two categories, that's why we can simply do label encoding, converting male as 1 and female as 0, because machine will not understand what is male, what is female, it will understand only 1 and 0. Then primary mode of transportation. Primary mode of transportation we have 1, 2, 3 and 4. And these are not hierarchical related, which means public transport is not going to be superior than car, or car cannot be superior than public transport. The likeliness or occurrence of these data are not interconnected or hierarchical in nature. That's why we have to do one-hot encoding here as well, and we do one-hot encoding, that is car, public transit and walking we are keeping, and we are just removing this one category, that is biking or something, we are just removing it. Now once we do that, what we will do, we will drop all these columns which have been encoded successfully. So we will drop it, all the columns: primary mode of transport, type of housing, employee status, marital status, occupation and income, because these are one hot encoded data. This data has been one hot encoded and created into a new column. So a new data frame. So primary mode of transportation is a new data frame now. Type of housing, which was earlier one column, is a new data frame called as TH. Employee status, which was one column, which was transformed into multiple columns, that is a new data frame. MS, which was earlier a new one column, it is transformed into a new data frame MS. And occupation, which is a new column, which is transformed into occupation. So likewise, all the columns needs to be transformed, and we have transformed this. We will add the data which was there, okay, wherever all these columns were there. Similarly, in the same order, we are going to add the other columns, the same columns data frame. So for example, right now in our X we have age, education level, number of dependents, location, work experience, household size, ownership and gender. We have successfully done the encoding part, label encoding part for these all columns which were categorical, and numerical column we do not have to do any change. Rest other columns we are doing change, but we will concatenate the existing X which had these all columns with the data frames of these columns which are removed. So how we are doing it? Say for example, I have age, education, all these columns till gender. Now public transport we are adding, which is car, public and all. The single family home, type of residence we are adding, as well as employee status, marital status, occupation, all this category of columns we are adding, okay. So once we do it, we have an array which is not losing any information except the one categorical column from each of the one hot encoded columns. Why we are doing it? Because we just want to remove the multicollinearity effect over here. So this is our set of columns, and then we will use y is equal to df income. We are creating a new column which is y, or array, which will hold income column. So here we are predicting income of a person based on certain inputs which are here, like age, education level and all other inputs. Based on these inputs, we are converting, or we are trying to find out income of an individual. So our X is going to be all these columns, and our Y is going to be the income columns. Then we will install TensorFlow. If you already have TensorFlow, no need to install. Otherwise, you have to use this command pip install TensorFlow. It will install the latest version of TensorFlow. Then we will import TensorFlow, which is just now installed. We will import TensorFlow as TF. We will then import Keras sequential model. Why we are using sequential model? Sequential model will allow me to stack one over the other multiple hidden layers and layers. So we are using sequential model. Then we will use dense. Dense is a layer. Now what is this dense? We will discuss at the time of implementation. Then we are using train test split to split the data into training and testing, and then we are also using standard scaler. So what we will do, we will first split the data into training and testing. So we have already done this in machine learning. We'll try to understand what happens here. So our data x and y, which is our input and output, we split the x and y into two further parts, that is two parts, that one part will be a training part, another part will be testing part. So x train and x test is a division of x, and y train and y test is a division of y. X train has 80% of data because the test size we are keeping here is 0.2, which means testing data will have 0.2% of data, which means 20% data is testing and 80% data is training. Why we are putting 80 and 20 as a split? Because 80 and 20 is the right proportion to train and test a model, so as to make the model understand the hidden features of the data and also validate the model. So that's why we are using training and testing. So x train we are keeping and x test we are keeping, then we have y train and y test. So whatever is the corresponding x value, for that value the y value will be selected in the splitting part, and the training and testing of data is shuffled and it is then splitted. So we are using a random state here because train test split will always split the data into randomly. So randomly we are getting a pair of x and y into x train, y train, x test, y test, and random state we are fixing as 0 because we do not want to keep the data changing all the time when we are running it. After that we'll call the standard scaler. Now we have imported the data that we have is in different order. If you talk about x, we can see age is 5669, but education level is 210, 210, number of dependents is 50, 123, and so like that, and location is 122, 212, like that. So we can see each of the data is not on a single scale, which means this is in 2 digits, this is in 1 digit. Somewhere we can see data which is in again in 2 digit or 1 digit and like that. So we want to keep a uniformity across all the data. Why we do it? Because that helps us in doing faster processing of data, and as we are doing a deep learning model building, so deep learning always is a computationally expensive. That's why it is better to scale the data. So it is better to scale the input data, that is x train and y train. So we scale the data using standard scaler. If we transform the x train, we will transform the x test based on the training fitting which we have done on the training data. Then we are using model as sequential. This is our model. So sequential is our model. Sequential enables me to put all layers one over the other. Then we will have a look at the shape of the x train. So x train has a shape of 21. So why we are doing this, I will tell you, because we want to fix a size of the input data. Before going into model building, so we have created a model is equal to sequential, which is an empty model and which will have multiple layers over it. So right now it doesn't have any layer. So before going into layer building, let us understand what is this what is the concept of activation function. So we have discussed recently what is an activation function. So activation function is the processing. So say this is our neuron and it is taking some input x1, x2, x3, x4 as we discussed, and there are certain weights associated, weights 1, weights 2, weights 3 and weight 4, and there are certain values to these weights. Now what happens in the activation function? Activation function takes input data and processes the data based on the activation function that we have decided. So whatever is the input value here, our activation function, whatever activation function, according to that the value is processed and a signal or a value is generated as an output. So if it is a step activation function, so it will set the data into 2 stages, that is 0 or 1, which means whatever is the value, it will convert that value into 0 and 1. Similarly, sigmoid activation function is a binary activation function which will give me probability of values. Okay, So it will give me two set of probability values. Basically higher values basically indicates that that is going to be one category, lower probability values indicates that it is a zero category. So that is our sigmoid activation function. Then we have softmax activation function. Softmax activation function basically converts, takes all the input data and converts it into the n number of categories. If say if we are having 3 categories, so softmax will convert it into 3. So 3 probabilities it will give, Thailand, Jamaica, Dubai, say for example. So it will give probabilities of being Thailand, being Jamaica or being Dubai based on this input data. Similarly, we have tanh activation function. Tanh activation function gives me data as negative or positive. It is kind of a linear set of activation function. It is giving us value between -1 to +1. Then we have ReLU. ReLU activation function gives the data as 0 or positive, which means whatever, after processing this data, after doing some computation, whatever is the value, it will convert it into, if it is negative, it will convert it to 0 or it will convert it to positive. So if it is negative, it will convert to 0, or if it is positive, it will keep it as it is. So ReLU activation function converts the data as 0 or positive. So these are our activation function. Now if we have this clear understanding of this activation function, we will slowly implement this activation function, and slowly you will be able to understand what are the uses where we can use this activation function. Okay, so let's move forward. So initially we have created a model sequential model which is empty and it doesn't have anything over it. So what we will do, we will first add a dense layer over it. So we are adding a dense layer of 128 neurons. Now this is a dense layer, and what is a dense layer? So when we talked about our neural network, so dense means each neuron in this first layer is connected to each neuron in this next layer. Okay, so dense activation function basically tells us that dense layer is all about connecting all the neurons to all the neurons of the next layer. Now this is our input layer, and that is why we need to specify input dimension. So input dimension is equal to the number of columns that we have in our data. So in our data we have columns as 21. We have 21 columns. That is why we are going to use the extend.shape1, which means I am taking 21 input from our input data, and then activation we are keeping it as ReLU, which means in the first layer the activation function is going to be ReLU. Now in the second layer we are keeping ReLU activation function. Why we are using ReLU? ReLU is used to break the linearity among the data. ReLU brings non-linearity in the data. It removes the dependence of a data. That is why ReLU activation function is very much helpful. Then we are reducing the neuron size after every layer. So here we had 128 neurons. In this layer we have 128. Here we have 64, then we have 32, and in the output layer we are having only 1. So in output layer we are keeping one output, which means we are keeping only one neuron as an output. That's what I am saying, that in the output layer, if it is regression problem, we will keep one neuron only. That neuron basically, whatever is the output of that neuron, that basically is our output or y value. So we have constructed this model. After that we will use compile. So when we use compile, the optimizer is going to be Adam, and optimizer, what is optimizer? Let's discuss this. Optimizer is the method of recorrecting weights. So in our neural network, if we talked about this neural network. So in neural network we are propagating in forward direction like this, and we are generating some output in the forward direction. If we are moving in the forward direction, a output is generated. Say in my case I have only one neuron, so we are generating output for this neuron. So this output is compared against the actual value of the output, which means for this set of input data, what is the output data? So when we talk about a neural network, we have something called as a forward propagation, and then we have backward propagation. So what is backward propagation? In backward propagation, we see whatever is the output generated by this neural network, and we compare it output with the actual data value. And this is what we are going to do here in the backward propagation. We see what is the difference between the actual and the actual as well as the predicted value, or the value generated by the neural network. And the purpose of this neural network training is to minimize the gap between this actual and the predicted value, and that's what we do in the backward propagation with the help of gradient descent and different optimizer algorithm. And that's what we are going to do. We have discussed already all these optimizers in the theory part, and we can see we are using this optimizer, which is ADAM optimizer here, which is the best optimizer. And ADAM optimizer helps us to optimize in a way that it converges to the lowest possible error with high speed and effectively, and that is why ADAM is used. It is very effective optimizer. We are using loss calculation with respect to mean squared error, and metrics we are using is the mean absolute error, which means we are trying to reduce the loss, which is mean squared error, and the performance we will be governing with respect to mean absolute error, which we want to reduce. Then we compile the model. Once the model is compiled, now we will fit the model with the data. So the data that we are going to fit here is the X-train and Y-train values. We are putting epochs as 500, which means we are trying to build up 500 times of training, which means what? In each training we are using a batch size of 32, and validation set split we are going to use as 0.2. Now we take data set in an epoch and we train the model on that data set, and whatever is the error generated, we try to reduce the error by changing the weights of that neural network. So in the next epoch we will change the weight, and we will change the weight in a way ADAM works. Okay, ADAM is an optimizer, basically a gradient descent algorithm. So it will try to reduce the loss, which is MSE. So weights will be changed with respect to reducing the loss, and every iteration this operation happens. So in the first iteration training happens, and in the second iteration the weight adjustment and retraining of the model with respect to the new changed weight will happen. So we can see that initially the loss is very high for validation data. Mean absolute error is also very high, 77.3352. And as we move forward in the next iteration, yeah, again it is very high and the loss is also high, but in the third epoch the mean absolute error goes down from 77 to 74. Similarly, it goes down further up in the next iteration, then again goes down, and as we go forward in each and every epoch we can see the mean absolute error is going down and down and down. So as we move further with the final, if we talk about the last epoch or last set of data where we are training it, we can see a comparatively very low mean absolute error. So earlier we started with 77 like 7,70,000 was the error that we saw in the first part, but 7 lakh, just let me confirm the number, it is 7,73,000 was the initial starting error or mean absolute error, and at the end let's see what is the mean absolute error, which is, it is going to be somewhere 1,03,000. So it is getting reduced by 6,000. If you increase further the epoch, it may also get reduced. See what happens in a gradient descent is our algorithm. So if we talk about the weights and if we talk about error, so error keeps on increasing, reducing at a point, and again it goes back up. So you can see somewhere it is up and somewhere it is low. So our objective is to find out a spot where the errors are least. or mean absolute error is least. So here we have least error compared to this, okay. And if we see the convergence, so our errors or our gradient descent algorithm goes in this direction where error is least at this point, and the way we are fixing the learning rate, it will automatically converge. So it keeps on happening and we are actually moving forward. So if we are increasing now further the epochs, it is not necessary we will go to where lowest value of error. It is the lowest value of error is fixed. Like below this, it cannot be going lower further. So that is why here we have to stop, and we see that at the epoch number 498, we have a considerable lower value of error, and this is something which we can store it at the later point for building the model. So right now, if we talk about this entire scenario, we have kind of optimized. We were at 7,73,000 and right now we are at 1,32,3,000, which is the lowest error. Now once that is done, we will evaluate the performance of the model. So for that, we need to find out the loss and mean absolute error by using model.evaluate, and we will evaluate over the testing data. And we see on the testing data we are getting an error of 851, which is too high. We'll try to test this data and how the errors are going with respect to training and validation. So for that, we will try to reduce, or we will try to plot the data using the plot function, and we are going to plot the actual model loss with validation loss at each step. And what we are going to do is we are going to have the epochs on the x-axis and loss on the y-axis. So we can see that the blue colored line basically represents the loss of the overall model, while the orange color line basically represents the loss at that particular validation data set. So we can see a considerable the loss over the data loss over the actual model is very less compared to the validation loss. Loss at the validation is very high. So this is how the model is developed. Now if we want to fine tune the model, we can change the parameters, we can change the epochs, and we can increase the number of layers in a model. For example, here we have used, so here we have used 1, 2, 3, 4. So there are 3 hidden layers. We can increase the number of hidden layers and the number of neurons, and based on that, it will help us out in getting more accuracy towards the model. Now one thing we have to keep in mind, if we increase the number of layers, so the model will become heavy and it will take time to process the information and develop results or give some output. So based on that, we have to decide like what is the processing power that we are having with our computer and all, or whatever application we are using. If we are using an application, how much of computational speed we can afford to provide to that model. So based on that, we need to decide what kind of model and how much dense it should be. So at the end, we can develop predicted values, and we can predict the data using the predicted values, and we can see y-test predicted values we have developed. We can compare the predicted value with the actual value and try to find out how much is the performance. If it is good enough, we can definitely go with the model. So right now we are using a very common data which is not at all aligned with linearity, and it is not a logical data set, to be honest. So we are just using randomly one data set. We are considering some parameters as input and we are considering one parameter as output. So the objective of doing this is so that you can work on any models without any so that you can develop any models if you have such kind of data set. So this entire code helps you out with developing model and with any kind of data set if you are doing it for regression purpose. So we have seen how we perform regression. So we are now going to perform classification over our regression over our model or over a data set using ANN model. We are using ANN here for classification purpose. So as we can see in this data set, here we have this model. We are using ANN. The architecture will be same. This is our input layer. These are hidden layers. This is output layer. These circular bodies basically represent neurons, and there will be a different set of activation function. We have already seen the activation function and description in the previous ANN regression class. So we will skip this part of introduction to this ANN. Definitely you can refer to it for reference and understand better. Now we will move on to the data set, the actual data set. First we will import pandas as PD, and then we'll import numpy as NP. We'll use matplotlib.pyplot as PLT. These are the general dependencies or libraries which will help us to process the data and organize it in a very structured way. We have already discussed this. We are reading the data set and we'll try to understand the data set. We have user ID as a column, we have device model, operating system, app usage, and all different form of columns are there. Screen on time, we have battery drain, we have number of apps installed, we have data usage in megabytes per day, and age, gender, and behavioral class. This behavioral class can be anything, like it can be these classes basically represent a severity of usage of phones or devices of an individual. So these are individual. This single row represent an individual, which phone he is using, and what is the usage statistics, and in which category this particular person lies into. So now we will try to understand this data better with the help of info function, and this info function will give me the data and its statistics, how the data is actually distributed. It is having 700 non-null values, 700 non-null values in each of the column, and there is no missing value actually, and we can see some integer values, float values, object, and all different types of data is here. Then what we will do is we will start analyzing data one by one. So the first thing that we will do is gender column. We will see the gender column, the count is quite symmetric, it is balanced, and we are not doing visualization here. We will directly be doing the data cleaning part, and we apply label encoder over a column that is device model, because it is a categorical column. Device model, if we talk about this column, we are going to apply label encoding. Why I am applying it is just to convert the number, just to convert the data into numeric part. Here my idea is not to get a highly accurate data model or machine deep learning model. Here my objective is to show you how the implementation works. So I'm not bothered about what kind of data is there inside this column. I'm just going to implement it straight away. So I will implement label encoding. By logic it should not be there, label encoding should not be there, but just to ease out the process and speed up this explanation, that is why I'm just using using label encoder here, which is also fine, which will help you to understand better about the data. So each devices will be encoding with respect to the model or device it is having. Then we have label encoding done over the operating system. Here we can do label encoding. There are different operating system, we can see Android, Google, and all. So we are applying label encoding over it. Actually by logic we have to go and we have to convert this as one hot encoding, which we are not doing for the sake of time convenience. So ideally you should go for one hot encoding for these two columns. Now we'll move forward with the third column, that is operating system. We have already converted it as label encoding, and after operating system we will use gender, on which we are again using label encoding. Gender has only two categories, so it is fine with label encoding over gender column. Now we will drop certain columns, that is user ID, behavior class, and operating system for X. So in X we will not have user ID, behavior class, and operating system. We will convert it into we will remove it, and on the X is our independent data or input data. So X will not have all these columns, the rest other columns will be there. and y will have only one column, that is user behavior class. So y will have user behavior class as only column, and what we are going to do is we are subtracting y with one value, because when we if you see this user behavior class, user behavior class has values 1 to 4 as values. There are 4 categories in user behavior class, which is 1 to 4. So as it has 1 to 4, and we are developing a deep learning model over it, and when the deep learning model starts working and we use the deep learning model, and when we develop an algorithm and it tries to develop some relationship, so 1 to 4 are not the number it is going to consider. It is always going to start with 0. So it wants 0 to 4 or 0 to 3. So here we are using 1 to 4. So 1, basically what we will do is we will subtract each value with 1. So 1 will become 0, 2 will become 1, 3 will become 2, and 4 will become 3. Like that we are going to do. And there are 5 unique values in y, so which means there is values from 0 to 4 here. And then we will apply standard scalar over our x data, and when we apply standard scalar over x data, entire data will get reduced to a lower version. And once the data is getting reduced to a lower version, or a version which can be suitable for computation purpose, then we will split the data into training and testing part. It is fine if you do it after or before. If you are doing it before, so better you do it for entire x. If you are doing it after, then you have to do it for training and testing, as we have done in the regression class. So both the methods are fine. So you can see the regression ANN regression class or the tutorial, where you will see the alternate approach of doing training, testing, split, or doing the standard scalar part. These two process we can do in alternate methods. Now we are splitting the data in the same proportionate that we have used recently. So 0.2 is the testing size, and training size is going to be 80% of the entire data. We had 700 data points, so it is going to get splitted accordingly. Now here we will again import the model, that is sequential, and then we are using layers such as dense and dropout. Now this dense and dropout, we have already discussed about the dense layer. We will discuss about the dropout layer, what exactly it is going to do in our model. And these are all activation functions which we have already discussed in the previous class. So right now I am going to skip it, and we will move ahead with the model building. So here we have a sequential model, which is an empty model basically, which allows us to stack up layers one over the other. And the first layer is the input layer, which is a dense layer with units or neurons as 128. And here we have activation function as ReLU. Always ReLU is going to be activation function for the input as well as hidden states. And input dimension, or the data that we are getting, is going to be in the shape of xtrain1 dot shape1. So xtrain1 dot shape1 will give me the input data, or the columns, number of columns in the input data. And then we are going to apply the dense layer. So dense layer will get connected. Say if I have this 2 neurons and here I have 3 neurons. So when I am applying dense layer, each neuron is connected to each other data point here. So that is our dense approach. Now we will move on to the dropout layer. So next dropout layer has 16 say output or 16 neurons. So say I have a next layer which again has say 3 neurons. Okay, so between these 2 neurons I am putting a dropout of 0.3, which means if I am connecting this with this, so I am not connecting, I am just connecting with a proportionate of 30%. I am going to drop 30% of data, or 30% of linkages to the neuron, which means not each and every neuron is connected to the every neuron. There will be a drop. Say this is connected, this neuron is connected to all 3, but this neuron is connected to only 2. Sometimes this neuron is only connected to the first and the last. So such kind of dropout will happen between these 2 layers. So dropout layer will not connect each and every layer with other layer. It is going to connect partially based on the dropout proportion that you are going to mention. Now when we are doing this dropout, so it will always drop out the data, or data linkages, or this neuron connections. So what is going to happen when we are doing dropout? So what happens when we are using dense layers? So in a dense layer, the data is the machine learning or the deep learning model is doing a lot of learning. It is trying to learn each and every feature in detail. When we are doing such kind of things, so the model becomes very active, and it becomes very data dependent, which means it is very much dependent on the input or the training data on which it is learning. It is very much reliable, but it is not reliable with the new set of data, which means if I have anything new to be if I have any new data which I am getting the model exposed to, so model will not be able to work well on the new data. It will do overfitting, which means it will work on the training data well, it will give good accuracy on the training data, but on the testing data it is not going to give good accuracy. The accuracy will drop. So such kind of mechanism is an overfitting mechanism, where it is fitting good on the training data but not on the testing data. So to avoid overfitting, we have to introduce such kind of break, which means we are not allowing our model to learn everything from the previous layers. We are allowing some kind of break. So if we are providing some breaks, and if we are not allowing each and every neuron to connect with each and other neuron, so model will now start doing assumptions. What is assumption? Model will try to generalize the data. When the model generalizes the data, here the model becomes more intelligent and gives the decision based on newer approach or some generalized approach. So model becomes good in generalization. So it is like there are two types of student. One student who studies everything and answers everything, but when we give him a new test with new set of questions, he is not able to answer. And there is a student who is not learning everything, he is learning partially, but he is trying to solve problems, newer problems which are not at all there, or he is very much exposed to new environment. So such learner will be able to work well or perform well in both the situation, when he knows the question and when he doesn't know the question. So he will equally be able to face such kind of questions. So that is why, to reduce overfitting, we are using this dropout mechanism of our data. So when we do it, we drop out the data here between these two dense layers, which means here the first layer is fully connected, second layer is partially connected, and in the softmax or the last layer, we are using y dot n unique. Now what is this y dot n unique? Y dot n unique is the total number of categories in the y column. Okay, so what is the y column? That is our output. So in the output, how many total number of unique categories are there? So there are y dot n unique. So we saw it was 5. So at the output layer, we will have 5 neurons. Okay, where it will be, these neurons will be created with the help of softmax function, which means these 5 neurons are created using softmax function. Now what happens in a softmax function? There is probability assigned to each one of those, and when we sum up the probability, it is going to be 1, which means the value or the category which has highest probability will be considered as the category. This particular category, suppose this category has the highest probability among all other categories, so that is the class of that particular input row. So based on that, the softmax activation function works. And then we can also use checkpoint, model.checkpoint. So sometimes it is not working in the newer version, so you have to downgrade your TensorFlow and then work on it. So better you can use it, otherwise you can skip it out. There will be you can refer to the Keras documentation, official documentation for model checkpoints and callbacks process. So what is callbacks process? Now when I am developing a model, as I discussed, like there was a point in the regression part where where we saw that at certain points the loss is going down, again the loss was increasing. So say epoch number 5, so loss is 22, and epoch number 6, the loss is 27. So I want low loss, I want minimum loss, so I want to preserve the weights of epoch number 5. So how we will do when we are working on a data set which has multiple epochs and multiple data values? So for that we will use this model checkpoint approach. So what happens in model checkpoint? In model checkpoint, it will run across each and every epoch, and it will store whenever the model loss is going down. So for example, here the model loss was 25, error loss was 25, and here the error loss is 22. So it will store this error loss, the weights corresponding to this epoch. So whatever was the weight for this epoch, it will get stored in this, stored in the callback, and accordingly all the places wherever we are getting lesser error, all those will get stored as a callback, and we can use it for developing a model. So I'll show you how it works actually. So first part is model checkpoint. Model checkpoint we have imported. So model checkpoint is to create a checkpoint wherever we are having less error. Okay. So the first thing is we will compile the data. While compiling, we are using optimizer, which is Adam. Now we are using loss as sparse categorical cross entropy. Sparse categorical cross entropy is used whenever we have classification data set. So here we are doing classification data set. So we will have sparse categorical cross entropy. If it is regression, we are using mean absolute error or mean squared error. So our loss is sparse categorical cross entropy. And matrix, we are keeping accuracy. We are focused on improving the accuracy of this model. So our objective is to find higher accuracy in a model. And then we are using checkpoint. So checkpoint will do what? Checkpoint will we will create a model checkpoint, and in this model checkpoint we are going to create a checkpoint using model checkpoint, and the checkpoint name will be this. So the name is best model weights. It is getting stored into my working directory. So when I run it, it will get stored into my working directory as best model weights.hy. So this is a file which will get stored, and this file stores the best weights out of all the epochs that we have run. We are going to monitor validation accuracy. So we are monitoring validation accuracy because validation is a newer data set on which the model is getting fitted. Then we are using SIF best only as true, so which means that it will run across all the epochs one by one, and it will save the best weights as best model weights.hy, not all the weights. And it will we are using mode is equal to maximum, which means maximum accuracy we are trying to fetch. So let's try to understand the implementation part. So when we use history, when we run the model, we will fit the data as xtrain and ytrain. We are keeping a batch size of 100. We are keeping epochs as 100, and validation data we are putting is as xtest and ytest, and callbacks we are putting as checkpoint. So here we are using an argument called as callbacks, which we have not used in the regression. So we can use it in regression as well. So when we use callbacks is equal to checkpoint, so it will call this checkpoint, and it will use this model checkpoint, all these parameters. So these are the settings. So now when my model starts learning, so epoch by epoch it will start learning. So let me show the entire epoch by epoch arrangement. So in the first epoch, the model fits the data xtrain and ytrain, and model validates on the xtest and ytest. So here I am providing my validation set also. So training will happen on xtrain and ytrain, and it will check if it is making correct predictions or not. So in the validation data set, if in the epoch number 1, the accuracy is 0.09, which is very low, and the loss is 1.8640, which is very low, and that is why we can see it is the loss is 1.582 on the data set. Accuracy is considerably increased here. The accuracy is higher here, and the validation loss is 1.3, and validation accuracy is 0.39 in the first epoch. So we will focus on validation accuracy for now, and let's see how it is getting improved over the time, because here we are going to monitor validation accuracy. Wherever we are having validation accuracy as high, we are going to store that weights, corresponding weights. So that is why we will focus only on validation accuracy epoch by epoch. So if we talk about this epoch, validation accuracy is 0.39, and epoch number 2, we can see the validation accuracy is 0.37. Okay, we'll move forward. In the epoch 3, the validation epoch is accuracy is 0.47. Now what is happening? So here accuracy was high, the weights corresponding to this accuracy will get stored into this checkpoint. Now in the second accuracy, second it is getting down. So in the second epoch, the accuracy is low, which means we are not going to preserve the weights for the epoch number 2. In the third epoch, the accuracy is increasing, which means now we have to replace the weights which were earlier preserved. So we will replace the weights which were earlier preserved, and we will store only the weight of epoch number 3. Similarly, in the fifth epoch, we are seeing a considerable fourth epoch. We are seeing a considerable improvement. We are seeing the accuracy, validation accuracy going up as 0.54, and we will store that epoch weights now. We will not store the weights for third epoch. Similarly, when we go for fifth epoch, the accuracy increases. Now the old weights will get replaced, and we will store the new weights of epoch number 5. And similarly, as we go down and down and down, it will keep on replacing whenever the accuracy is increasing. If the accuracy is going down, it will not replace, it will preserve the old weights only. So this is how the process goes. Like here, if you see the epoch number, let me confirm, epoch number 10. So in epoch number 10, the accuracy is 0.95, but in epoch number 11 we can see the accuracy is 0.93. So which means here the weights were fine, it was working fine and showing high accuracy, but here the weights got down. So here the accuracy is got down, so we will not save the weights of epoch number 9, 11. We have saved only the epoch number 10 weights. Now we will move forward in epoch number 12. Epoch number 12, again 9571 is our 9571 is the accuracy here. Earlier we had 9500, so which means epoch number 12 is better than epoch number 10. That's why the weights of 10 will be removed and the weights of 12 will be preserved. This keeps on happening continuously at the end, which means once the entire epochs are finished, like 100 epochs are done, wherever we see highest accuracy, here in this the highest accuracy is at epoch number 97, where the accuracy is 100, which is 1.0, which is 100 completely accurate model, which is considered to be. So the epoch corresponding to so the accuracy corresponding to epoch number 97, or the weights corresponding to the epoch number 97 is now added to the callback. And now we will do a simple prediction here. So when we do the prediction, and we have created the model, the weights have been saved, we will do the prediction and we will see that some value is getting generated. So when we talk about ypred, so ypred, we are putting all x data and we are predicting the prediction. So these are the values generated, 0, 1, 2, 3, 4 categories or classes, and we will see how the model is performing over the testing data, and we can see that model has perfectly performing over the testing data. Only one problem is there in this particular, when it is trying to predict say category number 4 or 3. So here we are getting error, otherwise the model is perfectly working on the testing data, which means here we have developed a perfect model. Ideally it should not be, because as our model is very as well we were training, we are getting a good model, but ideally as the way we have arranged the data was not logical at all, so it should not be relied upon. But yeah, this is how the model works. And now we will predict the history of the data. So history, how the model accuracy or validation accuracy compared to the original model accuracy were. So we can see that as the model accuracy was going down, which is in red color, the green the accuracy of the validation was also going down, which is in green color. So red color and green color both are going down in a similar pattern, which means the training accuracy and the testing accuracy or training loss and testing loss are going down in a same fashion, which means they are totally aligned, which means the model is learning well on training as well as validation, both the methods. And same we can see for accuracy as well. So model is learning well over training as well as testing. We can confirm it with respect to accuracy, this graph. Okay. Now if you talk about this weights, we can use this weight which we have preserved, which is stored in the form of H5 format, best model weights.h5. So we can call in any time and we can create a model out of it, and that model can be utilized for building accurate models. Okay, so right now we are saved with highest accurate model, and that's what we are getting. We are getting a model which is highly accurate. Somewhere we can see a little bit reduction, but yeah, the accuracy of training as well as testing are totally similar. So we have developed a very correct model here. That's the implementation of classification algorithm. How we can implement a classification: we have to do the same data cleaning process as we are doing. You can use your own strategy of cleaning the data that you have done. This is entirely focused on deep learning classification. You can clean the data as per your data cleaning methods, encoding methods, decoding method, missing value treatment, outlier treatment. Further to that, you can use standard scaler. After that, you can just use the train test split, and you can call in the sequential model, and you can add up multiple layers, that is dense dropout, compile the model and fit the model using training and testing data with the epochs that you decide, and this way the model will learn accurately from the data. Now we will start with convolutional neural network. So we have already seen what is a convolutional neural network. We will try to understand this with a very shorter architecture over here, how the implementation works, and then we will start implementing the convolutional neural network. We are going to see the two most popular convolutional neural networks, that is LeNet and one which is VGG16 model. We will try to understand all these models, and with this you will be able to implement any kind of convolutional neural network over an image data. So what is convolutional neural network? So convolutional neural network involves two parts. First is the convolutional part, and the second one is the neural network, which is our normal traditional ANN network. So in the convolutional operation, in the convolution part, we will apply a convolution operation, and in the normal part, in the ANN part, we will just apply an artificial neural network, a normal artificial neural network, whatever we have developed or learned earlier in the previous classes. Convolutional operation usually happens over the image data. It is very well worked out on the image data. All the image processing algorithms, all the image identification, classification, operations, everything that you can see on the internet right now with respect to images, where it is automatically classifying something as some category or some other category, is using convolutional neural network in the backend. So this is the backbone of image processing in the today's world, and that's what we are going to learn today. So first thing that we are going to understand is it works well on the images. So let's start with an example, which is an image. So here we have an image which is of a zebra, and on this image we consider this image as our input data. So our input here is an image, and on this input image we are going to apply the convolutional operation. So the convolutional operation start with identifying the convolution operation starts with identifying patterns in this image. Okay, how does this happen? So it happens with the help of kernel technique. In the kernel we have in the kernel technique we do extractions of important features from these images and preserve it into a array. So first thing is that image that we can see in front of us is a formation of three parts. It is the rows, the columns, and third is the channels. So image is formation of three parts: width, height, and channels. So what are these channels? Channels are every image is constructed with the help of three channels, that is red, green, and blue, and that's how any image is getting distributed. So we have three channels, and for these three channels we are going to apply a kernel over the three channels. So the first channel will be of red, second channel will be of green, and third channel will be of blue. So these channels are important to identify, distinguish anything between with respect to colors. Now a image can be split up into three parts, that is red, green, and blue. Now in a kernel, so kernel is a formation of a matrix. It is a matrix which which has certain numbers. These number represents a particular feature. So it can be, this number can be like cross. So if I am trying to identify a cross, just give me, so say I want to extract something from this data. I want to extract so this is my image, and I want to map this image with respect to such a line. So 1 1 1 represents there is this horizontal line. Okay, so this particular matrix that we can see is a kernel. Kernel sees that what is happening, what we are trying to identify. So we are identifying a line. Okay, so this kernel is nothing but line, where this 1 1 1 represents this line and 0 0 0 represents that there is nothing in this part. So I am identifying kernel, this line in my image. So I apply this convolution operation on this each and every part of this image. I will constantly keep on applying it over the entire parts. Now what happens in this? So say my image has, just a minute. So here we have an image, and in this image line is present in this part and this part, and I am detecting line in each and every space. So in this space line is not there. So when we apply the convolution operation, so this line basically represents 1 1 and 1. So 1 is not present in this place. So I will multiply this this entire values with this values in this corner. Okay, so I am applying convolutional operation. So here the empty space basically indicates 0 0, empty space is 0, and this line represents 1. So line is 1 and rest other part is 0 0 0 and 0 below as well, which means when I do cross multiplication of this array with this part of the image, so the resultant will be 0, which means I have not detected anything, I have not detected a line. So then I move forward in this region and I will do the cross multiplication of these values with the values in this array, and again I have not detected anything. Similarly it keeps on happening. Okay, the size of this image, say it is 10 by 10, when I apply the convolution operation it may become 5 by 5 or 3 by 3 or 7 by 7. Convolution operation is to minimize the unnecessary information in a data set. So we apply this convolution operation over this data set in each and every corner of this data set, in each and every corner. And once we apply this in each and every corner, so when we reach at this corner it will tell us that yeah, some line is represented here. So here it will just give out a value as 1. Here it will return 1 and rest other values will be 0 0 0. So shorter version of the image tells us that we do not have anything in the corners, we have the line, or this line was present at the center. That's why we are getting a new matrix which is shorter version of this. This was 10 by 10 array, and the new array that we have, say it is 5 by 5 based on the kerneling operation that we are applying. Now while we are applying this kernel operation, there are two things that we have to keep in mind. We have already discussed this in the theoretical explanation. First thing is how much gap we are taking at every corner. Okay, so at every, so first box is this, so second box is just after this first row, or it is directly after 2 rows. Okay, so this particular thing that we are going to talk is stride. So stride is how much stride is all about skipping out search in that particular. Striding is skipping out searching certain rows in that or columns in that particular array. So stride, usually the search process goes like this. It will search in all these corners first, one by one, and then it will go down. So it is vertically going in this horizontally going in this direction, and vertically it is going in this direction, which means the movement of this kernel or the multiplication operation of this kernel is going to happen in each and every corner. So stride will tell me that should I do it in each and every corner, or is it fine to skip certain columns. For example, if I am doing search in this column, So if I am putting stride of 2, so it will say stride of 2 or stride of 3. So if I am searching in this corner, if it is done, do I want to search from here, or do I want to skip some and I want to search here? So this operation striding will decide. So how much I have to move in this direction horizontally and how much I have to do in this direction. So the stride will decide the speed of kernel operation, and second one is pooling, padding. Second one is padding. So padding is all about helping the kernel to learn everything in the data. So when we are applying a kernel technique, for example, and if I am keeping stride of 1 unit in the horizontal direction or in the vertical direction, so what will happen is it will skip one row at a time. Okay, it will skip one row at a time, it will skip one row at a time, and it will keep moving forward in the right direction as well as the vertical direction below. So while this is happening, it will be able to search more in this part or the central part, but it will skip out the corners. But if you want to the algorithm not to skip the corners as well, so we can add a padding. Padding is all about adding an extra layer, on top of our array. So this is our array. So any image can be transformed into an array. So this array, in this array, I am adding a padding layer. Okay, so we are adding a padding layer on top of this array. While we are adding a padding layer, so it will skip this part. Padding is all about having zeros, increasing the dimension of this image and having zeros on top and below and all the corners. The values will be zeros in all the corners. So when I apply convolution operation, so it will search more in this region, search here, and likewise it will keep on search here, or search the kernel feature into this, and it will search here again. So while this is happening, it is not skipping the central part, which means it is now be focusing more on the central part as well as corners of this image, which means when we are applying padding, it will do extensive search in the central part. This becomes the central part and the padded region becomes the corner. So it will now skip the unnecessary padded value and it will search more in this part where the image is actually there. So padding is done to avoid the kernel or feature mapping skipping the corners. So when we are doing normally over in data, it will skip the corners, but when we add padding, it will skip the padded part, or it will search less in the padded part. So that is the benefit of adding padding. After that, once we do have this convolutional operation or the kernel feature mapping, so whatever is the output array, we will do pooling of it. What is pooling? Pooling is all about reducing the image dimension. So earlier this was 10 by 10 and I got an image as 5 by 5 as an output here. This is 5 by 5 say. So when I do polling, I will extract useful information from this 5 by 5 array and convert it to say 3 by 3. So pooling basically helps us to extract more information from this data, or it helps us to extract meaningful information from the data. So there are different types of pooling, that is max pooling, average pooling, min pooling. Usually we are using max pooling and min pooling, average pooling. So pooling operation will reduce the image further in shorter one, and we can have multiple convolution layers. So this is my first convolutional layer. So here we have this first convolution operation happening, convolution plus ReLU operation. This is the second convolution plus ReLU. This is the third. Why we are using ReLU? ReLU helps us to break the linearity. So we want to break the linear dependence or linear association among the data. That is why we need to put ReLU activation function as well. And once this is done, we get, say for example, I just remove this 2 layers. I am having a single kernel, single image. I am applying convolutional operation where I will apply the kernel method. I will multiply or search for features inside this data, and I will do the pooling, and after pooling I am getting an array like this. So what is this array? So I have to I am getting an array of images, multiple arrays I will be getting. As you can see, multiple small arrays will be getting. So we have to feed this to a neural network architecture. So if I want to feed this image to a neural network architecture, I cannot directly pass this array to the neural network. So what I have to do is I have to flatten the image, which means whatever is the image, whatever is the array that we have got, we will flatten it, which means the array will be converted. So if say my array is like this, it has value 1 2 3 4 5 6. So when I do flattening, it will become like this: 1 2 3 4 5 6. My array will be flattened and it will convert my two-dimensional array into a single dimensional array. So that is what we are going to do in the flattening layer. Flattening allows to convert the data into one dimension. Why we are doing it? Because the neural network cannot accept two-dimensional images. Neural network needs one-dimensional information to do the processing. So now each and every attribute will be set out here as an individual input data, and the two-dimensional data will array will be getting converted to one dimension, and each and every value will become an input. And then we will apply a fully connected neural network. Now fully connected neural network, this is the same that we have seen the normal ANN architecture, and then we can use classification over it, and based on the probability value we will decide whether it is horse, zebra or dog. So this is the entire convolutional operation in short we are doing. So to sum it up, what we are doing is, a image is there, on it I am applying a convolutional operation. What is convolution? Convolution comprises of feature mapping certain features from the images with the help of kernel. Kernel will search the image features in that image, and if the features are mapping, it will get stored as numbers with the cross multiplication or the multiplication between the kernel value and that particular area. While it is doing, it may lose out the corners. To avoid it lose the kernel, what we can do is we can use the padding process. Also, if I want to skip certain regions and move forward faster, which means if I want to do the search but I want to do a faster search, I can stride or increase the stride, which means I will now be not searching each and every corner thoroughly. I am just searching fastly and skipping certain rows from the data. So this entire operation keeps on happening, and once this is done, I will get an array. I will apply the ReLU activation function and I will get an array of features or reduced version of the images. So this image is there, reduced version of the image I will get. On this reduced version of image, I will apply the pooling method. Pooling is all about extracting meaningful or insightful information. So I can use minimum pooling, maximum pooling or average pooling. Once the average pooling, minimum pooling, maximum pooling, any kind of pooling which we are applying is done, I will convert the data. I will get an array, multiple arrays I will be getting for each and every aspects of this data, and this array, these all set of arrays cannot be directly fed into the neural network. So I have to convert it into flattened layer, which means I have to convert everything into a single dimension, and that's where I use flattening layer. Flattening will convert all the arrays into single dimension, and then we apply the fully connected neural network over that data, and we will get the decision whether it is horse, zebra or dog. So that is the entire CNN architecture that we have talked about. Now we'll start the implementation. To start the implementation, we will first import sequential from Keras.models. Then we will import layers, which is convolutional 2D, max pooling 2D. We are going to import layers, that is activation layer. We are using flattening, we are using dense, we are using dropout. All these layers we are going to import. Then we are using import backend SK. Why we are using backend SK? It helps us to process the information or the image information while we are working on it. Then we will use image data generator. Now what is this image data generator? Image data generator is a part of data augmentation or image data augmentation. Image data augmentation is say for example, I have an image, and I have an image of dog, okay, with me, and say if I have another version of the same dog, okay, zoomed version of that image, which means the face of the dog is big now. So this is also a dog and this is also a dog. The only difference is this image is a bigger one, but the dog size is small, and in this image the dog size is big. Sometimes what happens, like I have half face of the dog, and here I have full face of the dog, okay. So even if it is a half face, it is a partial representation of a full face. So this is also a dog and this is also a dog. So what happens, we cannot have all this possible set of data for the same image. If I have the same image and if I'm passing the same image in a different format, for example, the location or the position of the dog has changed and it has moved somewhere else, and if I'm trying to use that data to recognize or to make the machine understand, or to identify whether it is a dog or a cat, my machine will not recognize it correctly because the position has changed. So image data generator helps us to generate multiple images. It is the augmentation process. It will generate multiple images of the image, of all the dog set images. So a single image can be converted into multiple set of images with the help of images data generator. Some images will be zoomed up, some will be light colored, some will be blurred out, some will be partially shared. Shared means I will not have the entire image, I may have the some part of the image. Some images will be twisted, because it is not possible that all the time the dog the images we are going to get is in the single structure only. It may be twisted 90 degree, 30 degrees. So a single image is converted into multiple images with the help of twisting, turning, sharing it out, or um, or just blurring it out or zooming the image. Then we are importing optimizer, which is Adam. Then we are using image to array. Image to array is used to process the image. So Keras dot preprocessing helps dot image has the image processor, that is image. It will convert the image into an array. We have Keras dot utils. We have to convert the data into categorical format. Now here we need to convert the data into categorical. So we will use two categorical function from Keras dot utils. Then we have train test split. Now the images that we are going to get are not going to be in a form of Excel, right? The images will be stored in a form of directory. It will be stored in a directory. So I will call in the data images using this imutils path. So I will require the system path of that images, and I will use paths to get the images one by one into my Jupyter notebook for doing the pre-processing part. Then we have matplotlib.pyplot. In the pyplot, we use it for creating visuals or see the images. Then we have NumPy. We have argparse to parse the arguments. Then we have random, if in case we want to do the random shuffling of the images. We have CV2 to process the data. It is an open CV library which is very much effective in image handling. Then we have OS, if in case we want to get path of the images and work on the OS. So system related activity, operating system, OS will help us. We will import warnings, and we are using TQDM. So TQDM is a library which will help us to create a progress bar over the loops or the whatever operation we are doing. So we need a progress bar to just see, okay, how much it is done, how much it is pending. So for that, TQDM will help us. We have iter tools which will help us to iterate over the data. Then we have TensorFlow as TF, which is our base library for processing such kind of deep learning data. And we see the TensorFlow version, which is 2.1.2.0, which I am using. We filter the warnings and we ignore the warnings. It is essential because sometimes when we are running, you will get unnecessary warnings. So to change the warnings or remove it, we can use filter warnings. Seed we are setting it as 42 because we are using randomization here. So seed 42 will help us to use a random set of 42 number only. Here we are developing a model that is a LeNet model, classification model. I will talk about this LeNet model further. Okay, we'll discuss LeNet model for now, and then we will talk about the image handling process and everything. So LeNet model is we are creating a class called as LeNet, and we create static method, and this static method name is build, and in this build method we have width, height, depth and classes. Now width, height and depth basically helps us to tell the dimension of the image array, and here we take classes as an input, like what are the total classes. So if you are doing 3 class classification, so class will be 3, like dog, cat and camel. And if in case you are using something else, there are 4 categories, classes will become 4. So we are using sequential model or sequential architecture, on which I will post one by one all the layers, and input shape is going to be height, width and depth for this convolutional operation. If k dot image data format, which means if the format of that image is not going to be channel is equal to channel first format, which means whenever we are storing the image, always we represent the data with the help of height of the image, width of the image and depth. But sometimes some image formats, the depth is at the first, we call it as channel first images. So for such images which is channel first format, so depth will come first and then height and width will be coming. So if it is a normal image, if we will put it as height, width and depth. If it is a channel first format image, the input shape will change. That is the only difference. Okay, so it will become depth, height and width. Okay, and once this is done, we will first create a input layer which is convolutional 2D layer. So in the convolutional 2D input layer, we are specifying the neurons as 20. We are specifying the kernel size as 5 by 5. We are using a 5 by 5 kernel to reduce or apply the feature mapping process. We are using padding the same, which means we are not going to do any padding over here. And input shape is going to be the input shape, whatever input shape is there. So whether it is channel first, channel last, whatever type of image is there, automatically it will change the channel and it will create an input shape. Then we are going to add activation function, which is a ReLU. We will apply the activation function ReLU because after the convolution operation, ReLU function will get activated, and then max pooling 2D we are going to apply. We are using the pooling operation to reduce 5 by, now once I apply a 5 by 5 kernel on an image, say the image size is 100 by 100, it will get reduced to 5 by 5. Say 100 by 100, it may get reduced to 50 by 50. Further, to reduce that image and extract only the meaningful information, we do pooling 2D operation, and pooling size we are putting it as 2 by 2. We are using a pooling kernel of 2 by 2, and it will apply with the help of strides 2 by 2. Strides 2 by 2, which means it will skip one row or one column. Okay, so when it is applying one column, it is going to strip in the horizontal direction, and one column it is going to strip in the vertical direction. So both the parts, both the ways it is going to apply. Now the same convolutional neural network, here we have the input convolutional neural network. This is our next convolutional operation we are applying. Then we have the same convolutional operation. So this is a LeNet model which is developed by Yann LeCun, and in this model these are certain variables, number of neurons, number of convolutional layers, these are fixed. So we cannot, we are just applying multiple convolutional layer. We apply 3 convolutional layer, and we, after the convolution operation is done, we flatten the image, flatten the array, all this operation. The more we add convolution operation, more detail we are going to check into that image. We apply this flattening, and once flattening is done, we apply the dense activation function. Dense activation function, basically we are taking, now we are starting with ANN. This is our ANN part. We apply ANN, and we are taking dense of 500 neurons we are taking. Then we apply activation function ReLU. We can add multiple dense. The more dense we have, the more it will take time to process the information. Then the output is going to be softmax. So the activation function softmax we are going to use, and in the output we are using classes. So it is the same number of classes that we have passed as an input, and then activation function softmax will create 4 or 5 category or 3 category based on the number of classes that we have specified. At the end, this class is going to return a model. So this is how a model is getting constructed. A LeNet model is getting constructed. So we have created this LeNet model, which is a combination of multiple convolutional layers, activation function, and max pooling. Similarly, we have this VGG16 model now. VGG16 is a graphical model, or visual geometry group is a kind of organization or people who have created this model, which has 16 layers of neural networks, or layers, hidden layers. So it starts with a sequential layer, then we have convolutional layers with 64 neurons, 3 by 3 kernel. There are 2 convolutional layers parallelly, and then we have max pooling, again 2 convolutional layers parallelly, and then max pooling, and there will be some more blocks over here which will be more number of neurons and more number of convolutional neural network, but ideally I have reduced it because ultimately it will take more time to train the data and the images over it, and it will just like the laptop will get hanged, so it is not possible to train on a multiple convolutional neural network. So actually it should have 16 convolutional operations, and then after doing all the pooling and all, there are 16 convolutional layers to be honest. Here we are having only 4, and after that we have this flattening and then dense. We are using 4096 because there is a huge amount of neurons will be required, huge amount of data is getting used, because image, when we convert this image into an array, even though it is compressed one, we will be having multiple arrays, and for multiple arrays there will be multiple input. So for that we will require more number of neurons. So that is why we have this 4096 neurons with activation function as ReLU, and we will use dropout directly. Again we have 4096, which means these two 4096 hidden layers having a dropout of 0.5%. Again we are using a dropout, and after this dropout we are using this output layer with number of classes as the same number of classes that we had here, and activation function we are using softmax because output is classification, so softmax is the best thing to use, and we'll use model, will return model as an output. So these are 2 classes, and this will help us create a model, data model, that is VGG16 or LeNet. These are 2 convolutional neural networks. Now we will use the data set. We will read the data set, and this is to store the model, this is to plot PNG. For now we will skip it. We are using epochs as 25, and learning rate we are using 10 raised to minus 3, which means 0.001, and batch size we are using 32. Now here we will start with working on the images first. So it is not the CSV file actually which we read with the help of pd.read_csv. It is a complex process because images are stored in memory location, and memory location we read the address of that memory location. So first we will store data, which is image, and then we will store the labels of the data. So to store the data we will create an empty list, and in this list we will have multiple arrays, and these arrays, each array will represent an image. So every image will be broken down into 3 parts, that is 3 arrays will be that, red, green and blue. So we will have array, first image array which will be 3 arrays of red, green, blue, second image array red, green, blue, third image, like that we will be having, and we are going to convert the data into form of matrix. So the brighter regions will be given as 1 or 255 as the value, and the lighter region on that image will be given as 0. So that's what we are going to do. And labels, it is a complex process. So now we will try to understand how we are going to do that. So first of all we will grab out all the image paths from our data set. So images are stored in a folder called as data set. So what is data set? Let's see. Data set, this is data set. Okay, what I am doing is I am trying to search the data set folder in my drive, okay, in my current working directory. So in my current working directory, which is, say right now I am on desktop, dataset and CNN project file. So if I go on desktop, let me go on the desktop part, and I'll go on dataset, and then I have CNN project. So here I have my file, and in this I am searching for dataset folder. So here you can see dataset folder is there, and in this dataset folder I have 3 folders, subfolders, which is forest, buildings and sea. and in forest I will have images of forest, in buildings I will have images of buildings, and in sea I have images of sea. So I want to extract all the image paths, all the images and its path. So I will first sort the images and I will sort it out. So I will create a list of all the paths which are present in this image path. So I will use paths.list images on this dataset folder. So I will be searching inside this dataset folder images and their paths. So say this is my image, okay. So its path, memory address, that I am going to store the address of that image I will be storing into a list. Similarly, I'll do it for all the images and I'll store the paths of each and every images. I'm putting a random seed of 42, okay, to shuffle that image. Initially, I will sort the images when I'm collecting it, and then I will shuffle the images. After shuffling the image paths, we will now start with using or creating labels of that images. I just have the directory or the folder. I do not have labels like we have in the when we are working on that regression problems or classification problems. We had an Excel file where we have X and then we have Y. Here we do not have such kind of thing. We have only the data folders. So in this data set folder I have this all images. So whenever I talk about images, I am going to find out each and every image path. So I will use TQDM with TQDM. TQDM is going to create a progress bar. So TQDM is an iterator. Basically it will iterate as many times this for loop is getting iterated, and for every iteration of this for loop, P bar or the progress bar is getting updated by 1 unit. So the total of this progress bar, how many times it is going to execute, it is going to get executed the total number of image paths I have. So I am doing what, for each and every image I am trying to identify its label and store that label as well as the image array, okay. So this progress bar will run n number of times. N basically represents the size of image, the number of images that I have. Then for IDX and image path, so when I am using enumerate, it will enumerate the images as well as path, which means 0 image, 1 image, 2 image. So it will store two things, it will give me two things, ID of the image and the path of the image. I am going to store image, I will read the image from the image path. So image paths is a list of all the images. If you talk about this image paths, it is a list of all the image paths, and I am reading one by one all the images from that image paths. I am reading all the images from that image path. So when I am using for loop, I will first read the first image path and I will store that image path as an image array. Then I will resize that image. I will reduce the size of the image by using cv2.resize. It will reduce the size to 28 by 28 that I am specifying here. You can use any choice of size. Once this resizing is done, which means the image can be anything of any size. Once the image getting imported, it will get resized automatically. First operation that I will do after reading that image is resizing that image of 22 and 28 by 28, so as to have uniformity of the images. Then we will convert that image to an array format. So image is resized and now the image is getting converted to array format and stored back to image. Now this image is nothing but an array of image, and in the empty list data I am adding that array. So in this empty list data I will add that array, and for the first image I have converted it to image. I have resized that image of 28 by 28 size. I have converted it to array and I have added it to data, and for that data I have to also generate a label. For that image I have to also generate a label and store inside the label labels list. So for that I have to generate label. So to generate a label I will create image path dot split. So whatever is the image path, for example, for a particular image, if I talk about say forest, and this is the image. If we talk about this image, so forest the path of this image, I'm taking this dummy path which is from localhost, but ideally the path of the image will look like this. And I want to, if I talk about the image path, the label of the image is present over here. This is the label of the image I want for that image. So this image, the label is this one. So what I will do is I will split this path into multiple items based on this separator, which is the OS path separator. Okay, so whatever is the OS, if you are using a Mac, it will be like this. If you are using something else, it will be backward slash. So I am separating the image with respect to the OS path. Now I separate it, and I want the second last element, this one. Okay, so if I separate it with respect to hyphen or forward slash, so this is the last element and this is the second last element. So I am using image path separator, and from that I am using the second last part. So os.path.sep will give me separator, so it can be forward slash or backward slash, okay, depending upon your OS. And image path.split, it will split that data or the image address, web address or the image address based on the image path. And -2 will give me the second last part of that image, which is the address, which is nothing but the label of that image. So label is going to be the second last part. So if the label is equal to buildings, I will put label value as 0. If the label is equal to forest, I will put label is equal to 1. And if the label is equal to C, I will put label is equal to 2. So as we know that in our case, there are 3 types of folders. So if we talk about if we talk about our images, so the data set has CNN project, and if I go in the data set, I have 3 folders: forest, buildings and sea. So if it is forest and buildings and sea, I want to give it a proper label encoding. So I am doing label encoding itself here only, and I will add that label. So if it is say buildings, okay, the first image, if it is a building, automatically the label 0 will be getting added to the empty list labels. So labels is an empty list, on this I will be adding 0. If it is C, it will add 2 in the labels folder. So this way I am going to iterate over each and every images, and it will get stored inside the labels folder. Okay, labels list, and the progress bar is going to update it at every. So this is the progress bar that I was talking about. So this is getting developed due to this TQDM library. If you don't want it, you can skip it, or if it is not working, also you can skip it. It is just to track the progress of my operation. Now if I talk about data 0, so you can see that this is the first image. So this first image, as you can see, it is an array, first, second and third. Okay, so maybe this is red, this is green and this is blue. This is the first image that we are talking about, and that's how, like, we have 3 red, green, blue channel. Okay, sorry, this one may be the red, then this one is green, there are multiple other things, and then blue. So basically you can see that 28 by 28 is the size of an array and 3 are the channel. So if I talk about a single image, the image width and height is 28 by 28, and the channel, there are 3 channels of this image. So it is multidimensional image, multidimensional array. Now we will do what? We will reduce the images. So what are this number representing? These numbers are starting from 0 to 255 only. 0 being completely dark, or 255 being completely bright. Okay, so I want to scale this on a single scale, so I cannot use standard scaler or something like that, and I cannot do direct processing of that of these images. Okay, even though it is on a scale of 0 to 255, there are some values where I have 2 digit, and some places I have 3 digit number, somewhere I can have only 1 digit number, somewhere I will have 0. So the processing and computation becomes very difficult. So it is necessary to scale this data. That is why we are going to divide each and every value by 255. We'll first convert it to NP array, and once we convert it to NP array, and we will divide it by 255. Now the data which was earlier a list is now a NP array. And then labels, which was earlier list, we will convert it to an NP array. Why we are using NP array? Because NP array, NumPy array, is faster compared to normal list. Now we are using labels. You can see it is an NumPy array of the categories, that particular images, whether it is building, forest and sea. We'll split the data. Now the data is nothing but our data, the NumPy array data and labels. We will split it into training and testing. We are putting a test size of 0.25 and training size of 0.75, and random state we are using 42 throughout, and we use train y. We have the train y and test y. Now when we are building a CNN model, we are using a complex architecture here. That's why it is necessary to convert the training, the y data or the values into categorical format. So we are going to convert it into categorical format using two categorical. So we'll use two categorical over training y as well as testing y, and we have only 3 classes. So we are going to create as a categorical format with 3 classes. So if you see, we have 3 categories. So earlier it was 1, 2, 0, 1, 2. Okay. So this is 0, this is 1, and this is 2. So 2 basically represents C. So the first image in the training data is a C, and it is encoded, kind of encoded we have created. So we are using two categorical to encode the data. Why we are doing it? We have to map it with respect to our softmax function. That's why we need to do it. After that, we are using image data generator to augment the data. As I told you that image, a single image in a single proportionate cannot be used for further classification. So images needs to be oriented in different order. Okay, so while training an algorithm, it should not learn only if the data is in a certain angle. If I change the angle of the image, if I provide a new image in a different angle, it should be still be able to recognize what is that image. That is what the purpose of classification is. For that we will use image data generator. So we are using, it automatically generates newer array of images with respect to whatever specification you have given. So we are using rotation range 30, which means it will rotate 30° off and on, okay, on both the directions. So even if the image that we are providing is 30° tilted, it is fine, it will still recognize into correctly. Even if the image is shifted by range 0.1, which means, for example, the image is not the actual image and it is shifted, which means partially it is not visible. If the dog image, if I am talking about the forest image, if it is partially shifted to by 0.1 unit, then also it is fine. We cannot have 0.2, 0.3. If we do it, so we will have more images generated and it will just increase the burden over our model. And that is why we will use 0.1. Right now I am using 0.1. If you have a model, if you have that computational problem, data computational efficiency, if you are using cloud or something, or you have a deployable application, you can increase this ranges and these angles as well. I am just doing it for the sake of demonstration, so that's why I am using very smaller numbers over here. Height shift, width shift is about shifting width, height shift is about vertical shifting, shear range is about 0.2. For example, complete image is not there, partially sheared image is there, so 0.2 degree shear is fine. Zoom 0.2 if the image is zoomed or a bigger image is there, still it will be able to. So I am using a zoom range of 0.2. Horizontal flip, if the image is completely horizontally flipped, still it should be able to recognize, the model should be able to learn from it. And fill mode is equal to nearest. Fill mode is equal to nearest is a method in OpenCV or image processing where if in case there are transitions happening in the data, so fill nearest method will use that nearest method of computational transformation of image. For example, say we have gradient, okay, we have sharp gradient between two images. So nearest method is the nearest interpolation method. We use Lagrange's nearest interpolation method to wherever there is a gradient or there is a sharp edge, and if the image is not, if we are not able to, or when we are capturing the image, something is missing while capturing that image, or something is not identifiable, it should use the nearest interpolation, which means if there is a white color next to this region, so if this particular part is not clearly visible, automatically it should take the white color because nearest region is white. So such kind of nearest Lagrange's interpolation method is used over it. So this is our augmentator. We have not yet augmented our images. So what we will do is we will call in we'll start with building the model and compiling it. So first thing that we are going to do here is we will call the model. So our model is LeanNet, okay, and we are going to build the model. We are providing width, height and depth of the model, and we are going to provide the classes. So there are 3 classes. We are using the optimizer Adam. We are calling it, we have already used or called the model. Then we are using compile. Compile will compile the model based on the loss, which is categorical cross entropy, and it will try to reduce the categorical cross entropy. And optimizer we are using Adam, and metrics we are using accuracy. We can use the model checkpoint for saving the optimal model, and we have compiled the model successfully. Now we are going to we have compiled the model successfully. Now we will create a VGG model. So VGG model, here we are going to call the VGG16 model, build the VGG16 model. 3 is the dimension for the VGG16 model. Number of classes is 3. Here also we are using Adam optimizer and compile the VGG16 model. So for compiling loss we are using categorical cross entropy, and accuracy is the metrics which we want to govern. Okay. Now if we talk about the model summary, so first model is our LeanNet model. So the model summary of LeanNet model, we can see how many parameters. So initially the image comes and 1520 parameters of the weights we are going to develop, and slowly the weights are going to get developed more and more with respect to the activation function and the number of neurons that we are passing. And we are going to train how many weights? So we are going to train 6,03,673 weights total. These are all set of weights. In each layer we can see how many weights are generated. So wherever weights are getting generated, so convolutional 2D, there we need weights. Then convolutional 2D, second convolutional where we need weights, third convolutional we need weights, and here in the dense we are automatically generating more weights because we have specified 500 neurons. So based on the formation of these and these, we are getting this new weights. Okay, so if we try to multiply it, we can kind of get the weights over here, and that's how the weights are getting generated. 6 lakh in the LeanNet model. And now we talk about VGG16 model. Here also similarly it starts. So this is how a LeanNet model is constructed with 6 lakh parameters or weights. Now we talk about the VGG16 model. So in VGG16 as we discussed, it was supposed to have 16 convolutional neural network, but we have only 4 convolutional neural network. So it will develop the neurons or number of weights for this 4 convolutional neural network or convolution operation. And after that we have one dense and one dropout. You can see that earlier it was 256, 94, 208 kind of weights, and it is getting dropout, like we are using 50% dropout. So 1678, 1312 is the dropout, like half of it, like totally the weights are getting reduced. And finally I have only this 3 as our output in the dense layer. So here we can see in VGG model 42,74,790, okay, no, 4 crore 27 lakh 47,970. So here we are training more weights. VGG model we are using more weights. So but obvious, VGG model is going to be very heavy compared to this LeanNet model, and we have not even used 16 convolution operation here. We are just using simple convolution model. And now we will start with fitting the model. So when we fit this model, I have already run it, and we cannot spend more time on it. So I have already run it. So we just observe the output over here. So while fitting the model, so this is our model which we have created. So now we will fit the LeanNet model over the training data. So here, if you remember, previously we have directly used x is equal to train and y is equal to test and something like that. But now here we will not directly pass in the input data. We will convert or augment it. We'll do data augmentation while training the data. See, what is the best part of using this AUG? We are not saving anything in a physical memory. Okay, we are kind of using it on the go, and x is equal to aug.flow we will use to create augmented version of images, and we will use train x and train y. By using train x and train y, it will create different versions of augmentation, like we have discussed earlier, shearing, width shift, and height shift, rotation, zoom, all this kind of different arrays will be created. And yeah, linear, here it is. So batch size is 32. I think we have discussed earlier, 32 batch size. Validation, we are using validation. So here we are using the original validation data, that is text x and y. Okay, validation data as per the train test split. Steps per epoch, we are using the steps per epoch will be dependent on size of the training data divided by batch size. So whatever is the steps, how much steps we are going to implement, that we are going to use. Then epochs is equal to 50 we are using, and verbose equal to 1. So to start with, we can see that initially the validation accuracy is 0.653. It keeps on increasing, and to a point it increases 86, 87, 86. It keeps on increasing. Let's see if we are getting 90. So I am using very few epochs here, which is 50, and by 50 we are getting 8773 as the best so far. Maybe we have some best version above or below, but yeah, 8773 is the best. You can preserve the weights by using the checkpoint method that we have discussed in the previous classification method. If not, you can go ahead with whatever we have. Even this accuracy is best for the validation. So this is a validation accuracy. We are bothered about validation accuracy because validation data is a new data set on which the model will actually give some predictions. Okay, so if we are able to perform on the new data, which means that our model will perform on any kind of new images. So 87% accuracy is given by the LeanNet model. Then we will move forward with VGG16 model. In VGG16, we use the same approach. We create augmented by a type of images. Batch size we are specifying 32. Validation data, we are using the validation data in the train test split that we generated. Steps per epoch, similarly epochs is equal to 50, verbose equal to 1. Verbose is equal to 1 is just to present this information correctly. If you keep it 0, so possibly you will not see all the information clearly. So verbose equal to 0 is all about presenting this epoch by epoch information correctly. So you can see initially 40% accuracy, and slowly it is increasing. We are using 50 epochs. You can see accuracy is going beyond 90 as well in some parts, like here at the end 90.61 is the accuracy. So it is much more reliable as we have higher accuracy compared to the LeanNet model. So it is giving good accuracy compared to LeanNet. So here if we talk about the LeanNet model, you can see if we compare the training and testing, so this code basically helps us to create a chart showing the accuracy of training data as well as the validation data. So accuracy of training data and validation data are kind of going in a similar order, higher in the upper range, and it is following the same trend actually. And same we will do it for loss, and the loss is also going down in the same order for LeanNet model. Similarly, if we do it for VGG16 CNN model, so it is also, so VGG16 is much more, you can see that it is overlapping, the validation accuracy and the training accuracy kind of overlapping over each other, and the loss also will get overlapped to some extent. It will not be, but yeah, it is comparatively better if you compare the loss of LeanNet with CNN VGG16 model. Okay, so after that we will create this TensorFlow.Keras.preprocessing. Now we will use it over a new images. So for that, what we will do, say if I have certain images, I want to test if this images yeah. Now if I want to save these images wherever I have developed this processing, So we have successfully developed a CNN model and we have successfully trained it. We can now be utilizing it for further implementing over other images, testing other images, whether it is building forest or sea, so that we can easily do, we can use image to array. We are importing image to array. We are using load model to load the model if it is saved. NumPy we are using, image argparse, imutil, cv2, matplotlib we are using, and we are using image parse. So what we are going to do, first we are creating a function called as display image. This function is doing what? It will take an array and it will show that array as an image. Okay, so we are using figure is equal to plt.figure, using this plt.figure method from matplotlib, and axis is equal to figure.add subplots. We are using 111 subplot to show that image, and we are using ax.imshow. Imshow will convert that array into an image and show it as an image. Now here also let us just skip this part because we have already developed. Now we will talk about okay, just yeah. So we are talking about new set of images now. So there is a folder called as test examples. Okay, in my CNN project directory, if we talk about, there is a test example you can see test example. So here there are different images, and this is a mix. It is a combination of building, forest, sea. We don't know what it is. Okay, I will do what? I will call one by one all these images and I will test using my model, and my model will recognize whether it is building or forest or sea, and it will label it on that particular image. So let us do it one by one. Let us call in these images. Let us call in these images and put a label on it. So first of all, we will use test image paths and we will sort this data, which is first of all we will get the paths of all the images. The classes that we have is building, forest and sea. So 0 is building, 1 is forest and 2 is sea, and we are using TQDM. We are using the same for loop, and we are reading the images one by one from all the image paths that we have generated. So here we are using image paths over test image paths. One by one I will get one path at a time, read that part, and I will create an original copy of that path, and we will resize that image. Say this is why we are creating copy, because when I do pre-processing of the data now, so it will change the when I'm reading it, so it will change that particular image, maybe in black and white structure or something like that. So I don't want it to change the original image, and when I want to put a label, I don't want to change the label as well. So why we are doing it is, this is my original image and this is my image which I will be using for all the array operation and all. So I will first resize the image the way we are doing. We are converting it and dividing it by 255. We'll convert it to image to array. We are using expand dims to expand the dimension of the images, and we will use model.predict function. So predict function will predict what is there in that image. So I will pass this image array in this predict function. My predict function will learn what is there in this image path, and it will give me an array which is the probability of array like this. So I want, it is going to give me a nested array basically. Okay, nested list. I don't want nested list, I want the internal list, this one. So that is why we are using square bracket 0, and we will print the prediction of configuration, whatever is the prediction. Okay, once this is done, we are going to create a label. This label that we are going to create is nothing but np.argmax of predict configuration. So predict configuration is going to give me this list, and argmax will find out which part is maximum. Say this one is maximum, or this one maximum, or this one maximum. So it will give me the maximum value from this list. So from all classes, so all classes is what? This is my all classes, buildings, forest and sea, and below it say there are the probability values. So I will get the label corresponding to the highest probability value from all classes. So on all classes I will apply this np.argmax. np.argmax will tell me is this high, or this high. So say this is the highest, which is 0.8. So it will give me 0.8 the value corresponding to 0.8 in the all classes. So 0.8 is at second position. So what is at second position? Forest. So here forest will get stored. Predict conf will in here we will get here we will get forest as stored, and we also want the probability. So if you want probability, so predict conf np.argmax predict conf. So it will tell me what is the probability of being that particular value. So it will give me the probability of that data as well. And what we are going to do, we are creating a label. It is a string value. This string value has label which is either building forest or C, and the probability of being a building forest or C. Okay, and then we are using output is equal to imutils and resize. It will resize the images, and it will imutils will resize the original image, and we will set the width is equal to 400, and we will put text on that image. So as I told you, when I use this image, so we are transforming this image continuously. So I cannot label this image now. If I want to put label on it, it will be difficult because it cannot be retransformed. So it is better to create a copy and put the label on that copy. So I have created this original image on which I will put label. Now what is that label? I am putting that label on the original image. So original image is stored as an output with which is resized, and which is width is equal to 400, everything we have done. On that output is my original image. Now on that output original image I am putting a label which is our text format. We are specifying where to put this label and which kind of font we have to use. So CV2 has different fonts, so we have using font Hershey Simplex, a simple format we are using, and the position of the font and size and texture, everything we are specifying. This is the color. Okay, this is the color of that font, this is the thickness or width, and this is like these are different attributes with respect to placing that text on that image, which means I have taken an image, I have tested that image, what kind of image it is, whether it is building forest in C. I have stored that label into label, I have stored the probability, I have created a string label. On it I have the label as well as the probability of that label, and then I am putting that label on the original image. So I have created two copies. So one copy will go for processing purpose in the machine learning or deep learning model, and the second will be used as a copy on which I will place the image label. So I will place the label on that copy, which is nothing but that same original image, and image will be used in the CV2.CV2 color in the original format. So earlier when we have taken the image, the image may not be in the color format when we are extracting the image. So we will convert it to BGR to RGB, which means we are converting the image when we are importing, it is always imported in BGR format. But what we want is it has to be in RGB format. So we will convert that image into RGB, which is the original image content. And then we will display image. We have already created this display image function over here. That function we will be using to show that image, and that's what is happening here. So when we run this, if you see, so yeah, so here when we run it, so we are taking one by one each and every images from test examples. So the first image, as you can see, it is actually a C, but it is trying to recognize it as building. So model is prone to make error. It is a linear model, so it will take it may take some error. This is also recognized as building and here it is recognizing C correctly, you can see. So it is able to recognize C correctly. This is C, this is also C, this is also C, this is buildings, which it is able to correctly not recognize with a very low percentage, 57. So maybe the model is confused. Here it is correctly recognizing, here it is correctly recognizing. Buildings it is wrongly recognizing. So it depends. So here it is correctly recognizing buildings. So it is possible. So the linear model, according to its understanding, it is recognizing whether it is building forest in C. Now the same kind of implementation is going to happen for VGG16. Only thing is the model is going to change. Earlier we have used model here. Here we will be using VGG model. Rest other everything will remain same, and here I have made a mistake, it should be VGG16 output images. Okay, so I have to store it in VGG16 output, and once this is done, you can see it is correctly recognizing this as C because it is a C. This is also a C, 47% confidence, 90% confidence it is saying C. This is also C, 100% C. So likewise, it is correctly able to recognize C's and buildings. Sometimes it is making wrong predictions, like the earlier here it is correctly recognizing this as buildings. This is also a building, 98% confident, and VGG16, as said, it is giving a correct prediction compared to the any other model, or compared to the LeNet model. Okay, because we are using a lesser number of neurons over there, so but obvious it is going to use less. So this is how you can implement a CNN model, take some images and classify it as any categories that you want, and this is the core foundation for any image processing library if you are working on any complex image architectures, image libraries. So we are using convolutional neural network as a backend in every image processing or classification exercise. Now we will start with RNN model as well as LSTM model in a single data set. What is RNN? RNN basically stands for recurrent neural network, and what exactly it does? It is similar to our traditional artificial neural network, but it generates two output. First output is gone to the next layer, and second output that it is getting generated, it is passing out on to the next timestamp. So if you talk about this feed forward neural network, this is our simple feed forward neural network. These are our inputs, and we are for this inputs a certain Y output is getting generated. Okay, but here in this feed recurrent neural network, it is generating, it is taking inputs, it is processing the inputs, it is generating an output, but it is passing this passing a part of this output or hidden state to the new or the next neuron or next row. Okay, so basically what it is trying to do, so the objective of RNN is to preserve the previous memory and utilize the previous memory so as to give output for the current. So whenever we see an association of data where the previous information is relevant to the current output, so there we can use RNN. So RNN takes the output of the previous neuron, okay, output of the previous processing, and that output is also utilized for the current processing. So this particular information basically passes on to the next neuron, which is same neuron for the next iteration of data. So if you want to understand it better, so we can see here how this neuron works. So X is a neuron. This is a simple RNN architecture which we have where it will be some input data will come, and this input data will have certain weights, and it will be processed in this neuron, and some output will be getting generated. Okay, so this output is getting generated, but there is a hidden state which is getting generated back in this data. So if you see how this works, so this is our neural network or neuron, a single RNN neuron, and this RNN neuron is at timestamp t-1. This timestamp t-1, the input at timestamp t-1 is taken, it is processed, and output is getting generated L, and it is also generating a new hidden state V. This hidden state V is getting passed on to the new set of information. When I talk about new set of information, it is not the new layer, it is the next data set or next row in the data set, and in this next state row of the data set, it is taking information of the current row of information as well as the previous information, part of the previous information, and it is going to generate an output LT. Also it will generate a new information, it will also pass this information to the next state after or next row, which means the processing of a single information is not only dependent on the current row, it is also dependent on the previous row. So this is how a traditional RNN works, and this is useful because whatever decision making we are doing in deep learning, it is dependent also on the previous observation of attributes. So that is why it is important. So now let us talk about RNN in detail and the implementation of the RNN. So first of all, we will import NumPy. We know what is NumPy. It is used to process numerical array and numerical operation. We will call TensorFlow. We will be using a textual data now because RNN and LSTMs are usually used on a textual data. So we are going to use a text processor, which is tokenizer, and after that we are going to use sequence. We are going to use paired sequences. We are using sequential architecture to build up multiple layers. Now here we are using embedding layer, simple RNN and dense. What is this embedding? Embedding is used to convert textual information into a meaningful information. So it kind of helps us to restore semantic or meaningful information from a text data. Now we will read the data. So we are using this Twitter comments class.csv. This Twitter comments class.csv is a set of tweets tweeted by different gamers on different games, and they have generated different tweets out there. So if we talk about this data, so this data has serial number, tag, sentiment and tweet. Earlier it was not there. We have set the new column names, that is serial number, tag, sentiment and tweet. Serial number is this, which means this is basically uniquely identifies a player. So there is a player with 2401 as a serial number, and he's playing Borderlands, and his sentiments are assumed to be positive. Someone has tagged his sentiment as positive about the game because of the content, that whatever tweet he has made, which means while he's playing that game, he's totally engaged into that game, and it shows that he is positive, like he likes that game, and that is why he has given such kind of comments. So the comments can be like anything. Now gaming comments are different from the natural language comment. Like normally what we are talking, if it is a product review or something, the comments will be different, but the gaming comments are different. So here we are trying to understand that whether he is positive about this game or not. Like this comment will decide, this tweet will decide whether he is positive about that game or not. So we are all talking about this positive. If you want to see all the data set, we can definitely see this data set. Okay, kind of the algorithm is processing, so maybe that is the reason. So let us move forward. Now we will talk about the data set, and we will see if there are any missing values. So there are 848 tweets which are missing. So when we talk about missing value treatment, it is not possible to treat missing values directly in this data set because it is a comments or it is a tweets given by one. We cannot put something which is fabricated, like we have done in any other machine learning algorithm or any other algorithm where we can use mean, median, mode imputation, where we can use forward or backward fill. Here we cannot do it, okay? Or for example, we are using KNN imputer. We cannot use any kind of imputer, so we have to simply drop these rows. We can use it KNN imputer, but right now it is free, and it is fair to drop the rows wherever missing values are present. So we have dropped the missing values. We are dropping the we are seeing the shape of the data. Now we are left out with 73824 73,824 rows and 4 columns. Now we will talk about sentiments. The sentiments are quite balanced. We can see negative sentiments are higher than positive sentiments. Now these are sentiments for all different games. We are not talking about a single game in general. So these are different sentiments for different games. We'll try to understand the sentiment. We'll convert this sentiment and store as val. Okay, val is a series now. Twitter.sentiment will store the sentiment as a series. Now we will use label encoder, and we will encode the sentiment column. So we will do the encoding for this val, and now we have labels as 33012 So there are 4 sentiments. So sentiments will start from 0 to 3. So these are our sentiments, and now we will also store the tweets. So we will store the tweets as sentences. Okay, so we are storing the tweets as sentences, and we will talk about the first sentence or the first tweet. It is I am getting Borderlands and I will murder you all. Basically this shows that this guy is totally involved and engaged in this game, and it shows that yeah, he is positive, like he's happy with the game. So that's what we are seeing here, and then we talk about the different processing. So first we will process the data. We use regular expression to clean the data. So here what we are going to do is we are going to use a sort of natural language processing, a simple processing we will be doing. We will use NLTK library, we'll use stop words, Porter stemmer, word net lematizer, and we will use TF-IDF vectorizer, train test bed, and we are using stop words, wordnet, and ordinary multilingual word 1.4 version, dictionary or corpus of word. So these are different things that we are going to use today, and we will explain this at the time of implementation wherever we are using. Now starting with stop words first. So we are creating a set of stop words. Now what are the stop words? Stop words, basically when we talk about natural language processing, and what we are doing in natural language processing is we are trying to convert a human natural language into machine readable language. So the comments that we have seen so far are not at all, like, the machine will not be able to understand what this comment is all about. For him it is just a text, okay? So he will not be, the machine will not be able to understand what this text is. So we have to make him understand. So in order to do that process, we have to do certain steps by which we can create that sentence into a machine readable, or for a machine readable machine value, or a equally equivalent machine readable information. And for that we start with certain steps. So when we talk about normally when we are talking in a natural language processing, so the words which are very frequently used have very less weightage in a discussion, okay? So when we are talking about such words, so such words are is, are, at, the, that, why, that's why. All these words are more commonly used in a discussion, and that is why these are not relevant for machine. For a machine it is just an word which is an extra. So we need to remove all those words. So that is why stop words are these words which are used very commonly in a discussion. So we will call it as stop words, and we will kind of create a set of stop words and use it for removing it. Then we will use Porter stemmer and lemmatization. Now see, whenever a word is there, that word will have multiple versions. For example, played, playing, player, players. All these different set of words are originating from the word play. So we are not supposed to use all these words when we are developing. So when we are cleaning a text, what we are going to do is we are going to represent each word as a column, okay? That is what going to be our numerical information, or information which is going to be fed to our RNN LSTM network. So when we talk about this data which is textual in context, so we are going to convert, we are going to have a sentence, we will remove stop words from the sentence, and whatever is left out, we will trim that information, okay? We will use that information, and whatever words are there, we will convert that words into columns, okay? So if we have multiple type of words like player, play, plays, playing, all these different words are originating from a single word which is play. So which means play is important. The alternatives or the derivative of the word play are not important here, because they basically represent the same act, that is play. So in such instances we have to trim out all the additional information. To trim out this additional ing, ed, er, prefix and suffixes, we use stemmer. Stemmer will remove the prefix and suffixes from the word so as to have very less number of words, because see, when we have lot of sentences, we will have lot of words, different words, and for this lot of words we will have multiple columns, and we have to reduce the number of columns. Why? Because RNN LSTM network, whatever network we are talking about, require less information or less number of columns. If the number of columns are more, it will increase the problem of dimensionality, and that will reduce the efficiency of the model. So that is why we apply stemming, which means player, player, playings will not be three different columns, it will be just a single column called as play. That we do with stemmer. And then we have lemmatization. So lemmatization is all about bringing the word to its root form. For example, if I have three different forms of word, good, better, best, something like that, like I'm not giving you the literal example, but these three are positive, superlative, and positive, comparative and superlative degree of a word. So the base root word is good only, okay? So lemmatization is all about converting any word into its base root form. which means even if there are occurrences of good and best in a particular sentence, it will only use good, best will be totally ignored. So the base root form of best is good, which shows if any kind of sentiment across that word. So basically, if two words have different meaning, same meaning, but both are kind of similar version of the same, so it will reduce it. So lemmatization is done based on semantic or meaningful information about it. So we are using WordNet lemmatizer, which is coming from the NLTK stem. So in the stemming part, we have word not lemmatizer. Now here we are using ordinary multilingual word, that is 1.4, and according to it, that is a corpus of set of words, and there we will have different set of lemmatization, stemmer, porter, and then we have stop words. Whatever is defined in that corpus of words, we are going to implement that only. If you want to create your own set of all these algorithms, so that is going to be a totally different, and it will take a lot of time. So better we are using this ordinary multilingual word, which is developed by NLTK. We are downloading it and we are working on it. So now we will start with cleaning process of the data. So for cleaning process, what we are going to do is we are going to take a text from we are going to take a text, and on this text we will convert it to string format and lower it. So once we lower it, we will, anything, if it is capital, small, anything, it will get lowered down in the lower case, and then wherever we can see these two lines are responsible to convert or remove any special characters or any uncertainties or extra spaces from my text. So we are using regular expression here, and this is the regular expression that we are searching in that text. If that regular expression is there, so it will remove that regular expression with empty quotes. So it is happening for both here as well as here. So which means if there is anything which is completely against the regular expression, or which is completely against like if it has special characters or something like that, it will just remove that particular part. And once special characters and extra spaces is removed, then we will go on creating or doing removing the stop words. So now we will remove the stop words from our text. So for removing the stop words, we are using this list comprehension method. For example, if first I will do what, I will split the data text into different words, because I have already cleaned the data now. Now once I have cleaned the data, I will not have any extra special character or extra spaces, and we are using text.split. So when we are using text.split, it will convert the words into a list. So like all the words in that text will become list, and in that list I am iterating over each word, and while iterating over each word, if that word is present inside the stop word, I will not use it. I will not add this word in this list. Okay. So what I am doing is, if the word is present inside the stop words, I am not adding it. If it is not present, then I am going to add. So that is why I am using if word is not inside the stop words, whatever word in that particular list, okay, is not inside this stop words, I am going to add it in this list comprehension list. Okay. So after doing this operation, I am removing all the stop words which are there, and after that I am using dot join function. So now we are talking about cleaning the data. So we have the text, we have information in the form of text information, and we have treated the text information. We need to treat the text information, like for example, we have a text written by someone as a comment or tweet. So we need to remove unnecessary information, because if we do not remove it, it will just get overloaded, like the model will get overloaded with junk information. So first thing what we will do, we will create a function called as text cleaner, and text cleaner takes textual information as an input, and first thing we will convert this textual information into string. Why we are doing it? Because maybe in certain regions we have numeric information as well, so we will convert that as well into text. We'll convert it to lowercase after converting it to text. And then why we are converting it to lowercase? Because capital word and small word will be considered different if we do not do it. So that is why we will convert everything into smaller case. And In these two lines, we are removing a special character and extra spaces. So we are using regular expression to detect if a particular regular expression, for example, empty space is not present. So wherever is the empty space, it will remove it with empty blank quotes, and wherever it is present or any special character is present, it will remove it with blank quotes, like it will replace it with blank string in the text that we have provided. After that, we will use list comprehension method to check if a particular word is stop word or not. So after cleaning the text, we will not have any special characters, empty spaces. So now we have only words inside that text. So we will use the split method. Split method is going to convert the text into list of words. So once we convert it into list of words, we will see that if that word, whatever we have converted, is present inside the stop words. If it is not present in the stop words, we will put it into this list, otherwise we will not. The meaning is, if that word is not a stop word, we will place it inside this list. And we are using join method. Join method, we are putting some space over here, space, because in this list it is going to be a list of words. We do not want list of words, we want a text in entire comment. So we have removed the stop words, and we have we are joining that words after removing the stop words. So we have removed the stop words, and we have a text which is free of stop words, and this text is again used, and on that text we are going to apply the stemming operation. So here we are not removing anything, we are just applying stemming. What is stemming? Stemming is a process of converting that word into the base root form. Okay, so when we talk about the base root form, which means we are going to remove the prefix and suffix from it. We can also do lemmatization here, like here we can remove this and we can do the lemmatization. I have already given the code. So lemmatization will do what? It will create a word of base root form based on meaning, okay, based on literal English meaning. Then we will return that text. Basically what is happening here, we are taking a text, we are cleaning it, doing stop word removal, doing stemming and lemmatization, and giving a text which is free of stop words, which is free of lemmatized version of words, and which is also free from any special character. So we have a cleaner text here. Now we will create a column called as comments clean, and this comments clean column is it will have all the text which is refined with respect to this text cleaner. So on the original tweet column, we are going to apply text cleaner function. So we are using the apply method. So tweet dot apply, on this we are going to apply this function text cleaner, and automatically we are getting a clean version of text. As you can see, earlier it was written im getting on borderlands, but now we can see getting is becoming get, on is getting removed because it is a stop word, borderlands is becoming borderland, murder is there, and rest of the words will be there. Similarly, all other words like just realize that the Windows partition of my, and you can see just is getting removed because it is considered as stop word. Realized is become realize, okay, ed is getting removed because it is just using the stemming operation. So now earlier we had suppose 10 words, now we have only very few words. Here also we have more words, but here we have very less words. So we have kind of cleaned the data, and this is our first sentence. Now we will do the act of tokenization. Now whatever we have converted or cleaned, we need to use it for model building. So we will first create it in a machine readable format by using tokenization. Now what is tokenization? Every word will become a token now. So for tokenization we are using tokenizer, which is present in NLTK, and we will clean all the sentences and we create the clean sentences. Now tokenizer dot fit on text. So we are going to apply tokenizer method on clean sentences that we have just developed, and we will use word index. So word index, if you want to see, so tokenizer dot word index. Now what is tokenizer going to do? Tokenizer is going to assign an index to each and every word which is cleaned version. So game becomes 1, play becomes 2, getting was converted into get, and get becomes 3, like becomes 4, im becomes 5. Likewise, these all words will get converted into some index. Some index will be assigned. Now these numbers represent a particular word. Every number represents a particular word. This we have to keep in mind. And then we will apply tokenizer to tokenizer, and we will convert text to sequences. So we are going to create sequences of this tokens. Okay, so if you want to see sequences, we will talk about sequences. So sequences are basically this. So this is 5 3 69 1164. So what is this 5 3 69? You can refer here. 5 is basically im, 3 basically is get, like that. So these sequences are the encoded version of your word, which is getting developed by WordNet tokenizer or tokenizer. Then we are going to use max length. Why we are using max length now? We need to identify the longest sentence which is there inside my data. Why we are doing it? Because we also want to do paired sequences, because whenever we are creating an array, the array should be uniform. It should not be that the first row has only 3 words, like here we have only 4 words, here we have only 3 words. So it is not uniform, the data is not uniform. When we want to feed this to a neural network architecture, the data has to be uniform with respect to rows and columns. Certain rows have only 3 columns, certain rows have 5 columns, certain rows have 10 columns. So what we will do? We will do padding operation. The padding operation is all about adding extra rows. Wherever we have extra rows, we will put it as 0. So for that we will use paired sequences. Paired sequences will take sentences which we have developed or the sequences we have developed, and it will pad with respect to maximum length. It will use 0 padding, which means wherever the words are not present, it will put it as 0. So it will create an array of 163 dimension. Why 163? Because the maximum length of a particular sentence, which means a sentence having maximum number of word is 163. And there are 73824 rows into it, and we will use so this is our sequences. If you want to see paired sequences, you can see this is the padded sequences. Okay, so if we talk about sequences, so sequences 5 3 6 9 1 1 6 4, this is our sequence. The padded sequence version is 0 0 0, and here we have 5 3 6 9 69 1164. So what are these 0 0 0? These 0 0 0 are basically other words. For example, in our statement, it was im get borderland and something like that. The word was there. Okay, im getting borderland and something like that. The word was there. But this is in the sentence number 1, only these words are there. That's why we are getting indexes for these words. In some other sentence we have some other words. Okay, say play cricket, something like that, play cricket. So play cricket, maybe play cricket index is something else. Say play is here and cricket is say somewhere here. So these are 2 different words, right? So in the sentence where we have play cricket, so the paired sequence will be different. So here we will have 0 in all places except this place where we will have the value of the token or the index value of the token. So this is how we are arranging the data in a form of numeric representation. And then we are using clean sentences. We will see that clean sentences is im getting borderland murder and im getting borderland murder. This is how it is represented, and sequences is quite different. Okay, now we will use labels.shape to see what is the shape of the data. np.unique labels. So to see how many unique labels we have 0 1 2 3, which means 4 unique labels we have. Now we will use RNN model. So in RNN we are using embedding dimension of 16. Embedding is the process of converting a corpus of word or a token of word into a meaningful architecture of words. So we are using vocab size of length of word index plus 1, which means the size of words that we are using. What is the total size of the word? So we have word index, total word index, how many total words are there in all the possible words, and we will use model, we will create sequential model. So sequential model, first layer that we are talking about is an input layer. So input layer has to be embedding layer, because embedding layer will convert that input information into a meaningful information, and we are going to use vocab size as the input size, and embedding dimension is 16, that we can fine tune, and it basically represents how we want to do the embedding of the data. Input length we are going to use is the max length. So max length is the total length of number of columns. So the input length is going to be total number of columns. Then we are applying the simple RNN. So we are applying simple RNN with 32 neurons, and we are using dense activation function, which is having 4 as the output, because this is an output layer. So output layer we have 4 neurons, and activation is softmax. So this model takes input, it converts it in the embedding layer, it converts it into meaningful information based on the word net we have developed, and it applies simple RNN over it and dense. So simple RNN basically takes information of the current row and also output of the previous row. So this is how it works. And then model.compile, we will compile with the help of optimizer, which is an Adam optimizer. We are using loss as sparse categorical cross entropy. Metrics we can use accuracy, and model.fit we are using padded sequences. Padded sequences is the numerical equivalent comment. So whatever comment we have created, the numerical equivalent of that comment is going to be padded sequence, and labels is the corresponding label to that particular padded sequence. And epochs we are using 10, verbose is equal to 1. This is going to be heavy, so that is why we are keeping epochs as 10 only. And here what we are doing is we are just creating a sentence and testing this model. So we have created a sentence, this movie is amazing or something like that, and we convert the data, this comment, into a tokenized version of the comments. This is a simple word, so we are not doing any kind of cleaning process. We can do the cleaning process, it is very simple, we can do it, but we have just ignored it. We converted these words into padded sequences by using pad sequencing. We are using model predict. Model predict will model is our sequential architecture model. It will predict the padded test sequence that we have just developed, and whatever is the output, so it will give 4 probabilities as output. Out of that 4 probability, we have to identify which probability is maximum. So that we are going to do with the help of argmax, np.argmax, and that is nothing but the predicted output. Okay, so that sentiment of that particular comment, so sentiment of this comment, this movie is amazing, is what we are going to predict. Okay, whether it is positive, negative or neutral. Now we use this epoch by epoch. So in every epoch we can see there is a considerable improvement in the accuracy of the model. We have used very less number of epochs, so we are able to get very higher accuracy. And the sentiment prediction, it is giving 1 for that word, that is this movie is amazing. For this movie is amazing, the sentiment is 1. Now let us try to see what is the sentiment 1. So sentiment 1, so let me check what is the sentiment in the label. So if we talk about val, so val we can see positive, positive, positive. So positive is 3 in labels. So if you want to see what is the sentiment, let me le dot, we are going to use inverse transform, and in that we will pass on value as 1. Let's see. So 1 is negative sentiment. Okay, so it is telling us that the sentiment 1, so this comment that we have provided is a negative comment. So it depends on the model how it is trying to learn from the data. So maybe it is not able to correctly recognize the patterns, or maybe this comment with respect to gaming is maybe it is someone is saying in irony or something like that, so it is considered as a negative comment. So maybe such kind of learning our model is doing. So it is totally dependent on what information we are passing. So this is a comment which is negative, and this is how we can create a simple RNN. The objective here is to use a simple RNN model which can understand from the previous data. Now we will move on to the implementation of this model. So we can implement this model, or We can show it to someone who wants to just try to check out and play around it with the help of this Gradio interface. I will quickly go through it. We can simply get this code from the Gradio website. So what we are doing here is we are taking Gradio as an input. Gradio is an website or a library which allows us to create a web interface. So for that we will take Gradio, we will import NumPy, we will import pad sequences, label encoder. We are going to create a predict sentiments as a function. So what is this predict sentiment function is going to do? It is going to take some text, it will process that text and it will create a prediction, okay, and it will tell after predicting whether it is in which class, okay. It is, so basically what it is doing, it is using our model and it is predicting from it is taking a text and predicting whether it is positive, negative or neutral. So that is what this function is going to do. Why we are developing this function? Because Gradio interface requires a function, okay. So we are taking Gradio interface here and the output is the predicted label. We are creating an interface iFace by using gr.interface, and in this we are passing in this function. This function takes input as a text and gives a prediction whether it is what kind of text it is, positive, negative, neutral. Inputs is equal to text we have taken, the input format we are taking is a text, and the output is also again going to be a text, but this is an input. So here we can type anything, but here we cannot because this is an output, we cannot type here in the output section. Title is sentiment analysis, and this is some kind of description that I am giving. Enter a text to predict whether it is positive, negative, somewhat like that. And iFace.launch, it will create this local host, local URL. You can also have a URL which is not local by simply putting share is equal to true, and that will create a URL which can be shared with anyone, which is only applicable for 72 hours. And in this I can simply type amazing or any word I am just typing with respect to the context of this game. It is telling that it is negative, and if I put something like this kill you, so let's see what it is telling that it is a neutral comment. I'll put unhappy and let's see what it is putting. So it is telling that it is a negative. So based on the information which is we are passing, it is going to just give us whether it is positive, negative or neutral. You can click on this link and it will open as a web page over here, the same exact. So this can be used for someone who wants to share it with like create a shareable version of your code. You can use it. Now now we have created this function. So this is just to text, we will ignore it. This is the same function that I have used here. So I'll just remove it and let us come over LSTM module. So now let us try to understand the next algorithm, which is the text processing algorithm, that is LSTM. So the problem with traditional RNN is it is able to recognize only the first few entries or the previous few entries, but it is not able to retain the long-term memory of that particular data. So when we are having such kind of scenario, then we can use LSTM architecture. So what is LSTM? So LSTM stands for long short-term memory architecture. So the problem with traditional RNN is RNN remembers only the previous memory, which means the very previous memory, not the old memories. So whenever it is a long-term memory, RNN is not able to recognize. So in order to overcome this problem, we have an architecture called as LSTM, which stands for long short-term memory architecture. So this long short-term memory network is all about retaining the very previous information as well as the current information, and recognizing whether the previous or the old memories are important or not, or whether we have to forget it or store it. So let's try to understand the architecture of LSTM in detail, and then we will try winding up with understanding LSTM in detail. So this is our LSTM architecture, and in this LSTM we will take memory as C of t minus 1. So let's try to understand. So this is our memory, which is then long-term memory we can call, long memory we can call, and it is also called as cell state. In LSTM we have different gates. This is our hidden gate, input gate, this is our forget gate, this is our input gate, and this is our output gate. So these are different gates. We can see clearly it is mentioned what are these gates. And in forget gate we have sigmoid activation function, in input gate we have sigmoid plus tanh activation function, and in output gate we have only the sigmoid activation function, and this here we have tanh activation function which is coming from the cell state. So these are different activation function which are there. Now let us understand what happens in this LSTM architecture. So LSTM has this old memory running. So old memory is a formation of different set of information from the older memory, and then we have hidden state. Hidden state is the very previous memory. So hidden state will have memory from the previous timestamp, okay, which means say if I'm talking about an episode, okay, if you are watching a web series, so HT-1 is the previous episode, and CT-1 is nothing but all the collective memories of previous episode as well as today's episode or yesterday's episode, not the today's episode. So it is a collective memory of all past episode, and this is the memory or information of the current previous episode, okay. So this is the difference between this long memory and this hidden state, okay. Now we will talk about input X. So this is the today's episode. We are trying to remember today's episode. We are entering this information of today's episode as well as yesterday's episode. So we are taking today's episode and yesterday's episode, and we are passing it into this forget gate. So forget gate has sigmoid activation function. Sigmoid activation function helps to store the information whether it is relevant or not. So it will convert or process this information on a scale of sigmoid activation function with respect to probability values. It will generate a probability value, and it will tell us that whether it is this information which is coming from the current input information and hidden information, whether this information is relevant or how much it is relevant to the old memory, how much it is informative to the old memory. Okay, so based on this sigmoid activation function, the probability value is generated, and that probability value is nothing but our current memory, and this current memory will go into this old memory. When it is going to this old memory, we can see there is a dot product which is happening, where we can see there is a dot product. So if this probability value is very low, say if it is 0, which means this current information, when we process it, we have the value 0, and when this 0 is getting multiplied with the old memory, it will nullify all the information which was coming from the past. Or this current input information is responsible to tell us that whether we are going to keep this old memory or at what proportions we are going to keep this old memory, whether it is relevant or whether it is not. That is why this forget gate, we call it as a forget gate. Say if the output of sigmoid activation function is 0, so if it is 0, then when we multiply it with old memory, it is going to forget the old memory, and the output, the multiplication of 0 with this old memory, we are getting output as 0. So that is why it will forget the old memory, and that is why it is called as forget gate. Forget gate responsibility is to just take today's information and yesterday's information and see whether it is relevant or not with respect to old memory, and if it is the old memory is not, if it is not the information or the product, whatever is the output value, if it is very low, it will reduce the old memory value. And this is how the old memory value, whether it is going to get expanded or reduced, will be decided with the help of forget gate. If the value of sigmoid activation function is very high, it is closer to 1 or greater than 1, if it is closer to 1, which means that the today's episode was very interesting, and we are going to add this episode with the we are going to multiply that value with the old memory, and it will increase the old memory to some extent or keep it as it is. Okay, it will keep the old memory as it is, or it will reduce the old memory. That is what this forget gate is going to do. The objective of a forget gate is to either forget something or either keep it as it is. That's it. So that is our forget gate. Then we talk about input gate. So in input gate we have two parts, that is first is input T and this is CT, candidate memory. Input gate has input memory. So first what we will do, we will pass in the hidden state and input state into this input gate, into this sigmoid activation function, and we will pass the same to the tanh activation function. When we are passing it to the this sigmoid activation function, similarly the same way it will decide whether it is relevant to the current information or not. If this value goes very low, the product of this input information or the memory that we are having today and the process version of today's information, the product is also going to be low. So tan h is going to do what? Tan h is going to convert this information into minus and plus 1. Minus means negative memory, plus means positive memory. So when it is converting the number into, say, whatever value, minus 1 or plus 1, this IT, this information will reduce the effect of, if this value is very low from the sigmoid activation function, it will reduce the effect of this tan h because we are having a product of it. Otherwise, it will keep it as it is. If this value is 1, it will keep the tan h value or today's information as it is, whether it is positive or negative memory. Say if it is positive memory, it will go here and it will add to the long term memory. It will get added. So long term memory, if the forget gate has spared it, forget gate has told that no, this current information is relevant, and let us keep the memory as it is. So it will, a new value of the current episode will also get added to this existing pool of information. And once that is done, this combined memory will go inside this. So we have added memory of the today's episode. We have added memory of the today's episode. That is why it is called input gate. This is adding input to our today's episode. So now we will take the cell state. Cell state is a combination. Now in the output gate, we are going to take the cell state, which is nothing but today's memory and yesterday's memory. And we are passing it our input information as well as hidden state here in this sigmoid activation function. So this sigmoid activation function takes the today's information and yesterday's information. It will take the long term information of today and yesterday, and here it will apply sigmoid activation function. So sigmoid decides whether it is relevant or not relevant. If it is relevant, it will multiply and keep the yesterday's information as it is, which means, so we have this long term memory coming in. This long term memory is put in the tan h activation function. It will convert the value into -1 and +1. So if this long term memory is good, it will go in the positive direction. If it is not good, it will go in the negative direction. So you say if it is positive, so we have added today's memory with filtering it with respect to softmax function, sigmoid activation function. This sigmoid activation function. So now the tan h activation function takes the old memory and old and the current memory basically. Now here we have added the today's memory, right? So it will take today's and old memory, and it will scale it on a scale of -1 to +1. Okay. Now we will decide that whether like this hidden state and today's memory, like yesterday's memory and today's memory, will go inside this sigmoid activation function. And this sigmoid activation function, whatever is the output, it will be multiplied with this tan h value. So whatever is the output of this tan h, will multiply it. And the purpose of doing it is just to see that today's memory or today's information is relevant and contextual with respect to the old memory. So old memory is added, today's information is considered whether it is important or not, it is also added, and the old memory in combination with today's memory will come here, and the relevance of old memory and today's memory is decided here. It will go inside, it will get multiplied. If the value of sigmoid is 1, definitely as it is, today's memory and old memory will be passed on to the hidden state. If it is not, so reduced version of it will be passed on to the hidden state as well as the output. So this is the output gate, and this is going to give the output of this neuron, and this is the hidden state HT, and this is the cell state CT. So cell state CT is a formation of previous memory, and whether it is whether we are forgetting anything from the previous memory or not, and today's memory will be added it or not with respect to the processing done here, and whether if it is added as it is, the cell state will move on forward. So what is the cell state? Is a combination of old memory and today's memory if the forget gate has spared that particular memory. So this is our hidden state HT, and later on it will move forward and it will keep on like we will have similar architecture of LSTM ahead, and it will take like that. So this is the timestamp HT -1 and this is the timestamp HT, and it will, the information is going to go to the next timestamp. So that is the difference between RNN and LSTM. So LSTM takes into consideration the old memory, while RNN doesn't take into consideration the old memory. So now we will build up the LSTM model here. So LSTM model here we are going to call with the help of layers. We are going to call the LSTM layer and dropout layer, and we are going to create a model complex LSTM, which is a complex LSTM model, and we are going to use sequential architecture over here. And on this sequential architecture, we are first taking input as embedding layer. Embedding layer, why we are taking? Because embedding will enable the meaningful information of the word net that we have created, or the word indexes that we have created. So vocab size is decided according to so we are going to use the same vocab size because the data set is same. Embedding dimension is going to be the same that we have used previously, and input length is the max length. So here it will tell us that how much input we are taking. So what is the token size? So we have 163 as the token size, or the total number of columns. We are taking that many number of columns. We are using LSTM now. So LSTM, we are using 64 neurons in this LSTM, which means we have 64 such kind of neurons, similar neurons parallelly, and these are similar to it. It is connected to the to current layer as well as the upcoming data points. Then we are using return sequences as true, and return sequences to get the output of the current layer as well as hidden state. We are going to create it. Then we are using dropout layer of 0.5. So we are going to drop out the LSTM networks. Here we have 64, here we have 32. So like we are partially connecting these two LSTM layers. Then we are using dropout of 0.5, and we are connecting it with the dense layer, activation layer, with 64 neurons. So which means this layer and this layer will get connected partially with 64 neurons. And then we are using a dense activation layer with 4 as an output, because this is an output neuron or output layer. And then we have the softmax as an output, because classification has to be done always in the form of softmax. Now here we will implement or compile this LSTM architecture. So for compiling this LSTM architecture, we are using this Adam optimizer. We are using loss as sparse categorical cross entropy, and metrics we are using as accuracy. Then we will fit the data on this LSTM that we have created. So we are using padded sequence, which is our input data. We are using labels, which is our output data. Epochs, we are putting 10, verbose equal to 1. So this will take a lot of time because we have multiple layers here, and it is embedding also is going to happen. So it will take a lot of time. After that, once we have done, we can see there is a considerable improvement in the accuracy level of the model, and it is also taking into consideration the old comments as well. So which is actually not to be there in this scenario. RNN is fine. We can use RNN there, but yeah, which if we are using context also, the old context, so that will definitely help us whether to recognize a comment as positive, negative, or neutral. So we are using the same comment over here, but the only difference is the model that we are going to use is LSTM model. And once we use this LSTM model, we'll see that what kind of category this particular comment stands into. So it is in the 3 category. 3 basically represents positive. So this is a positive category. Now we will see the Gradio interface. So we are using the same Gradio interface to create a web interface of the comment, and we are using the same process entirely. We create a function. The only difference is this function has model complex LSTM as the model of prediction. It is not RNN model, this is LSTM model, and it is going to give us a predicted label on that data, which means it will take some text and it will tell us that what is the category of that text. And we are using gr.iface and gr.interface, and interface we are going to use there are 2 we are taking function, and we are taking text as input, we are taking putting text as output. This is the title and description, and when we launch it, this is the web version of it, and this is where we can put any text. We can put just amazing or something, and let's see what is the output, and it is showing that it is positive, which means LSTM model basically works better than this RNN model because it takes into consideration the previous memory as well. So this is how a LSTM architecture or model basically works. So that is this is how basically RNN LSTM can be used for working on text classification data. So we have seen text classification, how we can do it with the help of deep learning model. We have seen image classification, how we can do it with the help of deep learning CNN model. We have also seen what is regression, how we can do it on using the ANN model. We have also seen classification, how to do it using ANN model. We can implement any kind of classification regression task that we want to do using this ANN model or deep learning concept. So it is similar to machine learning, but yeah, we can do a lot of detailed neural level analysis of any data using deep learning.